felt very proud of myself because
We're good.
now I know exactly how to do it. I might like write up a little thing about how.
Yeah, yeah, and I mean, we could do it collaboratively.
Yeah.
I mean, if
Totally.
you know,
We
just
should
make
write
sure
up
we don't
something.
lose anything. Um,
So it starts at 55.
okay, so it says it's live, but it's not really going to be online until 5 minutes.
Yeah.
What was I going to say? Oh yeah, I have to restart OBS when I connect the camera.
Oh.
I just
And it
yeah, it's
automatically
just-
goes back.
Yeah,
Yeah, the game changer for me was this, where you find this. Oh, oh yeah, go live. So yeah, like in like that button here that says manage broadcast, and then it actually shows the one you just created. And that's the
yeah,
process. Actually.
yeah. No, that's the
That's the
thing. That's
missing
like
piece. That was
like breathe easy at that point.
yeah, exactly.
Easily, yeah.
I didn't realize you guys were doing a behind the scenes thing too. That's
Well, it's just Kevin because so Kevin and I started a collaboration this year, really. Well, actually, we started meeting last year, but we realized it's not sexy work. This kind of stuff is not sexy. Like I'm making a film about a band, a Chapel Hill band that I really love, and I'm doing a lot of storytelling, like history of SSRI, like a bunch of different stuff that's like storytelling. That's the stuff that I love doing, and that I, trained to do it. I want to do. This stuff pays the bills. It's not sexy, but it's like, you have to do it.
Yeah.
And I'm happy to have it. Like I always, one of the things I've always said is like, what you say you're going to do, when you say you're going to do it at a high level, and you have lots of business. And that's what I've done for 17 years. So anyway, Kevin, I realized in the fall that Kevin outbid me on the project, and I was like, shit, like we shouldn't be competing against each other. We should be expanding high. So we got together and we created this idea of Blue Lane. It doesn't really mean anything, but I mean it's Blue Lane Video. We're going to do the stuff that's not sexy that there's a lot of.
Right.
For Duke and UNC and
not
hopefully NC
compete.
State. Yeah, not compete. Like lectures, events, performances, talks, whatever, that sort of stuff. And then interviews with students. Like testimonial stuff. Like it's not hard, it's not sexy, but there's a lot of it, there's a lot of demand, and if we can do it well, and streaming stuff too now. If we can do it well, there's going to be a lot of business. And then we can train subcontractors to do it, and we don't have to show up all the time. And we could, maybe one of us will be there, but,
That's great.
Yeah.
You told me that a lot of still photography. Right?
Yeah.
It's a good combo.
Yeah, still is his thing. It's weird because they're like two different. There was like two different languages. I think of it like German and Portuguese or something, where you're like, okay, some elements translate, but still photography. When somebody says we do still photography, I'm like, is natural lighting okay?
Yeah.
Because I don't do flashes and all that kind of crazy system. But but then when a still photographer tries to do video, they don't know how to edit, they don't know how to think in terms of linear stuff. So yeah, I mean, a lot of people make that transition, but I get really nervous when I hear somebody say they're a still photographer doing video. I'm like, do they know what they're doing? Maybe.
Yeah, of course. Yeah, it's a different scale.
Yeah, exactly.
One of them's moving, one of them's not moving.
Exactly. Yeah. It's a whole other dimension.
Yeah.
Okay, test. How's this going? Test. Is the okay, test. Here we go. Good.
Testing. Testing, is this working back there? Testing, does this work up in the back? Can you hear me in the back at all? Is this coming out? Maybe not. Testing.
Good morning, Jim.
Good morning, how are you?
Fine, fine. How are you?
Doing well, I think. Is this coming in the back of the room? Can you hear this?
A little bit.
Connor, can you hear this in the back? He can. Hello? There we go. That's working. All right.
It's
Get it
amazing.
down just a little more.
Yeah, small difference.
Hello? There we are. Maybe. Testing. All right. Can you hear me on that side okay? On your, on the machine mic? Gabe, can you hear me all right? Yeah. Okay.
Yeah.
Just doing an ear check.
I realized I left this on all night.
Oh
I
no.
mean,
Is that gonna hurt?
me.
Oh.
I just got home. I was like, oh, I forgot to turn that off.
All right, folks. Coffee is coming. We promise. We're not sure exactly what the snafu is. Something at Panera is not working quite right. We suspect that someone just didn't show up at work this morning. The backup coffee is brewing. It'll be ready in just a moment, so we'll at least have a limp across, and we can go with that. I recognize that I'm a lot to take on a normal day. Without coffee when you start in the morning, that's a bit much, so I appreciate you being here. So, all right. The plan today is to move over to the modeling sort of column of the work we wanted to do for this week. And so, let's get this going. So the plan is we're going to work through a series of different steps today. So the first talk today is going to give a little bit about missing data. So we're going to sort of bridge from the data collection yesterday and think about the distinction between what the data you missed and the data you have, and then we're going to move on to some sort of really high-level overview of what network regression models kind of look like and what the classes of those models are, just to get you sort of seed in the back of your head. And then we're going to work through a series of, I think Craig should be here any minute if he's not here yet. He'll talk about a certain kind of model, which is known as the peer influence model, sort of theoretically. And then we're going to jump into some more statistical sort of bits. And then Tom is giving us, Tom Valente is giving us some work on interventions, and then we'll do some work on visualization and so forth. So it's a pretty packed day. I think I'm forgetting somebody on the schedule. So yeah, and Scott Duxbury. So we'll start with the first set of models, thank you, that's what I remember. The first set of models are cross-sectional, and the second set of models are dynamic. So you'll get a sense of what all those are. That's I want to be, that's a lot, right? And I appreciate that. So this is when I had that little picture of the fire hose. Today is that day, all right? So don't worry. It's, just hold on tight. You'll be fine. And all the slides are there, and you can go through it. The key, like I said, of the first day is to try to understand the process and the reasoning and this kind of stuff, right? A bit of basic housekeeping. Tonight we have a barbecue down on the deck, so if you're up for that, please swing by. If you wanted a non-pork-centric meal, let me know. If you hadn't, let me know. We've ordered a few of them from Pure Soul for everybody that says local. They're a great vegan. They're probably the best vegan place in town, so if you're interested in that, let us know and we can make sure that happens. Otherwise, it's just, there's going to be beer and barbecue on the deck, so hope you can join us. There'll also be not beer if you don't want, so that's the plan. All right, let's jump in. I guess no time like the present. So one of the key elements, the program kind of had it backwards. We're going to focus, the main focus of this talk is going to be on missing data. And this is a set of work that John Morgan, myself, and Jeff Smith, I don't think John's quite here yet this morning, the three of us have been working on in a series of papers that Tom was kind enough to let us publish in Social Networks with Roman numerals, which was always one of my goals as a scholar, was to have Roman numeral papers. And so I think Ashton beat me. He has a 5 on one of his papers, which is pretty good. So we made it to 3, and then we're sort of shifting gears a bit. But There was this intuition coming out of the early work in social networks, particularly the work in anthropology, that these are system measures and that any missing data was going to destroy your inference and you're going to do anything. And the question was, well, how bad are we? Because we never really get a full sample, right? So we know that even under the best of circumstances, we end up with missing data. So if that's the case, like, should we just pack up and go home, or do we have a hope that we're going to get something good out of this? And so the short answer is, it ain't nearly as bad as you think it is, and it turns out we can know a lot from it. So we're going to talk through, first conceptually, how missing data is generated and the ways that we think about it, and then some sort of just basic logical reasons about what it means for your inference, and then we're going to talk about sort of our finding from a set of Monte Carlo findings and what to do about it. So the basic idea is that if this is your real world out there in the population, you go out and sample what you can and try to get everyone to take your survey. A few people refuse. And so the data you end up getting, like in this little example, all the red people just didn't take the survey. The data you get is a sample of the data you wanted. So it's never a full representation. Now it turns out that there's lots of different flavors of missing data. You can be either missing data on nodes or you can be missing data on edges. We're going to focus on the missing data that comes from the nodes being missing. So we assume that when nodes are missing, when people refuse to take your survey or otherwise don't want to be part of your study, whoa, what was that? Should not have automatically moved. When that sort of type of thing happens, you end up with all of their edges are gone as well. It can also be the case, of course, that people just don't remember to answer or don't name people. So even there, you can have missing data within ties, but I'm going to ignore that for today. So what does missing data look like? From a very practical standpoint, when you go out and give someone a survey, and this is what the data looks like from your respondent's point of view, there's lots of different ways that you can generate missing data. Probably the most common way is that people nominate others in the network that you don't have any information about, right? And so these are the people that they nominated that either weren't on your roster, was a name you couldn't match, or refused to take part in your survey. And in that case, what happens is when multiple people nominate this person, you as a respondent, when you see them, you can't tell that they're the same person. So you often get this, not is it just that the data is missing, but the information you get about those others that are outside, like some proportion of them are going to be conflated, and you have to treat them as if they're separate. So the most common, like this is the most commonly comes out of survey features, where you end up with some kind of roster or something. And for example, in AdHealth, we had to build the rosters in the summer, and kids would move in September before we gave the survey. So there's all kinds of kids who were in the room who weren't on the roster, and so when they get nominated, you couldn't know if they were the right person or not. So they're unmatched. That's what the UN stands for. Same thing, of course, happens to people who are outside of your boundary. So remember, network analysis assumes that there's some kind of a boundary specification, often a school or a company or a hospital or something like this. When that happens, again, if I nominate someone outside the boundary, we can't know if that person is the same person or not. There is one solution for this, which is to collect some kind of minimally identifying information so you can do some kind of smart matching. So it's not unreasonable to ask the gender, for example, and race and age, and things that would help you say, well, I know these two people are different, and it's possible that these two people are the same, and you can play some games about figuring out how much that distorts your measures. Now, oftentimes, when you have these kinds of features, right, you'll end up with data that is like, this is the same picture just from a different point of view, where the person, the focal person in this case, is not on the roster at all. You can have people who name others, but they can't be named in return. And this non-roster problem really creates an issue of asymmetry in your data. So you'll end up with lots of people who get nominated who are receiving ties who couldn't nominate ties because they didn't fill out the survey. But you also then get people who filled out your survey, but they couldn't be nominated in return. And so you have to make some assumptions about what proportion of those ties are reciprocated. As a very practical matter, when you do these kinds of models, what I recommend doing is when you get your data, you're going to have a set of edges, and I'll show you right here. When you collect your data, there's always going to be some set of nodes for which you have all of the information. So these are all the relations amongst the people who are on the roster and nameable, right? So that's your minimal set, your minimal coverage set. So you know all the relations amongst that realized boundary. And so it's good to take that data and treat it as one set of models. But then you can also just assume that all the rest of your data is there as well. And so whenever, it's a little frustrating with colleagues that I work with, whenever they send me data and say construct measures for me, I'll end up creating like 7 different measures for each, 7 different versions of each measure, because you're going to have the minimal set amongst just ties, you're going to have the maximal set for the ties that include all those out bits. But you have to understand which kinds of measures are good for each of those. And so if you're really interested in reciprocity, then you really can the only good thing you can do is focus on the ties within the set that you have full information on. If you're interested in things like global centrality or centralization, then the full network might be better because you have a better coverage of what's there. Right? And so thinking about how your data matches your problem is really important. Now what these next set of slides are designed to show is this logic of what information you have when you have a design-based sampling strategy. So such as many of these partial network analysis sort of strategies, in which you start with usually a seed of some sort or some set of seeds or some set of people who are willing to take your coupons in an RDS, and you interview all of those folks, and then they recruit others, or you go out and you recruit the people they've named. When that happens, you end up with this wave structure. And the beauty of this kind of wave structure is you actually have a lot of information about people that you might not think that you have. So you obviously have all the information amongst the people who filled out your survey, but you also have all the relations between, all the null relations between the people who didn't fill out your survey or the people who filled out your survey and the new people connected. That is the people like in sort of this ring of the set. Because if there was a tie there, presumably your focal actors would have named them, right? So in some sense, the zeros here, the non-tie from this person to this person is real, because if it were there, they had the opportunity to name that person and they didn't. And so the whole point of this slide and the next few that are on this piece is to help you think through this logic of who's in the risk set for your model. So there's a risk set that's the true risk set, which is the people who could be named and are within your boundary. And then there's the risk set that was realized by virtue of your sample design. In many cases, your risk set gets constrained. And so in this case, there are people out here 3 steps later, and we can't know anything about them because these folks weren't allowed to survey anybody. They weren't allowed to name anyone. So whenever you stop the connection, you're not there. Now, if you have a model where you don't let your second step folks name anyone, so like I name a peer, I interview those peers and they tell me who's there, that means that I don't have any idea about the relations amongst these set, right? So they're now out of the risk set because these folks had no opportunity to name within their set. And you can think about this, a classic RDS, you get no transverse edges, right? So in that kind of a model, you start with one node, you contact the people they name, they contact the people they name, and so forth, and you snowball out, but you never get these cross-tie edges. And this is why the network sampling with memory idea that Ashton told us about a couple of days ago is so powerful, because you get those kinds of transverse edges, and once you have those transverse edges, you can make some inferences about the probability of closing triads in your set. So it's a nice feature to have. But it's expensive. You have to go and interview those people and ask them about their questions, and so that's always the trade-off. This is the same kind of idea, just displayed a little differently, so I'm not going to go through what's there. So again, those particular slides were specific to this notion of a snowball sample or something like a snowball sample, and your problem is probably going to be different. But think about how your system has constrained who can be named. So when we go into school, the Prosper data, for example, all of those relations are within grade. Well, as Jimmy was saying a couple days ago, a grade is a weird boundary in a school. And so we know there are ties outside of the grade, and we probably ask kids how many friends they have outside of their grade, but we don't know exactly who they are. So that's a sample design constraint on missing data. And design constraints on missing data are going to lead to these kind of logical holes that then constrain the kind of measures you can have. So what we wanted to do, I don't know why this thing is moving automatically. There we go. There must be some timings built into this presentation that I forgot about somewhere. All right. One might assume that by this point in my career I know how to use PowerPoint, but there you go. Given the fact that the one way to read all of these examples is that you're going to have distorted data. So what do we do about it, and how does it affect what we're playing with? And so as you probably got a flavor, a sense for the other day, when I don't know the answer to something, I simulate it. I make it up and then try to figure out what I could learn from that data. That's my basic rubric for how to do work. And so this is what John and Jeff and I worked on. We thought, well, let's just take a set of data and figure out if we induce missing data in it, what do we recover when we measure it, when we model it as if we didn't have missing data? How much error is actually introduced? So we start with a set of networks that we're going to treat as if they're complete, as if they're true. Then we're going to remove the nodes, and we have a whole series of different strategies for removing them. First, we're going to do the obvious thing that's done in all the sort of standard missing data literature, which is to assume missing at random. That's sort of your best hope. So if the world is missing at random, what happens? Then we're going to be a little more realistic and say, let's assume that missing data is driven by either peripheral nodes who aren't engaged and they quit, or central nodes who are too busy. So either of those things could be a possibility, and we'll ask about that. Then we're going to ask, what happens when you apply various kinds of imputation strategies? So if we know that our data is missing in one way, can we recover it nicely, and will that help? And what does that do to the measures that we do? And of course, you do this many times, and you end up with a solution. So there are lots of different. We wanted this to be it's a weird kind of set of papers, because we wanted these to be reference papers. These are papers that you're supposed to go to when you're doing your study and go, I got a paper that looks like Smith, Moody, and Morgan's network number 6. And so my result is probably like theirs. That's what we had in mind with this paper, which is why, again, I'm thankful to Tom for letting us publish it, because it's got these ridiculous figures you're going to see in a second. So what we just tried to do is pick lots of different kinds of networks that we think would represent the kinds of networks that sociologists and health researchers would use. And so we have 12 different networks that range in size from the smallest is 43, and this is a corporate interlock network. And what's nice about this network, right, is that it's really clear. You can just look right at it and see what's there. And so it's got a nice core periphery structure. There's some isolates and pendants, but because it's small, it's really easy to see what's there. It's a corporate interlock network, so it's actually a one-mode projection of a two-mode network, but the two modes are sparse, so it doesn't have a lot of cliquing in it, so that's kind of nice. The prison network is a classic data that was collected in the 50s or 60s, if I remember correctly. And this was all social relations inside of a prison, and so it has a nice sort of little clique structure up here and a little bit of division. Then we get into some bigger networks. I guess the sorority network is fairly small, but you get into something like the social networks co-citation network. What's nice about this is that there's different subfields in the discipline, and so you get these bigger clusters. And then we have a more dense 6th grade network. In this case, this is 6th graders, right? So it's probably no surprise you have boys and girls, and so because they think each other are icky at this point. Revisitor Elite, this is data that Ben Cornwell and Lisa Keister collected in a large Midwestern city, asking people to do just a classic elite study. So it was a nomination of people who were like you and who you think are elite in the city. So it has this really nice centralized feature to it. We have a set of other high school networks and larger scale networks. And sort of one of these is the Prosper School. One of them is built off the Ad Health network. This is a corporate exchange network, and then we have a couple other sort of big, weirdly shaped networks. So the thing that's nice about the Colorado Springs network is it's highly centralized, but it's not centralized in a pure core periphery. There's lots of different stars in the network, and so that's what we took that. So we have these 12 different networks. And then for each one, we want to go through and ask we want to construct a series of measures with and without missing data. And so we have a series of measures that have to do with the kind of metrics we talked about the other day. So we have centrality and centralization scores, and then we have a series of topology scores. And so this is things like the bicomponent size or the component size, and then things like just simple closeness centrality and so forth. the Concore result is well, I'll explain what I mean in a second. So now, I do this to myself, right? And so ask yourself, you have now 12 networks, and you have, I don't know, something like, it's like 18 different measures, and then you have a dozen different levels of missing data. How do you explain to people what you found, right? And so this is what we came up with, and you can tell us if this is sensible to you or not. But our logic was that we know the cardinal values are going to be wrong. If I delete 10% of the ties in the network, then on average the density is going to, the number of ties is going to be 10% smaller. So you're going to have, so the cardinal value is going to be wrong. But in a regression context, we don't really care about the cardinal values. We care about the correlation of the measure with other things. And so the question is, how good a proxy is the measure you observe to the true measure? And so we just created a correlation score. So in this top line, that says that the true value, before we induced any missing data, and we correlated that with the observed value when you have missing data. And then if we remove 10% of the nodes, you end up with this correlation. If you remove 70% of the nodes, you end up with this correlation. So that gets flipped over here on this side. And so on this side, what you see is the percent missing on the x-axis, and that correlation score is on the y-axis. And so what you see here is that at 10% missing, your correlation to the true value is well over 90%. So if you have a little bit of missing data for n-degree and a network that looks like the River City Elites, it doesn't hurt you at all. You can go all the way out to 70%, and you end up with the mean missing value of still over 90%. Right? So your correlation is 0.9, even if you're missing 70% of the nodes for this case. Now that's a really good case, right? And so I showed you this one for a reason, because it sort of tells my story nicely. But that's what all of these plots look like. And so you're going to see a fair number of them, as you might imagine, for all the rest. There you go. So these are the results across all of the different models. And so just to, again, have the first thing to do is to step back and sort of ask yourself, what's the big picture story I'm seeing here? So the big picture story is across all settings, across all networks, there's a negative slope. Well, that's obvious. I mean, that's what we expect. That the more missing data you have, the worse your measures, the worse your calculated measures are going to be proxies of the true measure. But the slope of those measures really differ across the network. So there's high variability across the different kinds of networks and the different kinds of measures. So for example, if I'm a relatively small, sparse network, and I'm looking at something like Bonasich power centrality, there's a strong linear association between the amount of missing data and the realized score. The amount of the drop in the correlation is going to be 7% for each additional 10% of data missing. So that's what that slope score is here. And so I think that on the one hand, and this is all random missing data, the first story that comes out is that size helps. So small networks, right, tend to have the strongest drop in overall centrality, with the exception of a couple of the slightly bigger and more sensitive measures. The other sort of quick sort of take-home bit is that in-degree and out-degree are really robust measures. That probably shouldn't surprise us, because these are local measures, right? So the number of people who nominate me or the number of people who you nominate, a random sample of those people are good representatives of it. And I think what people don't appreciate is that they're good representatives up to, we're talking 60, 70% of missing data, you're still getting correlations above 0.8. And you get down to the real system level measures down here. So these ones really do great. The system level measures are where my centrality depends on someone else's centrality, which is eigenvector of Bonasich centrality or closeness in between the centrality. These can be pretty sensitive. And so it really does depend on the kind of network you have. Highly clustered big networks like co-citation networks or co-authorship networks or the River City Elites, these tend to be reasonably robust to these features. But very spindly networks or highly transitive networks, like the school networks or the Colorado Springs networks, the other sorts of Prosper networks, these things tend to have a very strong relation. They degrade quickly with respect to missing data. So for example, if you look at the elite study here and between the centrality, it ends up having a pretty huge effect. Now, we don't expect you to go to these plots and go look at it. So there's another way of displaying this in a minute, and I'll show you that. These methods are the exact same kind of story, but you'll notice that the, the plot here is like really different. So what are you looking at? This is the homophily coefficient. So you might imagine that one of the measures we really care about is the association of my characteristics with your characteristics. And that was the homophily score that we calculated. And we did the same trick. We said, let's look at the missing data and look at the variance and the resulting answer that we came from. And if you have a sortativity on in and out degree, you get this, essentially you get an unbiased estimate. That's what's happening in the middle. But the variance goes through the roof. Right? And at the far end, you might get some bias. That's what's coming up here in the mean levels. But oftentimes, these things are largely symmetric, especially once you get into larger networks, where you end up with a score that is an accurate estimate, but a giant standard error. Right? And so you're going to be highly uncertain to what you get. For behavior, on the other hand, right, it turns out that homophily scores on behavior are really robust to sampling. So missing data on the network do almost no damage to homophily scores. And this is the hidden story in this paper, is that if your data are missing at random and you're really interested in whether or not peers smoke together or drink together or these kinds of behaviors, it doesn't matter sort of even if it's a weak association, you end up with an unbiased estimate across the board. And not even terribly like variable responses. Because remember, we're looking over here at 70% missing data at the end of these, and you're still not an unreasonable estimate on these sets. So that's good news for applied analysts who care about homophily, which is, I think, probably the bread and butter of most of us in the health world, that your networks are not really being destroyed too much in terms of missing data. Now, the final sort of set of scores are what we refer to topology scores. So this is the shape of the overall shape of the network you're going to induce by looking at by this kind of missing data. The story is sort of a mix here. It does a little bit better. We had to add some positive sort of branches to this. By and large, it's much like the centrality, so the individual level centrality scores. There's a negative correlation, so it degrades over time. But it's because of a few of the small networks, these ones that this is not my favorite display, as you can tell. But the take-home story is that the hierarchical mixing scores tend to do the worst, and the proportion of the nodes in the biconnected component and distance scores tend to do the worst. And it makes sense when you stop and think about what this is. These are scores that depend on the long distance path structure of the network. And so if your score depends, if your topology is being calculated on the long distance path structure of the network, it's a little more sensitive than it would be with something which is effectively the aggregation of a local score, which would be the transitivity score or the hierarchical tau score. So the concore, the role sort of division, and this is, we say we just take the network and cut it at 2 steps each time. Those end up being very stable. So if you want to do block modeling in these networks, because block modeling tends to be the aggregation of local orbits, it does pretty well. So even though you end up with a fair amount of missing data, it doesn't destroy the thing overall. I'm really sorry there's no coffee. I'm putting myself to sleep here. So, all right. So you don't have to go to these charts to go figure out what you're doing. We have these wonderful little lookup tables in the papers. This is taken from the second paper where we did the same exercise, but we made the missing data correlated with centrality. And what these tables do, they allow you to go here and say what's the most missing data that I could get in this network and still end up with a 0.9 correlation between my observed score and the true score. And so if you're looking at something like, if your network is like the sorority network, sort of an open, not very dense but small network, you could miss something like 23% of the missing data, and still you could be missing almost a quarter of your respondents and still have a 0.9 correlation with the true score. And that's, it doesn't matter if you're losing the peripheral nodes, that would be the negative 0.7, or the positive node. So you can either remove the central nodes, hurt you more than the peripheral nodes, but by and large, you're going to do good on that set. So that's what these tables mean. The A's mean that you could lose up, it was unestimable in the sense that by the time we got to 70% missing, you were still not below 0.9. And so in co-authorship networks, you can lose a bunch of people and not hurt yourself, right, in these particular measures. Does that make sense? So it's a nice, so that's the whole point of these. You can go through, if you look at the overall across all networks, you have this ability to ask yourself, excuse me, what happens when I'm missing data? For something like InDegree, like on average, if you're missing 50% of the peripheral nodes, you're not going to hurt yourself much. If you're missing about a third of the central nodes, you're still not going to hurt yourself. I mean, a correlation of 0.9 between the true and the observed is still really high, so that's a pretty high threshold. We're happy with that. Closeness and betweenness centrality are the bad news stories. So in these cases, if you're losing, you can only lose about 17% of the peripheral nodes or about 10% of the central nodes and still get a reasonable, a high fidelity estimate of betweenness centrality. That's how you would read that sentence. And the same thing, same sort of stories then with these topology scores. And so what I hope you, oh, that was the wrong button. So what I hope you do is go and check some of these tables out when you're thinking about your own data, and say, well, this is what, if I assume that I've lost the peripheral nodes, which is the negative score, or the central nodes, if it's the positive score, like then you can go and look up and say, well, where am I in this set? How likely am I to be in trouble with the measures I'm reporting? Now the obvious question is, if I'm missing data, how do I fix it? And so it might be, all right, Moody, you discovered, you've told me that I actually am going to be a little bit biased. So how about if I do the standard thing that we do in regular statistics and impute my missing data? We can impute it based on some kind of a set. So the final paper in this series where we tried to introduce a series of corrective behaviors. And we do this in a series of different ways. We start with, if this is your missing data in reality, so the true network is the union of all of these, but you're missing these two red nodes and thus all of their relations. What do you actually get, right? So how would you impute these data? So the standard thing we do in the social sciences is we just work with the data we have. And so we're calling this listwise deletion, just because it's just like you would do in regression context, where you toss out any cases where you have missing data. In a network standpoint, another option is to say, well, we know that these two nodes, for example, nominated somebody out in the network. They didn't reciprocate. So let's just go ahead and keep all the ties as reported by my actors and add back in the nodes that are missing. So in this case, we know that node E was named by two of our respondents. We put the directed edges from A and D to that node, and we just keep the asymmetry in the network. The alternative is to say that we'll put them in the network, but we'll assume it's a reciprocal tie. And the advantage of doing that is that whenever you impute this way, where you just add the ties as observed, by virtue of the fact that E can't nominate anyone else, you can't get a closed circuit. So you have to have, in this case, there's no way, if you were to think about a flow process, for example, it would come here, it would start there, and it would always get stuck on these nodes that you've added. In order to avoid that, and some of the circuit-based measures in the network are going to assume that you can move things around, you want to have a reciprocal tie so that any flow that comes here can find its way back to the people you sampled. So that's why we made that assumption. Both of those are hard rules. There are a series of probabilistic rules. So the first rule is to say, let's just assume that we have some proportion of ties that are reciprocal, so we're going to apply that proportion, and we're going to flip a coin with that weight and reciprocate the tie as observed. And the final approach is to say, well, we can do better than all of these heuristic rule of thumbs by using a statistical model of the network. And if we know homophily, we know transitive closure as the network as a whole, we can assume that's true for the unobserved networks, and we can impute ties based on a model. So that's the logic of these different pieces we've gone through and done. And so we do the same exact thing. In terms of the model set process, we have essentially a very simple version, which is just a dyadic independent model. We have a baseline probability of a tie forming at all, and then some homophily terms that are built into the model. And then we have that plus this transitive closure effect. And the same sort of kind of model that we go through, we do, the display got to be absolutely ridiculous. So we have a table in the paper that says, do this, right? So, which is, I think, what many sort of users want. So for example, if you're interested in calculating, total degree and your network is directed, then quite honestly, you can do anything you want, you're going to be fine, right? That's the best choice. It's like there just is no difference in any of these responsibilities. If you, excuse me, if you have any type of missing data, then any of the simple models are going to be just fine. You don't need anything harder than either the asymmetric set or the coin flip. If, on the other hand, you're interested in closeness centrality, then you probably do need to do kind of a more model-based approach, right? Regardless of what kind of missing data you have. If you don't see your combination here, so for example, we don't have in degree with undirected, that doesn't make any sense, but the goal was to go through and figure this out. If you go through and you look, the thing that was probably most surprising to us, that's sort of the big picture take home here, is that the listwise deletion strategy, and these are bias scores now on the y-axis as opposed to correlation, so it's a different metric than we had in the last set of slides. We got a different reviewer, so they wanted us to switch it up. So we ended up with the basic story here is that you end up with doing listwise deletion is probably the worst thing to do generally, because you're just throwing away so much more information that across any of these kinds of scores, whether you're selecting peripheral nodes or central nodes or just missing data at random, in all cases the listwise deletion is going to lead to the most bias score. But the more surprising bit is the other kinds of the simple imputation methods, before you even get to these complex model-based things, tend to work just fine, right? So the model-based isn't that hard anymore. It's a lot easier to do now than when we wrote this paper, but it's still the case that it's a lot of extra sort of architecture on top of those kinds of models that you don't want to do unless you can help it. And often cases you just don't need to for the problems we want to answer. And that's also true. So that was for our undirected networks. It's a similar result for directed networks, and a similar result for the different kinds of centrality scores. So again, throughout the cases, there are a couple of bits and pieces here where there's a slight advantage over one modeling strategy or another, but by and large, these things tend to work pretty well together. And again, there's these lookup tables in the model. I'm not going to bore you any more than that. There's another thing that's in this paper, which is kind of cute, which I think is kind of fun, which is we added a series of decision trees. So if you want to go into the model, you can say, I have a centralized network. I'm interested in calculating centrality measures and their path-based measures. Then probably the best choice that you can do is a probabilistic imputation. If instead you have an interest in something like topology measures on undirected networks, then a complex model is what you're going to need. So these trees are in the paper if you want to go through and look at it. Now the reviewers rightly said, come on, Moody. No one goes to a hard copy of a journal and looks anything up anymore and traces through the back of a table. It's like, find something for us that people can do. Make us an app. So we did. We made an app. And so we made a little app, which is our network bias calculator. The problem is it was calculated in Java, and now no one likes Java anymore because it's a security risk. So so it's not working right now. It's died recently. So unless your administrators will let you use Java, in which case you can have it, but our administrators won't. So we don't have it. But we're rewriting it as a Shiny app, and so it'll be available, hopefully, knock on wood. This is one of the things, Emily doesn't know it yet, but this is one of the things she's working on this summer, is to translate this code into Shiny. And so in that case, then, what this allows you to do is to go in and pick one of these archetypical network types, plug in the kind of reason your data is missing, and some assumptions about what you have in your network, and it'll pop out this thing that tells this is the amount of expected bias you would expect in that kind of a network. So it's designed to be a tool to say, all right, and you might think this is a lot of work, and many times reviewers don't want this, but grant reviewers do. So when you're writing your NIH grant and you have this is the equivalent of a power calculation in a network study. You're going to say, well, we assume we're going to get an 80% response rate, and that's going to, and if I'm a grumpy network reviewer, I'm going to say, well, that means all your scores are completely worthless. And you can say, no, they're not completely worthless. In fact, given some reasonable assumptions about the network, it looks like we're going to have a correlation of 0.9 in this case with this true scores, and it'll be perfectly valid. So it's a nice way to be able to answer those questions, which is why we built this thing. All right, I want to spend a little bit of time now giving you an overview of network models. And then I think by now the backup coffee should be done. And so, is it somebody yes? It is done, right. So I will, so this will take me about, so I'll do this quickly so there's time to have some coffee before Craig comes up. But I just want to, again, this is maybe let me do it in 2 steps since these are really 2 problems. Are there questions on missing data? Questions, comments, thoughts, please?
So I think you gave some suggestions in scenarios where the data is not missing that random. Like I'm trying to be curious. So like some of the scenarios you guys would be like, say the central, they're more likely to missing or the peripheral ones might be to like how you sampled your people, but then for the scenarios where like maybe you guys are missing like for other
Yeah.
level characteristics. I'm curious if you could do that.
We did not. So we did a centrality gradient for peripheral versus central. And so we had your missing data was either highly conditioned by your closeness centrality, either positive with a positive or negative slope. So that was what we did. We could instead say that males or whites or rich or poor are more or less likely. And so if those we haven't looked at that. So the question is if those things correlate with centrality, then you can sort of back out that set. If it's segmented, then it probably doesn't affect any of the rest of the network other than your ability to understand the segmentation. And so that's why we just didn't go that direction. But it's a great question. So if you want to move that way, we have the architecture set up. So. Other questions, please. Mm-hmm. We did both. So we induced, the way we tested this is we induced homophily on the network with a weak correlation and with a very strong correlation. And in both cases, they were remarkably, if your data is missing at random, you're golden, nothing matters. If your data is missing based on peripheral versus central, there's a you're slightly more likely to get a bias, but even then, not much. So homophily scores, it's kind of remarkable that homophily scores are just remarkably robust to missing data. Unless, and this is the point that I think that might have been driven over here, we didn't test for direct selection on the dependent variable. So if you're looking at, say, smoking as your homophily score, and none of your smokers filled out your survey because they refused to talk to you, then you're certain to have bias, right? But so long as you're not selecting on the dependent variable you're trying to explain, our results suggest that it's really robust. Yeah. All right. So now we want to do just a little bit of an overview just to get you in the headspace of network models. And so network models are this sort of broad, what I'm just using as a broad class of ideas to think about when you're doing what all of us have to do to get a paper published. We have to collect some data, describe the data, model the data. And so the model of the data is usually a regression model. And there's about 3 or 4 different flavors of these models that are common in our field. By far, I think the most common network model is what I call a network metric model. And in that case, there's some dependent variable, self-rated health, smoking, the number of hours you exercise, and it's a function of a standard intercept, and you can make that random or whatever it is you like to do, some network score, and everything else you control for, right? And so there's probably 1,000 papers that look like this. And so the question is that kosher? Can you do that? And in most cases, you're doing a standard general linear model, right? And as such, all the standard assumptions about that error term, that little guy over here on the left, on the right, apply. And so what we assume is that you have the assumption of regression is homoscedastic error terms that are not autocorrelated, right? So independent IID assumptions on this. The problem with a network model is that almost always that assumption is wrong, that the E's are going to be you're usually going to have at least network autocorrelation. And so network autocorrelation says that my error is correlated with the error of people I'm connected to. And so in practice, most people ignore that. So you will be like 90% of the papers you cite if you do nothing and just use the network score, run the model. That's what people typically do. And at first, I was really concerned with that And so John and I spent a lot of time, and Jeff and I, Jeff and I have a third sort of, another set of papers that we're starting on to try to really unpack this set. Because the right thing to do is to replace E there with a network autocorrelation term. So you have EIJ, which is going to then sort of give you a feedback process built into the model. And I'll show you what that model looks like in a second. But it turns out that if you have just error autocorrelation as opposed to behavior correlation, so if it's just that the errors in your model are correlated, then like a lot of autocorrelation, all it does is increase your standard errors. And so you end up with a less precise estimate, but not a biased estimate. And so for the vast majority of cases, you've already soaked up a lot of the variance in that autocorrelation with your centrality scores or your clustering scores or something like that, because it turns out that in most settings, people's centrality is highly correlated with their peers' centrality. So that means that I actually have an instrument for the network autocorrelation when I'm doing it. And so in practice, this ends up not being a bad estimate. It's usually pretty close to unbiased. And it's all, the one complication is that it ends up being a confounded interpretation. Is that what the centrality score means isn't just that I'm central, but that I'm central and I have peers that are like me. And you're not able, by virtue of just putting this in the model, to be able to disentangle what proportion of that is autocorrelation and what proportion of that is a pure centrality effect. So that's a short way of saying it works, right? You can do that. What I recommend doing is always adding some other features that are going to, one is to do the network autocorrelation model. It turns out that it's not that hard to do, and we can show you that we'll show you that a little bit later today. But the other problem is if you just control for other connections in the network, you also do a good job of soaking up those kinds of problems. So if you have a community detection sort of piece, put that in as a control. If you have a latent space, put that in as a control. So you can put all these different features in the model, and that accounts for a lot of those kinds of errors that would otherwise be there. And so if I care about prominence, and I think that popular kids are more likely to smoke than unpopular kids, then I want to control for what clique they're in. So I want to have a control in the model for what community they're in and for the other things. And that ends up simplifying the model quite dramatically. So again, what's the best practice? You can do nothing. That's what most people do. It's hard for me to recommend that you do nothing when we know there's a problem, but in practice, that's what most people actually do. You can add the network autocorrelation term. That's the most direct correction for a likely problem. There are ways in which that can go wrong, but by and large, it ends up being pretty straightforward. And there are two nice tools for this. The key one is a spatial autocorrelation model. Like R has a nice spatial autocorrelation package. Stata and SAS also have great spatial autocorrelation projects. So these are pretty easy to correct for. You can, if you're really down in the weeds and you want to do this the hardcore way, you can just put the mean of your peers' dependent variable in there, and that'll soak up the vast majority of it. So there's lots of ways to correct for this that are reasonably simple, simple enough that it's probably worth doing. And you might learn something. All right. The second set of sort of broad class of models are what I refer to as dyadic relational models. In this case, to some dependent variable, what you really care about is the relational similarity. So are Craig and I similar on our opinions about the environment, right? That's the kind of question that we might ask. And it's a function of our being tied to each other. And so it's the network association, this AIJ, we think has some causal effect on our similarity. And we control for everything else in the network. The complication here is these are dyad models, and so you have all of the network autocorrelation that are built into the model that you have otherwise, but you also have repeated observations. And so you have these two sources of non-independence built into the model. The good news is that you know what's there, right? The theoretical advantages of these is that Craig and I's similarity might be different than my and my wife's similarity because we have a different relation, and so we have a different sort of outcome. And so it doesn't essentially take my outcomes and average it across all the nodes. You can do things that are directly relational. This is by far sort of the best practice for dealing with these things, particularly if you have ego network data, is multi-level models. And so you can nest the relation inside the person, and by nesting people in persons, you correct for all these features. And this is what Bria Perry presents in the advanced version of the network. If you have both sides of the network, it gets a little more complicated. The thing to do are these things called cross-nested HLMs or dual random effects models, where you essentially put a random intercept. You treat this, I should have written my equation better. You treat this intercept as, there's one version for I, one version for J, and that intercept then is a function of lots of other things. And so these models are estimable. They end up being a real pain in the ass to fit, just to be honest with you. So if you're going to do them, just give yourself a little bit of time, because it's going to take a while for them to converge, and you're going to specify them in ways, and it's not going to work, and it's going to make your life a little bit miserable, but they will typically work okay by the time you get them. You can also, I think, and again, I'm a big fan of as Peter Mucha likes to say, the simplest non-stupid thing. So what's the simplest non-stupid thing you can do? The simplest non-stupid thing you can do is include explicit controls for the similarity that would be otherwise confounding your estimate of the model. So the number of shared friends we have. So Craig and I's direct effect on each other is a function of the fact that we also jointly hang out with lots of other network people. So that's something that we can include in the model. Because the fundamental assumption of all of these general linear models is not that the cases are independent, but that the errors are conditionally independent. And so if you condition on all the right things, then the leftover unobserved error is unlikely to be that damaging. That's all by way of saying is that when you try to do the right thing and it doesn't work, don't feel so bad when you do the reasonable thing that will work, right? Because at some point you have to finish a dissertation and get your papers published. So, get those things out there. The other thing to do is to not make these bad assumptions. And so you can not make some of these bad assumptions by using non-parametric models. And so there's this whole series of non-parametric effects, such as QAP and multiple regression QAP, which don't make the same kind of inference assumptions that the general linear models do, that allow you then to sort of sidestep the problem by not making the assumption in the first place. And so that's a nice solution, but it requires a set of specifically known tools. And then finally, there's a series of, depending on the way your question is structured, you can treat this as an edge-level covariate in a predictor of another relational model. So if my question is, who hangs out with each other, it could be a function of who talks to each other. And so that's a bad example, but you have those kinds of, you can think of two relations in a multi-relational network with one predicting the other. You can use those tools. Which then takes us to the final model, or final class of models that we want to talk about, which are these network prediction models. In this case, you have the adjacency matrix on the left-hand side of the equation. You're trying to figure out what predicts a tie between people, or the strength of a tie if it's a valued relation, as a function of some features in the network. And there's usually two classic types of features. There's some type of homophily feature, so same race, same sex, same education, what have you. Or there's some endogenous feature of the network itself, transitivity, reciprocity, something like that. So those are the kinds of things that matter. And you might have a bunch of other things, of course, in the network that could be there. But substantively, those are the features that are there. And those are what are known as exponential random graph models. And so we completely flip this around and we say there's this probability that the tie exists in the network as a function of a series of statistics on the graph. And it turns out that those statistics can be of two classes. They can be either dyadic independence, which are known as homophily effects, or they can be endogenous non-dyadic independent effects, which are there. And I'm going over this really like that. Those last two sentences were gibberish to half of you, because we're going to spend an hour and a half on it here in the afternoon talking through all of the details of that. So again, this is just I'm telling you things multiple times today because it's a lot. So there we are. Okay. So yeah, I did that. And the final, why is that? Oh yeah, I guess did I miss those? I should have had a 4. That makes more sense. All right. So the final set of models, I just talked about these. These are contagion models. So the final set of models are what Craig's going to help us think about, or substantively, and actually are these things called peer influence models. A peer influence model says whatever my behavior is on the left-hand side is an endogenous function of the behaviors of my peers. And so how you estimate that, what that means sort of theoretically, is a good question. And we have to make sense of how that does it. But it turns out that estimating these models, there's now lots of tools to do it. And so the models have to make assumptions about convergence and about equilibrium and so forth, But in practice, there's lots of good ways to get this. If your data is dynamic, we have what are known as Siena models or stochastic actor-oriented models. That should be an AOM, not an OAM. But these actor-oriented models are going to be the topic of discussion on Friday morning. So we'll go over those in great detail. One thing I'm just going to point out, and I should have put this on its own slide as opposed to at the bottom of this last slide, is that there's two different sorts of problems that come up in most of these models. There's an analysis, sort of an estimation problem, and there's an inference problem. So there's a question of, can I get the model to work, and what does the model mean? And those are two separate questions. And can I get the model to work as an estimation problem, or is my answer correct given the data that I have, is often the least problematic of your questions. The more problematic question is, what does it mean? Right? What's the theory that drives this? Is it selection versus influence? The coefficient is exactly right. If I'm trying to just predict the outcome, the model is going to be accurate. But interpreting what it means something else. Okay? So that's not a problem we can fix in the machine. It's a problem you have to fix as analysts. Does that make sense? All right. I'm putting myself asleep. I don't want to take too much time with Craig's. The coffee is here. So let's take a get some coffee, say hello, and we'll start over again once people are caffeinated. So.
Kind of a little bit more of a rambling question for the audience.
Yeah.
But so is in qualitative, like usually used in interviews, there's like targeted sampling, sometimes of trying to get the person you think that has the more information. So is this similar technique as like the sampling memory?
Yes.
So you're trying to push it into another cluster to get
Right.
that information?
Exactly. You're trying to say that the fear with a lot of these kind of models is that if you just let your network do its own thing, it'll get stuck in these bubbles. But if you just tell people, hey, give the coupon to somebody who's not like you, then it'll jump out of that bubble and you get a wider set. So just like you ask people, you want to keep surveying people until you stop getting new information.
Like saturation.
Right. Yeah. Yeah.
Okay. And is that like the RDS manual had to like get two different people? Has that ever been analyzed as this, like to what extent, like a meta-analysis, to what extent?
I'm sure it has, just because there's been so much money spent on it, but I don't know the answer to it.
Because that, I mean, some people are going to think, oh, these are very different people. It's because they
Something happened with the internet somewhere in the world. So it's my really distinct pleasure to introduce Craig Rawlings today. Craig Rawlings is new assistant professor. He was new assistant professor at Duke, and he just got tenure. And not only was he tenure, he was promoted to a named chair, a Bass chair in sociology. So congratulations. Really fantastic role. But Bass chairs are given to people who are both great scholars and great teachers, and there's a few people who are more deserving of credit for this. His own work is on peer influence models and the theory of social culture and social balance. And he's focused on questions about how people come to know things and how people come to believe what they think they believe, as a function of how they're invested in the world around them. And his set of tasks have not been deeply in the health set, but have been really interesting. And I think I won't steal what you were talking about. But anyway, really happy to have Craig. Thank you so much.
Thank you. Well, thank you. It's great to be here. How you doing? Yeah? I feel very grateful for getting to go after coffee and some breakfast. So I'll pick up where Jim left off, and I should also note that Jim is a Bass fellow as well, and one can't do wrong just trying to keep up with Jim and watching him go further away. But you aim for the stars. It's kind of our tradition in this workshop to just hit you with tons and tons of material. All right. It's like the spaghetti model. Some things are going to stick, most things aren't. I'm going to try to point to a few pieces of spaghetti that I hope will stick. And they're not like equation-based, but they're thought-based. And the first one is where Jim left off, which is most of our methods problems are really theory problems in disguise, which is kind of great and kind of like, oh, right? You're never going to find a model that solves your problems when you're trying to answer complex questions. So in many ways, people spin their wheels a long time trying to find the right model, the right estimator, and really you should pursue relentlessly the question. What am I trying to learn about the world? And you may have to run lots and lots and lots of different models and then, sort through to help us learn what you've learned. All right. So network analysis really has these two research goals, and the first part of part one, and I hope you'll all come back for part two next year. The first part of part one has been a lot more about descriptive kinds of techniques, trying to accurately describe a social structure. Just description is hugely important in lots of contexts. But we're moving more into a context in which we're really trying to understand networks as being things that are the causes of certain things. Today, I'll be talking about flows, like things that spread through networks. And then later on today, we'll be talking more about the consequent, the sort of more the networks as outcomes when you're trying to predict ties. And that's when you're going to get into ergum, sturgum. And then tomorrow, I'm going to try to tee up a little bit for David Schaefer and thinking about the stochastic actor-oriented model or Siena model, which kind of does both of these things in a kind of dynamic coevolution sort of sense. So, stop me anytime. Raise your hands. I'm just, in the tradition. I'm going to be covering a lot of things. The first thing is trying to think more about diffusion and then social influence. So, the main way of thinking about why networks matter for how things flow through networks is if we look at a kind of view of the world that's very atomistic. Let's say that we did a survey and we asked people how many sexual partners they'd had in the last year, and then we just looked at the people who had had 2 sexual partners in the last year. We would get a view of the world like this, and we might be thinking about some important outcome, something that might diffuse through this, the probability that this person is going to be infected with some STI or not. And in this case, we would have a very rough model. 2 is definitely more likely than 1, is definitely more likely than 0. But if we interject a network in it, and maybe how many of you have seen this network? A few of you. This is a very famous network and something that Jim and others worked on. This is a single high school romantic sexual relation network over the course of a year. This wasn't a weekend. Wasn't the 70s. It's like so this was in the 90s, right, Jim? So definitely in the wake of the HIV/AIDS epidemic. And one of the cool parts of this paper is that Jim and others show that this network, this sort of what predicts the ties in this network are a very interesting combination of things. But one of them seems to be a kind of prohibition on dating your ex's ex. That people, they call it romantic leftovers rule. And the people in the network don't even quite articulate that, but they kind of follow this rule, it seems. But what are the consequences? Clearly, this and this give us very different views of the world with very different possibilities. So the whole point of network analysis is structure matters. It matters if you are a person here or you're a person here, you still have had 2 partners, but if you're in this main component and the structure of the main component itself, all of those things matter for flows. They matter for flows of things that are good, that you want, and they matter for things that are bad, that you don't want. So the main model here is that you are, in many ways, the company that you keep. That over time, we tend to become more similar to those who we have ties with. And that may be something that happens gradually, or it may be something that, what's the old saying, it happened gradually and then all at once, right? So there may be sort of tipping points, there may be ways that after you spend a certain amount of time, then it kind of clicks over. So I've been studying a lot of these processes, not necessarily in the realm of health. You've looked at all kinds of descriptive measures at this point, how dense the network is, how much connectivity and cohesion there is, the centrality and centralization that is. Our networks really held together by a few stars. It's like the collaboration network at Duke, if Jim were to leave, we'd just fall apart. What would we do? So that's very different than some other networks that are held together by a bunch of, pretty good people that are active. You've learned about small worlds, yes, a little bit. So the small world connectivity is this observation that goes back to a lot of social psychology, that people's networks tend to be very clustered locally. We tend to have strong local clustering, but we also have acquaintances that bridge distances of the social structure. So those bridges tend to be weak ties of acquaintanceship, not my best friend, but those weak ties tend to be incredibly important in flows of things, like things that you want and things that you don't want. So what is peer influence then? It just seems that so many of us in social sciences are trying to understand something about the effects that relations have on people's attitudes and behaviors. And I think in the study of health, maybe the emphasis has been a little more on behaviors, but obviously there's a huge segment of trying to think about people's attitudes and the link between attitudes and behaviors. Peer influence is a type of diffusion model. It's really concerned with the flow of something through people's ties. So it gauges these effects, but it focuses on, as the name would indicate, peers. It tends to focus on people who are friends, who are collaborators, people who are colleagues, people who tend to be in the same. Now there can be status or prestige differences and things like that. I would say Jim is my peer, but clearly much more, in the realm of informal and formal hierarchies, there are differences. So we focus it on friends and colleagues because we think that that's a particularly important place to think about these processes. Now, yesterday, Ashton talked a lot about how this has overlooked the importance of kinship, and I agree. Kins are, family is very important too. The emphasis tends to be on a small to medium-sized scale rather than on huge diffusion processes, rather than trying to understand the spread in very large networks. Although, again, there's a kind of, slippage there. And the things that spread, not always, but oftentimes, they can change as they move through the network. That if I tell you a really good joke, you might, just slightly change it or something like that, right? That we can think about, and this is why one of the reasons why cultural sociologists are so interested in peer influence is because it seems that the origin of so many of our important beliefs and attitudes are developed through this ongoing evolutionary process, like a huge telephone game, where people are constantly influencing each other, but slightly maybe adjusting things. So the origins of religion in the world, like why are there so many similar kinds of religions in the world? It's like, and being a scientist, I don't think it's because the people from the Pleiades came here and seeded us. It's not the ancient civilization, aliens, Ancient Aliens, History Channel. It's on the History Channel. What's going on? It's not Ancient Aliens, okay? But there's something about the commonality of our brains and how we remember things and how we tell things, how we influence each other, that tends to converge. Kind of like how crab-like creatures have evolved at least 3 or 4 different times and places. It's just the environment selects for these things. All right, I can go off. So the outline here then is I realized kind of in a little bit of a panic last night around 11:30, I don't know if we've really covered diffusion straight up, and that's kind of important for thinking about networks and health. Kind of, there's something kind of happened recently, and a lot to do with diffusion of things. So I'm going to cover this very quickly, but Jim Moody is absolutely the star in this, and I maybe, we'll do a little, if we need to, a little back and forth over there. Having Jim in one's personal network during COVID was just amazing. I remember very early on we had a conversation because right away when it was spreading here, it happened in RTP. It happened it was Amgen people, right? They'd gotten it at a conference in Boston and it started to come into the network here through a very sort of more, elite sort of group of people. And Jim just said, that's not gonna last. But once it gets into people in these other areas, it's going to be a totally different story, right? So being able to bounce ideas off of Jim over the course of COVID is like it was like having my own, like authority on MSNBC or something. And now we're going to go to Jim Moody. What's going to happen? So again, this is going to tee us up for more hardcore statistical models to follow. Okay, and I have until 11:30, right? 12:30? No, I'm just kidding. Seriously, how long do I have? I have an hour.
11.
No, 11:15.
Okay.
We'll see. So you may have heard of this thing called R naught, yes, or not. You've heard of R naught is the reproductive rate of.
You have as long as you want. You're only taking time from me.
Well, maybe we just do this together, like a little stand-up act. Okay. So the R naught is what we all were paying attention to a lot. If it's over 1, it's bad. The thing is spreading. It's going into the higher above 1, the more it's taking off, right? Remember, we were trying to bend the curve. We're trying to get that R naught down in some ways. And we had social distancing, which was just like, for a sociologist, was just the worst kind of term. It's like, we're not socially distancing. That's awful. We don't want that. We're physically distancing. So the point here is that R naught depends on the probability that a contact will be infected over the duration of the contact, beta, the likelihood of the contact, C, and the duration of infectiousness, D. And this is where things get networky, because the probability of contact, the likelihood of contact, is a network effect. And it depends entirely on the underlying topology of the network. So most diffusion models have this kind of S-shaped curve, right? That there's a slower period that, bless you, that reaches some kind of period of critical mass, takeoff, density dependence, and that then it shoots through a very rapid period, and then it, once everybody's gotten it, and boy, it was fun the first time and the second time, it levels off. Nobody knows a priori these things, right? It's very difficult to predict, but many of the simulations that Jim engages in gives us a good sense of what we might expect under certain conditions. Most models of this assume a heterogeneous mixing. That is a kind of a random network where we're just all kind of just randomly, interacting with each other. And that's why this is a smooth curve. It's a smooth curve because if it's a random mixing, it's going to be basically a kind of slow, blah, blah. It's going to spread. It's going to spread over here. And it's going to take off, and then it's going to level off. But that's not the social world. So most processes are not this kind of smooth S-shaped diffusion. They go through periods of local maxima where they and then they stall out. And just as Jim pointed out with the Amgen crew, it's like, okay, but once it jumps into a new part of the network, it takes off again. So one of the ways that people think about this stuff is just about individual characteristics, that there are some people that are maybe more susceptible for whatever reason to the spread of a contagion. And maybe that's a good contagion or a bad contagion, right? Maybe your immune system is different, but maybe also if it's something that's good, maybe you're a cutting edge person who's just like, I'm always looking for the new thing. I'm a leading person, right? I'm an innovator, right? And then there are others who are laggards, who are just, I don't know. It's like, I like Taylor Swift when she's classic rock, just like, just so it takes time for some people. Those are just kind of individual models. So if that's the case, the spread, again, has much more to do with individual variation. Now, we're sociologists, we're social network scholars. Structure matters. Structure matters. Structure matters. Structure matters. I want you to... The structure matters. So one of the early studies of this, which has already been touched upon a little bit, is about the diffusion of this new drug. I'm not sure I can pronounce it, Gamma-Nim. It's like a tetracycline. It was like Coleman, Katz, and Menzel kind of show that there were some doctors who were more central in the network, seemed to adopt this more rapidly and spread it through social contagion. Later on, Ron Burt and others have kind of reappraised this, and maybe this had a little bit more to do with what they call structural equivalence and monitoring of your competitors. But the general idea is that there's a direct path of influence, but there can also be indirect paths of influence as well. Those most diffusion studies focus more on the direct paths, the friends or colleagues. So there are various tipping points. And then Jim touched on this briefly yesterday about threshold models, that there may be some kinds of contagions that are more complex, that spread, it doesn't spread quickly. Like a simple contagion, like COVID, right, is I was in the elevator, it was pretty simple. Yeah, exactly. I mean, I was on a plane, not with my 235 best friends, but just, there. So it's a simple contagion, but there are social contagions that are also pretty simple too, about, like I said, like good jokes or gossip, something you want to tell. It just kind of flows really easily and moves through the network really quickly. There are other kinds of contagions, probably a lot of the sort of behavioral things that many of you are interested in that have to do are more complicated. Is it the first time that you meet somebody in high school who's like smoking a cigarette that you're like, that's bitchin', give me those, lighten it up. Yeah, I love that, I'm addicted, let's go. It's like, it doesn't happen that way, right? It happens slowly, and it's a more complex, there's a threshold. So I grew up in the 80s when everybody still smoked, right? My brother smoked, my dad smoked. I went to school, it seemed like all the cool kids smoked. I ran into an attractive person. I said, "You're smoking. That looks good." And then, off we were to the races. And then I ended up hanging out with this whole group of people behind the Circle K where it was at this little dead end. And we started calling ourselves they were the dead end kids. Where you going, the dead end? There's a little cigarette machine, like pull the handle, get your Pall Malls, 5 quarters. That's all it was. Ding, ding, ding. There are people in that place. They're like, "I know they're 15, but I'm making so much money here at this coffee shop." So there's just like this whole ecology that built up around it. Got into theater that way, of course, right? And then bam, I'm at NYU, Tisch School of the Arts. There you go. And I blame it all on cigarettes, which I quit very quickly after that. After I dropped out of theater school, actually. All right. So complex contagions are more like that. They also may be upheld more by beliefs and things that I obsess on. What I want you to take away from part 1 is the topology matters. The timing also really matters. And I'm sure, Jim, and I'm sure we'll get to this stuff, it's in the book too. If this is your jam, then there's a lot more to go into it with. You all got links to the tutorials for the book, yes? So chapters 14 and 15, you might want to walk through some of those tutorials to get a little deeper dive into this. So I never do R in public, John Morgan, I mean, that's masterful. I'm sitting in the back, I'm like, how's he doing this? It's like, it's not blowing up. Okay. And then culture and meanings and attitudes. So this is where most of my work has been done, and I do think it has a lot to do with health as well. This network, the topology, is particular. This is one high school, right? The spread in this network, obviously, again, the timing matters. This didn't all happen in one weekend. This isn't like, so some people were early adopters, I guess, if you will, in the year, and others kind of came in later. But the overall structure of this has implications for the flows of many things. It's actually kind of, I guess, kind of a hopeful structure in some ways, because there are all of these choke points around the main component, where if you think about the probability of something flowing through here, it has to go through a very narrow path. And the probability being a stochastic process, it's not guaranteed. And if that doesn't happen, then the spread is kind of stymied. That's very different than other kinds of networks. There's always, if what you want is a network that is conducive to the spread, this is a bad network, and you want to try to get a different network. So in my postdoc at Stanford, we were very interested in trying to what facilitates collaboration and knowledge flows among faculty. Those are good things. It's really good to talk with your colleagues across disciplinary boundaries, right? Stanford spent over $1 billion, and this was a long time ago when $1 billion meant something, and tried to create different interdisciplinary research institutes to try to thicken up the networks. And so this is BioX, which focuses on bioengineering, and you can see that there are faculty in the natural sciences and medicine, and you can then see engineering is kind of where these different disciplines fit in this overall structure is very interesting. So there might be some dense pockets that you're thinking, if I'm trying to facilitate the spread of knowledge and influence and creative thought, innovation, if you have this understanding of the structure, then you have a lot of understanding of where interventions could be made. And you also maybe know where, if this is a structure that you want to disrupt, where you're trying to disrupt the flow, you might target certain areas like here, between engineering And the natural sciences in particular seems to be one of those kind of, it's not just that one tie in the sexual network, but it's a kind of narrow, it's a little narrow tunnel. So you might want to disrupt that somehow. And so if you were somehow able to give early retirements or something, get these faculty out, you would thin this a lot in terms of the bioex faculty being removed from the network. So the topology matters. And there's always kind of a trade-off, because as networks become more dense and more modular, they become more of like that kind of small world structure of kind of like dense pockets that are kind of more loosely tied to each other. There's kind of two things that happen there. The density makes it so there are lots of non-redundant paths between everybody, right? There's not just one path. So I might not need to directly infect you. I could do it indirectly. And if there's multiple indirect paths, then that's an issue. But also, as networks become more dense, they also tend to have a local clustering, and they tend to have sort of more holes, structural holes, as we call them, tend to have structural holes to other parts of the network. So this, Jim, am I saying that right? So there's a trade-off in thinking about these things. So the first point, right, the first spaghetti that I want to really stick was methods problems are usually theory problems in disguise. Second is network form matters. So one can't pass on information or something else unless they're directly or indirectly tied. The connectivity refers to how actors in one part of the network are connected to actors in another part of the network. If you're not reachable, then no problem. That's not going to spread. Or maybe it's a big problem if you want it to spread. The distance, given that actors can be reached, how many steps are they from one another? So if you are tied, but it's a long journey to get tied to someone, they're reachable, but the path is, distance is long. So if something has a probability of flowing through the ties, like a wire, if it's like at each little juncture, there's a probability that it might fail. The longer that path, the more likely the failure. But then the more paths, it kind of pulls it in the other direction. So the number of paths really matter in this case. So multiple routes. That's probably the key here is to think about some of Jim's work again with Doug White on structural cohesion, that some networks are more connected, that they have multiple non-redundant paths that connect the actors in them. And that would be particularly important for the ways that simple contagions will flow through those ties. But also, I guess, when you have multiple direct ties, then that might trigger your threshold. So it's hard to think of a network that has multiple non-redundant ties but not thick interfaces. Yes, question.
I'm actually curious about your thoughts on how this, if you look at diffusion as hybrid networks, where you have people that have physical relationships but also have relationships online, and some of those are repeated connections, but they're not the same. And how that, I don't know.
Yeah, no, so multiplex ties is have we covered that a bit? Yeah, so certainly I think we all understand that social life is often layered, that there are, it's like Jim's like my colleague, but he's my friend, right? And that there are ways that, people, have formal, informal, that they have different kinds of relations to each other. And that really has served as a function of, in particular, thinking about role analysis. So you stack matrices of multiple different types of relationships to try to figure out what are the kinds of people that exist in this social structure, right? Does that make sense? So you certainly could do the same thing with diffusion to try to think about what kind of connectivity it matters more than others. You could do a little horse race. It's like, I think that many of us, for example, who've studied political polarization, have thought in the past like that direct friendship ties matter more than online kinds of ties. Well, guess what? I think we're wrong. It turns out that the psychologists have been kind of right all along, like that our relationships are kind of in our head. And if, people, I mean, think about all the people who are just like, my daughter, my best friend, all these people think I'm crazy, but GK76 says they're drinking children's blood. I'm all in on it, right? So is that answering your question in some way?
But also have these connections, and as you move through distance, like those networks are breaking off from organic patterns in the way that you normally would for your geographic setting.
Yeah.
So now connected through these
Yeah.
people, and you feel like those online networks might be a space for like continued strengthening of those like those bond relationships, or maybe because you see these people, you see them, but you don't actually know what's going on in their life. You're actually having there are weak ties that never end up being.
I do think that's like a really interesting area for development, and it reminds me of when we were presenting to some folks, and that they were saying that in the military they seem to be having a harder time with sort of some of the commitment generating mechanisms that they've had in the past, because generally to get people to commit, you separate them from their past, right? And then you generate all the kinds of strong ties within the network. But if they're like, going into the bathroom and they're like on their phone and they're interacting with their friends and their family, there's this other tie that's kind of competing with the earlier model of socialization that's going on. So it's like, in that case, it becomes an impediment to the social influence processes that seem to be vital for generating the kind of group commitment that enables people to basically kill and die for each other, right? That if they're like not separated and really generating those strong ties because they're also kind of have this online and social media life. So that's more what you're saying, right? I don't have an answer for that except to say that go out and do that. And I think, do you know other research that's been, because I think that that's a cutting edge kind of set of thoughts. Yeah.
My guess is that there's some well of social attention that humans have as critters. And the extent to which we have these kind of distraction features are going to, on the one hand, they create, if you're multiply connected, you essentially have made each path a little bit wider. You have fewer channels. But I think most online relations aren't, a lot of online relations, the reason they're kept online is because they're taking you into parts of the world. And so they're distracting, they're drawing down that well of human attention you have to invest. And so I suspect it is a trade-off. I think all of these principles apply. This is, a network is a pipe in this case. And so the fact that you have a 6-inch pipe versus a 12-inch pipe doesn't really matter, they're both pipes. And so the fact that they are working in different sort of, the question is whether or not they're connecting to the same sink or not. And I think if they're not, the water gets spread over a much thinner surface.
That's a great way of thinking about it. And also I think to draw out the analogy a little bit more, I think the answer to the earlier question in some ways was, we used to assume that interpersonal ties were wider pipes. And that assumption has been called deeply into question, right? That the width of the pipe may be a thing that is not necessarily dependent on co-presence and things like that. So just a quick view of this. You can see in this case, we live in a world of disconnected, node connectivity. In this world, we have a kind of one node that is sort of the cut point here, that between the two. Here there are two, and here there are multiple paths connecting. There are 3 paths connecting each independent paths connecting the actors. So you basically end up in a situation where the diffusion, of course, is never certain. So the probability is always, depends on the distance of the pipe in this case, right? With how many junctures does it have to go through? So it has to go through here and it has to go through there. And at each time, it may not necessarily spread. So diffusion increases with each alternative path connecting pairs of people in the network. And the probability that actor I infects actor J, Pij, is a constant over all relations. In this case, if it's 0.06 is the assumption, then in this case, S and T are connected through the following structure like this. At each stage, it has to go through, but there are two, so there are 1, 2, 3, 4, 5 paths here, 6, right? 1, 2, 3, 4, 5, 6, but there are 2 independent paths in that case. So in this case, it is 0.09 is the probability of the infection transferring. So the probability that, so basically there are lots of ways of calculating this. I don't want to put us back to sleep with math too much, but I'll put that out there. The illustration of it is easier to sort of get your head around, which is if we think of a constant probability of infection of 0.6, and we think of 10 non-redundant paths, then if there are 2, right, and then if there are 2 of 10, sorry, if there are 10 paths, it's almost certain. If there are 10 independent paths, it's almost certain to have a diffusion, right? And that goes down with the path distance. So as the paths, there's the number of paths, and then there's the distance of the paths, and those things are kind of toggling different parts of the probabilities. So as well as the constant probability of an infection. So if that is 1, then everybody just gets it when they're in contact, right? But there's some kind of stochastic process there that could go down in this case, right? That if it's 0.3 instead of 0.6, then we see very, very steep drop-offs in terms of path distance. The path distance matters. I know, Jim, you have a lot to add. So what are a couple other things that they might think of before we move straight forward to peer influence?
Yeah, I think for as far as basic sort of biological diffusion or these other types of diffusions goes, that all of these simulations that we've done in this case are one path at a time and independent paths. But I think it's also this notion that we're holding constant, the beat. There's great biology, and I think it's perhaps great sociology to be done on whether or not people's sort of susceptibility or continuous sort of whether essentially what affects PIJ. Because you can see the probability of transfer has a huge effect, a direct effect. And if it's the case that the fact that I work 6 jobs and I'm exhausted, it probably means that I'm more susceptible to getting the disease. In addition to all the rest of this, so as I think Craig's going to point out in a minute, in social diffusion, we're used to thinking about the feedback processes of what's going on with the if you will, and the person, but it's just as true in everything else we do. So I think that there's a very good reason to think about that some of these simplifying assumptions should be problematized both in the medical side and in the clinical side.
So stay tuned. Lots of great work, building on different kinds of simulations, trying to predict outbreaks. Jim's, done some very interesting work looking at kind of different ways that networks can, different kinds of networks are involved in how diseases kind of emerge and spread. So you've got like an animal-to-animal network that's layered onto like a person-to-animal network that's layered onto a person-to-person network. So you've kind of got ways of trying to build in a kind of multiplexity to this, and in fact, with different kinds of nodes. And so there's a lot of great work, I think, and now computational power and tools that are being developed here to try to do this sort of work. Now, I don't do this sort of work. I think about it, and I read it, and I think it's fascinating. The sort of work that I do has much more to do with people's attitudes and behaviors being basically a source of 2 main kinds of sociological things. One is the core of sociology, race, class, and gender, and that explains a lot, and it really does. That's like, if you got those things, you can explain a lot about people's attitudes and beliefs and behaviors. But a lot of times these are capturing ongoing social influence processes that have been happening over the life course. And they get contained in these kinds of categories, and those categories can become reified. And we think that, well, men and women, they're different, right? But maybe that's because of their networks more than their biology, right? And so clearly the sociology and the biology supports that. So the point here is that interpersonal influences are ongoing processes. We can't, as long as we're social, we're kind of affecting each other and being affected by each other. And we consciously or unconsciously start to adopt the attitudes and behaviors of our peers in particular. Again, peers are particularly important for a lot of these things. Because, like my colleague here, Michael Tomasello, has shown, the thing that makes us different than other primates is that we form a we, like that, right? Right now, SNNH 24, wow, like we've got an identity, we're a team, we got t-shirts, that's a thing. And we are able to do this, and we're able to generate with people who we share very little genetic material with, right? It's like, we're not family, we are family, but it's like, we're not family. Something else I've studied communes and cults, and I've looked at the relationship, the interesting slippage between when people will start to call each other sister or brother who aren't actually biologically related. So obviously this is a health sort of seminar workshop. Peer influence is hugely important in terms of health behaviors, teeing up again for the Ergum Sturgum and particularly the Siena model tomorrow, that if you think about me, 16-year-old me, it's like, how many cigarettes did I smoke before I met this person, and how many cigarettes did that person smoke before I met them, and then it's like, okay, now we have a tie, now we're friends, now we're peers. Now do I start smoking more, or do you start smoking less? Do we meet in the middle? Is there some kind of, so there's an underlying understanding of the process and what's spreading, and that shit's addictive. So, maybe it has a tendency to kind of ratchet itself up in terms of the person who's doing it spreads it to others more than the person who's doing it less. But also I think health beliefs and even worldviews are incredibly important for health. Trying to understand how people see the world, how they start to attach values and feelings and sort of how they see a behavior. I remember really thinking that it was cool to smoke, and I remember thinking and finding all kinds of reasons, like, well, it's part of, like, I'm a cutting edge, I don't care, so there's like ways of having a whole worldview. I'm an artist, we don't convention, life, it's the quality of your life, not the quantity. So all of these are kind of beliefs that can become attached and become a worldview. And that's something that spreads. That's something that you learn from others. Now, there are problems. There are always problems. But again, as I've said, the other spaghetti, most methods problems are theory problems in disguise. So these are problems, but you are not going to find a silver bullet to just take care of them. People who are like each other tend to form ties with each other. That's called homophily. And my colleague, Lynn Smith-Levin, wrote an excellent annual review piece on this. It's the most cited article in the Annual Review of Sociology and ever. Birds of a feather flock together. So people who are already similar are more likely to form ties. So if you don't take account of that, you might be confusing influence and selection, or homophily. There's reciprocity. People tend to form relationships and do things that they maybe exchange things. And if you aren't necessarily maybe seeing this, you might be seeing somebody giving something back to somebody. You might not, if you don't have the timing and when the relationship happened, you might be mistaking the directionality Transitive closure, people tend to form ties with people who they're indirectly tied with. The friend of a friend is a friend. That can be conflated with some of these processes. People who are popular tend to get more popular, so maybe certain kinds of behaviors are indicative of being popular in certain contexts. So maybe the smokers in some high schools are the popular kids, and so people want to be like the popular kids, that they try to become friends with them. So maybe that's not a direct thing. Shared foci, like you might just be in a place where there's a similar kind of exposure to certain kinds of things. Like, so all of these are potentially, not necessarily for sure, could be conflated with interpersonal influences. So there are broadcast effects too. Like obviously, we're not just in a world where we only learn things and are influenced by our friends. We might see the same television show. We might go to the same concert. We may have other kinds of exposure to things outside. Like they may open up a Chick-fil-A next door, and then we're all there. It's like, oh yeah. So that might be conflated with thinking that I'm influencing you in terms of your eating behaviors. And economists, this is the realm of a lot of cranky economists, and like my friend's father, Ben Mansky's father at Northwestern, is like, talks about the reflection problem, like, is it, again, which is kind of like about reciprocity maybe, or things getting the timing order. There are some possible solutions to this stuff that aren't necessarily statistical. You may have a good idea for an experiment. You may be able to actually go in and do something like Hannah Shepard did a study where they went into high schools, or maybe middle schools too, I think, and they took the networks of the kids and friendship networks, and they were able to see the kids who were the more central nodes in the network. And then they were allowed to do an intervention where they tried to do an anti-bullying intervention. And so some of the popular kids volunteered to participate in the anti-bullying campaign, be in a student rally, wear these bracelets, have their faces on posters, trying to reduce bullying behavior. And then they had that matched with other schools where they did not have the more central students in the network. And they find some pretty interesting effects. That you can kind of change the culture maybe. You can maybe change the culture of the school. Now with great power comes great responsibility. I don't know how I feel about all of that, but in this case, that's pretty brilliant. There are field experiments, so that's kind of more of a field experiment actually than a laboratory experiment. Laboratory experiments are you can bring people into the lab, you can manipulate the underlying structure of the network, or people like Damon Centola and others are doing this a lot now online with massive networks where they sort of vary the network topology. They'll say, okay, well, what happens if we make a small world where people can only communicate here, and then there are sort of like random weak ties, like quick interchanges? Do people change their behaviors? Like we'll give everybody a Fitbit, and then we'll start to see who they communicate with. And does that change? Does that lead to a global change? So there are ways of doing this with online experiments, perhaps, where you kind of as the researcher, you're manipulating the structure of the network, which is like a lot of researchers like, I get to play, network god. I will tell you, you're in a small world, and you're in an Erdős-Rényi network. Now let's see what you do. But obviously the important part of these kinds of experiments is we can learn a lot about social exchange theory, and I'll talk about social influence network theory. There are some natural experiments, like one that was done, it's not really, so at Duke, like a lot of places, you used to be able to choose your freshman, your first year housemate, and so what happened? People went online, they went onto Facebook, they went and they selected people who were a lot like themselves, and from the same town, same race, same interests, same majors, things like that. And if part of the power of going to a university is that you get exposed to difference and that you start to maybe see the world in a different way because you become friends with people who are different than the friends that you had coming in. This selection process was working against that. And so just this year, our colleague Sarah Gaither, I think, the article should be out. I'm assuming it's going to make a big splash, but it was randomized. So people now, we have a totally different housing structure here. Quad X. It's everything X. It's so like Gen X. Quad X. It's like, it's not Twitter, it's X, you know. Quad X is the model. They go into a dorm, they're randomized into a dorm, into housemates, and then they go, when they move from the East Campus to West Campus in the second year, they get funneled into dorms here with the same people. So, and so there are some very big effects in terms of who became, especially in terms of interracial friendships that came out of that randomization. So Jim talked a little bit about dyadic models. I'm a big fan of dyadic models, especially if you have a fairly large number of nodes in your network that are not necessarily as amenable to the kinds of Siena model and stuff that David Schaefer will talk about tomorrow. If you do happen to have networks that are, you know, what would you say, Jim, 200, 300 nodes for Siena? Or it's like, you know? Is David here? Hey, there you are. What's the, or now you're going to just say, oh, we can do it with 10,000 now, or?
I wouldn't do it. I mean, there's an assumption that everybody is aware of each other in the network. So you get
Yeah.
out of 1,000, you start validating that assumption. But practically speaking, you can 2,000,
Okay.
or multi-level with many networks.
Well, it's come a long way since I, you know, waited maybe 3 or 4 weeks for and gave up on a network of maybe 300. So, but obviously the power of this approach is you can model the coevolution of behaviors and networks. As long as you have multiple time points, you know, where you've observed it, you can actually capture, like, do people who smoke about the same tend to become friends with each other, right? That's homophily. We can take that out of the model, and then we can see whether or not they then stay friends or whether or not they start to smoke more. And I don't want to stay too much because that's what Dr. Schaefer will do. I'll talk a little bit more today about my own work in what's called social influence network theory. Just quickly, dyadic models, if the process is entirely dyadic, especially if you're like looking at like something like married couples and pairs, or I did an experimental study of dating, speed dating, like when people on speed dates click with each other when they don't, right? So it was like an experiment where they all sort of interacted and they recorded it, and we basically tried to predict like when do people click, right? That's an inherently dyadic process, and so you really it's kind of a core issue in terms of predicting the network, but not so much trying to predict the outcome of the network. So one of the more famous studies that was done was by Christakis and Fowler, 2007, and you're probably all familiar with this study, the Framingham Heart Study, which was data that wasn't collected for the purpose of doing a network analysis, but because they collected additional data on contacts, you know, who would we contact, who are some of your friends, who's your spouse, other things. And because the town, Framingham, was small enough, they could link this up into a fairly connected structure. Then they could look over a 30-year period of time, and they could see changes in this network over time as the individuals generally got bigger, as people tend to as they age. But then, even though there's that general trend, like some were getting more big, right? So, so the idea was, have you seen the video of this? Have you showed this? Have you ever seen? You haven't seen it? Let's do it. I'm gonna drink some more coffee while we listen to this. Oh. Okay. Yeah, well, if the volume worked, we would be hearing, I think, what the colors are, but I don't.
I think on the
I apologize. I don't know. What's that?
That'll feedback.
Oh, yeah. Okay, let's go back. Okay, I won't get near the speaker. I'll do my Jimi Hendrix kind of thing.
Is a dynamic graphic representation of a portion of the Framingham Park study social network. Each circle or node represents one person in the data set. Nodes with red borders are women, and nodes with blue borders are men. The size of each node is proportional to each person's body mass index, or BMI, which is the weight in kilograms divided by the square of the height in meters. A yellow node represents an obese person with a BMI greater than 30, and a green node represents a non-obese person. A line between two nodes represents a social connection between two people. Purple lines connecting nodes denote close genetic ties, for example, parents, children, and siblings. Gray lines denote non-genetic relations, such as friends and spouses. Obesity is a multicentric epidemic, with many people influencing one another and forming ties in complex ways. The network gets more compact and dense as more ties appear, and the entire network gets heavier over time. Quantitative analyses demonstrate a tendency for obese people and non-obese people to form clusters within the network, so that by the end of the study, this clustering can be discerned as in the densely interconnected clusters of obese persons here, and the non-obese persons here. The prevalence of obesity appears lower at the periphery of the network as compared with the center.
Yeah, so again, the study, it made a huge impact, and immediately the economists got very, very cranky, and that's their job. It's all right, But, the identification strategy, what are all the conflating factors? And so, we have a lot to learn there about, instrumental variables and all the other approaches that you might use, but then it opens up a whole other cans of worms. So a lot of this stuff is about disciplinary, standards, right? In sociology, we definitely don't obsess as much about really capturing the exact coefficient, but as long as we've done a due diligence to say, well, the effect is clearly there, and it's kind of in this range. So again, most methods problems are really theory problems in disguise. And Christakis and Fowler did a lot of due diligence that I think was kind of overlooked in the hoopla. A lot of people just, pimples seem to spread as well. We went and reanalyzed it, and acne seems to spread through these networks, and it's outrageous. That couldn't possibly be the case. And then you kind of go well, could, actually. Or maybe there's, but then, so anyway, I think it's more about trying to do your due diligence. Again, no one study is going to do it. No one analysis is going to do it. They compared the social distance between ego and alter and the geographic distance between ego and alter. For one, in terms of the relative increase in the probability of obesity in an ego if alter becomes obese. And they had 7 different examinations of this. And they find, as you can see across these, that the social distance is way more important than the physical distance. So what explanation? That definitely helps to discount the idea that it's just that delicious Chick-fil-A opened up next door, right? And that it's instead something about people's social comparisons with people. That might be the mechanism. Is your hand up? Yeah.
Yeah, I don't understand why this comes back, because we know that people's access to nutrition is guided by Northern geography. The same type of people across the whole nation have the same type of access to grocery stores, healthy foods. So I don't really understand why we say this has anything to do with it or anything specifically.
This is more of a sensitivity analysis, I think, which is you would expect, in other words, you would expect if this finding was really driven by geography and by a broadcast effect of just being in the same neighborhood, having the same socioeconomic status that might be tied to geography, or being located in a certain space in which you maybe have better access to fresh, you're not in a food desert, or you are in a food desert. And so you're basically looking at the physical distance between people, and you're comparing that to the social distance. And in this case, the physical distance doesn't really seem to matter all that much. But the social distance, that is, whether or not we're directly tied or indirectly tied through our peer or kinship networks, is the thing that seems to matter the most. Now, I'm not saying that boom, drop the mic, we did it, I'm out, right? But this is a sensitivity analysis, right?
Yeah, maybe I'm getting too much into the nitty-gritty of this specifically.
Yeah.
But I'm curious, like, do the methods of peer influence, rather than looking at geography, look at how these social distance might have, like, be closely correlated with context. Like, not just because we're farther apart, we know that the new Chick-fil-A opening up means that this is why people are getting obese or not. Like, the people who are socially close are also more likely to exist in food deserts, regardless of where they are.
Well, but this is a small town. Yeah. Yeah, it's a geographically constrained area, so yeah. I mean, I'm not saying, again, it's like, have we completely taken care of the error term here? I don't think that's the point. Jim, do you have something to add as well?
I just point out that the beauty of that particular question is that that's an observable, so it's controllable and not. So we know exactly the social distance and the physical distance.
Yeah.
The social distance effect is net of the physical distance.
Yeah, so you can kind of sweep that effect away and see what's left. And yeah. Mm-hmm, please. Mm-hmm. Well, that's a great question too. So I'll get to that in a second. Yeah. The point is that these are the kinds of questions that we should all be asking. This is the mind of like a scientist, which is, what if I'm wrong, right? Like, I want to really prove myself wrong. And if I can't, then I'm going to just provisionally accept that I'm probably right, okay? And I think that's the process here. So the other way they tried to do this is they looked at the different types of ties. So maybe this will also help explain a little bit of what you're getting at, which is it seems that if ego perceives Alter as a friend, that matters. And it matters even more if it's reciprocated. If I say you're my friend and you say I'm your friend, then that has the largest effect. But interestingly, if you think I'm your friend, but I don't think you're my friend, that doesn't seem to matter. So that directionality check really points to a mechanism that's more about social comparison. Like, you're in my world. My pipe of influence is open to you, right? Because I perceive you as my friend. Now, you perceive me as your friend, and I don't perceive you as no pipe. Okay? So, again, it's you can look at this effect, in terms of its comparison with siblings, which, spouse, it's even stronger than your spouse. So it points to a mechanism that suggests a connection between attitudes and behaviors, a connection between a certain norm and what one thinks of as terms of maybe how much one consumes or what a body should look like. And as sociologists, obviously, there's no judgment call here. I believe people can be healthy at every size, and maybe that's a controversial thing or not among health scholars. But I do think that I do want to just put a note there that there's another level at which, like, there's a lot of other things going on here that we should think of in terms of social construction. Yes?
How is the causality established? How do we know it's not a case that
Yeah. So how do we get the homophily effect? And that's connected with your question. I will get to that in a second. Yeah. And I'm not going to say that again, it's not like they just hit this out of the ballpark, or else they wouldn't have gotten beat up by every economist. I do want to say that there are other sort of dyadic approaches that I've done in the study of the Stanford faculty and their collaboration networks over time. This gets at a certain kind of robustness check in some ways that I think also gets a little bit at your concern, which is, hey, if I collaborate with you, then and we do well and we publish, then maybe we're just going to keep on collaborating together more, and that this is a kind of like, or if the sort of equivalent might be, if we go out to eat together and that's a thing that we do, then it's a kind of synergistic effect, that it's a kind of, it's not exogenous to the network. It's like, well, what do you do together? Well, we're central people in the network, right? You notice that they tend to be the ones who got bigger. There may be people who have more friends, and having more friends means that you go out with people and you do things. And so maybe that's part of being a friend in Framingham. I don't know. Maybe part of being a productive scholar at Stanford is we just get together and we talk and we write lots of grants and we just, that's the network. But if we're really thinking about influence, you would think that the influence would have a spillover effect. That if we were able to see somebody's behaviors or attitudes, in this case behaviors, really, apart from the social tie, that it would change their behavior. In other words, I'm going to be smoking more by myself, after I am influenced to smoke more. And it's like, it's not just I smoke with my friend. We're just all smoking more together. That's what it means to be a friend here in Eugene, Oregon in 1989, as we smoke. That was part of it. But like by myself, contemplating the stars, I'm smoking more. With my brother, who's my, kind of my friend, I'm smoking more, right? So there's some way that outside of that, there's a spillover effect. So there may be ways to kind of parse out that over time. And that's what we were able to do a little bit in the Stanford study by looking at, do people write more grants? If I write a grant with Jim, who's a master grant writer, I'm going to learn some stuff, right? And am I going to take what I learned and am I going to bring it over into writing grants with other people? And am I going to be better at it? And I would say I probably am. And based on the model, we looked at the number of the total spillover effect in writing grants and through different kinds of network ties, whether or not we collaborate on a grant together or we're on a dissertation committee together or we're just in the same center together. So different kinds of ties might be more conducive for certain kinds of behaviors. They might have a kind of elective affinity for us learning certain kinds of things. So we found that in this case, obviously there was a kind of a direct effect of writing grants on me being better at writing grants. So if I sit on a dissertation committee with Jim, I might learn a little bit of the mojo. I might get a little better at writing a grant, but I'm not going to get that much better at writing a grant. Question?
Yeah, I'm still not understanding how we connect it to peer influence. Like if you like maybe Jim just writes grants with people who also have excellent early childhood education, just because they speak the same language, they get along really well. It's not actually peer influence at all.
It's a selection.
This person, yeah.
Yeah.
And how do you?
Well, I think that I think that you can handle that in a lot of different ways, right? You can include all kinds of controls, and then you can get cranky and be like omitted variable bias, right? There's none of that. You could also compare against different similar others in the network. So there are ways of handling those issues, right? They're not fatal flaws to the model. I will get more into modeling around some of this in a minute. But the general idea is that you can include a lot of different fixed effects. So maybe we just say, look, we've got this over and we did this. We've got 15 years of data. We got 15 Jims. We've got 15 Craigs. Nothing different. We'll just stick in a fixed effect for each of us, right? And so then do we see changes? So you can sweep away all of that stable stuff. It's like I had excellent handwriting when I was 4. Gone, right? That's not in the model. So, again, these are nitty-gritty things. I'm happy to hang out. We're having a pig poll. We can talk more about this stuff, right? What I want you to get is I want you to just have the drive to know this stuff, right? So I like that you want to know it. And I just want to assure you that there are tools for getting us really closer to it. Jim, do you have anything else to add to it?
It depends on how deeply you're going to go to the modeling stuff next, but I think the main question is there's always this discussion between what's observable and what's unobservable. And what's unobservable and controllable, and what's unobservable and uncontrollable. So anything that's fixed, so that the unobservable and controllable is like the fixed effects of features. The unobserved and uncontrollable are some time-varying, unobserved measure that you think is affecting this confounding your peer influence with whatever this thing might be out there. And I think with the beauty that the critics of these models have taken for these kinds of approaches is that things you don't know are frightening. But if you think about it for a minute, how big can the monster be under your bed? It's only 3 inches tall under there, right? There's not a lot of room left for a big monster under the bed. Once you control for the observable, you control for the fixed unobservable, the unobservable confounders that could actually change the result are really hard to think about. Like, what are those things? So is it mathematically possible? Actually, probably not. Yeah, and that's what Ken's entire systematic sort of work on sensitivity analysis is about, is that you can actually estimate the size of how big an unobserved variable would have to correlate with the observed variable in your model to discount the sect, or to turn it around an experimental framework, and you could understand how many of your cases would have to be experimentally removed from a treatment effect to a control effect in order to invalidate the response. You can actually put a number on that for how big it would be. And it turns out that the vast majority of times, there's nothing left out there that could be that big. And so I think that we're afraid of things we're afraid of the monster under the bed because we can't look under the bed, but we can estimate how big the space under the bed is for the monster to hide. And most of the time, it's not nearly as big as we might think it is.
All right, I do want to, I'm just going to skip over all the stochastic actor-oriented stuff, because come back tomorrow morning and you'll learn all about this. I've used it, I've done it, it's cool. You should learn how to do it, and you'll find lots of cool things that way if you persist. Now, I was trained in this area, social influence network theory, that I'll touch upon briefly. I don't want to take up too much of Jim's time, and but I do want to just put down a big flag here for this type of model, which was really developed by one of my dissertation advisors, Noah Friedkin, and really captures the 2 aspects that of these processes. I think the sort of initial socialization model, race, class, gender, whatever, gets you to time 1 in your thinking about the world or your behavior. Generally, this is done a lot on opinions or beliefs or attitudes. So, do you believe, and a lot of this has also been done a lot in political polarization research, so trying to think about whether or not people are for or against certain kinds of issues. And that's some kind of linear combination of things in your life and some coefficient attached to that linear combination of things. Controlling for, putting that aside, there is this other process going on, which could be more or less pronounced, which is a social influence process, which is, again, let's not belabor the math, but it is cool. It is cool. If you're the sort of person, or you live in the sort of world, let's say, where everybody basically thinks that they're right 100% of the time, then there is no social influence. That means you've attributed absolutely nothing to others. And that's what this alpha is. So 1 minus 0 is 1, and this becomes your time 1 belief. This is wiped out. There's no social influence process at all. But most people, in most worlds, most things, there's some kind of balance. People attribute some influence to others. And they may not attribute equal influence to everybody in their group. When Jim says something, I attribute more influence, especially around certain kinds of salient topics. I'm like, yes, I put that on him. And so that's what this W matrix is. The W matrix is the attribution of influence to others in the group. That can vary from 0 to 1. If we belong to a cult, if we're all in a cult of Jim, we're all Jimlets, then we all attribute 100% of our influence to him. We attribute 0 to everybody in here. We're like, what are we doing? All right, and then we do it. All right, that's a W matrix that has an entry where all of us, it's completely, this is why it's called a social influence network. The network itself is the attributions of a kind of weight to others. The weight can only sum to 1. There's only so much of me to be open to others. And so if I attribute some to myself, then that ipso facto makes it so that I can't attribute it to others. So if it's 100% me, I'm just like, I'm perfect. It was absolutely perfect. There's nothing, for me to be influenced by because I'm perfect, right? Now, if I'm a person who's completely, insecure and I have no idea what I think and I just give it all to everybody else, right? Then I'm going to shift a lot. This model has been estimated in a lot of experimental conditions, bringing people into the lab, having them kind of like a mock jury situation, Is he guilty? Okay, well, how much money should be given in this case? We have to we're going to try to come to consensus on this. We may not come to consensus on it. So it's an iterative process so that at time t, my opinion is some combination of how much influence I accord to others and their previous beliefs at the previous iteration, plus whatever I weight my own opinion at the initial time of our encounter. So generally, this model has been elaborated in lots of different ways. So I basically explained all of this. The weights are constrained to be between 0 and 1. The sum of them is 1. You can look at this in terms of a network effect, that you have a network of people, but how much influence do you attribute? Maybe you attribute even influence through your ties, like everybody in this case, gets an equal weight of that and their own opinions. These people aren't tied, so 1 and 4, 1 accords no influence to 4 because they're not tied to 4. You could think about it in terms of like maybe I weight everybody twice myself, or maybe it's a entirely network structure. Like the more central you are to the network, the more people accord influence to you. So there's generally a way that people gain prestige and status in a network, and those people have more influence. And that's partly why they're in the center of the network. So you can then look at this as an iterative process of interpersonal influences as they unfold over time. And if you put it on a kind of network scheme, a kind of underlying topology, where maybe there are 3 different groups, and initially people just have random opinions in this world. Maybe they have 2 random opinions. They like Beyonce, or they like Taylor Swift, and some people like both, some people like neither, as a lot of people kind of more in the middle. It's just a random tastes or not for 2 different artists. And then if you unfold over 7 iterations and you accord some influence to others in the network, The network over time will start to converge onto something like a consensus, but in this case, because of the network structure, it never fully becomes realized as a complete consensus. The other part of the model that's interesting is that people may have heterogeneity in how much they attribute influence to others. And so maybe there are, again, some opinion leaders in the group. So if we put in to the group, in this case, you know, the alpha varies across people. So some people are just inherently more open to influence. They live in the same world. Some people are really closed off to influence. Whatever is there is is distributed among a weighted matrix of alters. So this allows for certain kinds of people to be opinion leaders in the group that have more pull, maybe for some people. It also allows maybe for some people to hold consensus in hostage, that they don't listen to anybody but themselves. And so they will not converge. So they're either going to be an outlier, or people are going to, if anybody attributes any influence to that person, then that person can make the group eventually. Maybe after 10 years, we converge on that person's belief because they just are stubbornly, you know, it's what was it, the 12 Angry Men sort of model of this. So if you have a group leader here, and you have a group leader down here, and you iterate this opinions of artists over time, you'll start to see through the network, it starts to actually be, arrayed in a kind of a different sort of structure of disagreement, and perhaps a kind of polarized world in which people are kind of converging on two different opinion leaders. Okay. Over time, I don't have time to share all of the cool stuff. I've studied book groups and how they converge on opinions around a novel. I've been studying Duke Divinity students and their social networks and how they converge or not on attitudes and beliefs around sexuality in the Bible. I've incorporated a lot of different things into this. What if beliefs are interconnected with each other? You know, if I stop believing in Adam and Eve, then maybe is that connected with a belief in sexuality or not? And people are telling me it is, so what happens? If I change this, do I change that? So what happens when you start to think about whole worldviews and how worldviews may be more or less constrained in this process? I lied and I didn't get to the statistical model of Christakis and Fowler, but the answer to some of it is that they include a lot of lagged effects, right? So they're like, well, let's just control for your belief or your size at time one, or let's just put in other kinds of controls for it. So that again, these are nitty-gritty modeling questions. They will never solve all your problems. So in the end, the sort of takeaway is, boy, I have a lot more slides to show. The takeaway is there's no perfect solution. Science is a team sport, and we're on the same team. Okay, thank you.
All right, thank you very much, Craig. I would normally let you guys ask him a bunch of questions, but he should take a whole day at some point. I'm not going to let him, because I need some time to prep you for Scott and for
David's work tomorrow, so we're going to do a little bit of background method stuff.
And I'll be around, and I'm determined this time to get to see Dr. Schaefer do his talk tomorrow. So these things are sometimes best discussed over a barbecue. So let's see me.
Awesome. Thank you guys. Folks need coffee. We get a quick break. Stand up. I got to put my machine this on. We're going to do it. We may do a live argument.
Ideally, camera too, but I'll turn it on. There's a button right here on the side. Little red button, but I'll be back in a minute.
All right, so apparently I don't know how to read, so I put my slides in the Urban workshop folder, not in the Disciplinary Networks folder on today's date. So hope we're having fun. Oh, we copied it. So now they're both. So in the statistical introduction to Urban folder, there is a .r file, which is the Moody Urban 2024 file. I speak R the way that Ava speaks English. I sort of like memorize the phrases, and I have sort of my at the right time. So this is a bare bones version of the set. There's also a .r data file in that same folder, so you can load that directly. The key element to make that work is that you're going to have to change your directory so that when you use it where you save that file. Now, I'm going to run a couple of bits that are live at the end of this presentation, perhaps. But otherwise, you'll see that I put everything in the slides, screenshotted, so that you don't have to worry about the fact that I'm writing the wrong file. So, but you can run this at home where it's not. Well, folks are doing the thing. I will point out just briefly. I really do recommend you go out and check out some of his Frank's work. He really has done a really nice job of building these tools. He now has an R tool, but it's like he really wants people to use it. He actually literally has an Excel file. You can take any given effect from a regression model, you plug in its coefficient, standard error, elements about the kind of correlation that you have there, and then ask yourself, what's going to happen with this? And it'll go through and tell you, it'll do this counterfactual analysis where it says how many zero effect cases would I need to have to invalidate the result, or how strong would another variable have to be to displace the findings that I have. So he's really done a good job of estimating the size of the monster under the bed. So I strongly encourage you to go find it. It's a great set. Whoa, sorry about that. All right. Is that too loud? Loud enough? We're okay? All right. First, Meltem, were you still here? Meltem just became a citizen this morning, so she just finished her test. So, congratulations. That's awesome. All right. Jokes about, being members of clubs it's not clear you want to be in, but aside, congratulations. All right. Okay, so what I'm going to do is talk about statistical models from networks from the current slide. Okay. And this is it's a much, much too big of a problem for the next time that I have to talk about this problem today. So it's going to be a little bit fast, and it's going to be, again, get at the conceptual set to see what's there. We have two ways of thinking about this. One is the graph is the dependent variable, so we're actually trying to explain the graph itself and what predicts the extent of ties and the different ways you might do this. And then the alternative is the graph is the independent variable, so we want to use the network to predict some outcome as we go. And so we'll talk through mainly on the first one, and in fact, the vast majority of time is going to be spent on these exponential random graph models once we get there. Now, when I say that this is a deep field and we're just barely scratching the surface, the point, of course, is that the history of random graphs, which is really what all of this work is based on, is a deep mathematical field. So random graph theory and sort of processes on random graphs, it's a well-known series in mathematical and physical sciences and statistical sciences that we're just going to spend a little bit of time on. But you can kind of trace the applied roots, the part of the world that we're going to spend most of our time in here, comes back through a series of ideas. And I want to give you a very informal understanding of what some of these ideas are so that we can get a sense of it. If you want to do more, and some of you will, and I strongly encourage it, check out these books. So there are some great books out there that have gone on over the last 10 years or so that have been building on these sets of models.
for those of us in the social sciences and you really want to sort of dig into statistical modeling of networks, the Inferential Network Statistics Analysis book in 2021 that just came out by Brice Damaris and his friends and Kramer is an excellent book. Also, we have the basic intro in our textbook, and the handbook has a series of chapters. There's also, the literature on this field has gotten really deep, so there's plenty of work to do it. For those of you that are statistical modelers and formal statisticians, I highly recommend Eric's book. It comes with some R packages that go with it. They're a little depreciated at this point because he hasn't updated them, but it gets you into the nuts and bolts of how this stuff works. So, network inferences problem are a little different than the kind of inference problems that we as social sciences are used to thinking about. So we're used to thinking about the inference problem of I sample a dozen nodes, they tell me some variable like their value, like the mean on those dozen nodes. How likely is it that that number applies to the rest of the population? So we're trying to infer from a sample to the population. In the random graph world, we really want to assume the network we have when we do a network analysis is the population. So there is no inference question, right? So I don't need to infer whether or not this network is representative of the population because I have the population. I've solved that problem by assumption, so I can go home, right? So there's nothing to do. So what are we actually trying to do? What we're trying to do is figure out whether or not this object that we've seen, this network object, would be observed by chance alone or not. So if I were to take this network and flip a coin, would I observe the same thing? So in a counterfactual, Marvel multiverse kind of world, to continue the geek sort of strain we've gone through the last couple of days, would I found the same thing in lots of different sort of versions of the universe, or is the version I had really unique? And so that's the key that we want to go to. And so it turns out that how we get there is a little bit hard to do. The core problem with it, like we see in a lot of things, is combinatorial. The number of possible graphs of the size of any graphs we aim to see grows, I hate the word grows exponentially because the exponent can be, negative, but you get the idea. Geometrically is a better phrase, right? So the number of possible graphs that are out there that you could compare your graph to is really big. And so we can't just go out and actually do a physical comparison to the universe of possible graphs. And so what we need to do is have some kind of a construction feature or some kind of an element that lets us assume what the universe of possible graphs looks like so that we can make sense of it. And the simplest possible universe of graphs we could have is known as an Erdos-Renyi graph. In an Erdos-Renyi graph, for each cell of the adjacency matrix, I flip a coin. Right? The edge is either on or off. And when you do that, the beauty of that process, of defining a coin flip process or a random assignment process, is that we can know some things that are very constant about the graph. So some really good formal proofs and understanding of what's going to happen. So for example, we know that we're going to end up with a Poisson degree distribution in the network or something like this. We also have some great sort of theory that shows us that when you do that process of flipping a coin, that if the average degree in the network crosses 1 of a pure Erdos-Renyi graph, you go through a phase transition where you have lots of disconnected pieces, a short ramp up, and a fully connected graph. Right? Notice one interesting feature of this. Right? It's not the density of the graph, it's the average degree. So this applies for a network of 100 nodes, 1,000 nodes, 1,000,000 nodes. That's kind of mind-blowing, right? It's kind of amazing that these practices have. But it's all in this assumption that the process that we're dealing with is a purely random coin flip kind of process. So what we'd like to know, of course, is that the simple random graph is a really poor model for real life. So very few of us have formed our relations entirely by random. We have something else going on. And so we need to condition on more than just the coin flip. We need to condition on other features of the graph, like the probability that we'll be in the same room, or the probability that we're the same age, or these other kind of features. So we can do that. Now it turns out, excuse me, it turns out that some parts of these conditionings, that we refer to this narrowing of the set of possible random graphs as conditioning. So some of these conditionings are well known. So we can condition, for example, on the distributions of degree. So we know that if some people send more ties than others, then it's likely that they're going to have more connections than the people who send a few. And so that's an easy thing to condition on. We condition on the ties sent, the ties received. We can condition on groups in the network. So there's lots of things we can do. And oftentimes there's a trade-off between this exact uniform set and sort of a set of algorithms for getting there. So for example, there's a great set of tools that Stan Wasserman came up with in the late 60s and early 70s for calculating the expected number of triads in a network relative to the number of the distribution of dyads in that graph. So if I know the number of asymmetric and mutual ties in the network, then I can calculate the expected number on the probability of seeing one of these kinds of triads, and thus the expected value, and I can compare the observed number to the expected and get some kind of a distance score. And that's great, because that allows us to compare it to an element, the distribution of dyads, that should be controlling the number of triads. And so once I know the distribution of dyads, then I can ask whether there's a preference for the number of triads that's above and beyond what we'd expect by chance. So for example, you might say that the fact that there's only 5 complete triads in this network, and I remember there's a few hundred nodes in this network, I forget how many, but 5 seems like a small number. But 5 is almost 10 times what you'd expect by chance, given the distribution of dyads in this network. And so it's actually, there seems to be a preference for closed triads in this network that you wouldn't have observed by just looking at the count. So that kind of conditioning is the process we're going to do throughout our set. And so this is, we do that process, for example, in the AdHealth data, and it turns out that across all of our schools, so this is a box plot of these expected values compared to observed values for all of this 200 different schools in AdHealth. I think it's about the right number, 120 some odd. And so what you find, of course, is that there's a relatively strong preference for transitive ties. So this notion that a friend of a friend is a friend, right? We see those kinds of triads observed more than we would otherwise, and we're unlikely to find these cyclic triads, or particularly these triads where a friend of a friend is not connected at all. And so this has some intuition about what drives the kind of networks we observe in these settings, and we can get those insights by looking at these conditionings. Turns out that if you know the distribution of triads, you also can say something about the global hierarchy in these networks, this is some really fun work that's been shown that if you constrain a network to get rid of particular types of triads, it implies that you must have certain kinds of macrostructures in the network. And just drawing a blank on the author's name for this work. It's like Jimmy, it'll come back to me later in the set. But what's nice is we have indices for these. So we can actually go through each of our schools and say, well, what kind of archetypical clustering system characterizes, in this case, in-grade networks in schools? And what you find is that we tend to have networks that are akin to this kind of hierarchical clustering or this collection of clusters kinds of model. And you might imagine, these models don't tell us how big these cliques are or these components are, but we know that these networks have this kind of clustered hierarchy and often multiple branches. And in these schools, these are 6th graders, what you end up having are usually boys and girls, right? So you can see, we know that by looking at these curves. So that's the advantage of random graphs. I'm not going to spend any more time really on where random net graphs themselves come from, just to say there are models out there for testing known random graphs of different kinds of patterns, different kind of micro constraints on the graph that allow you to judge your observed graph against us. We tend to take a much more constructionist approach to this kind of random graph construction. And it's to imagine, instead of saying that if a simple random graph doesn't fit our model, maybe a collection of aggregated simple random graphs would do it. So imagine I give you a network that looks like this. And so this is a network of adolescents. And in this case, there's race mixing. And so we find that the density of ties within the white group is higher than the density of the ties from whites to blacks or from whites to others. And if you look across the diagonal, right, that there's more ties on the diagonal than there is off the diagonal. So that's a block structure in this network. And so I know that a pure random graph isn't going to help, but I could construct a graph that is random and meets that. So I could say, let's have a network where I have the probability of I assign nodes as they match the population, and I match the density, but I flip a coin that's just weighted a little differently within group and between group. And so all I've done there is construct a new random graph where I've partitioned the purity randoms by varying the level of ties in each of these different types of cells. Now, as you can see, it still doesn't match very well, right? So this is a better match. I've matched the mixing matrix, but the structure still isn't right. So this is still a much more diffuse sort of hairball graph, and there's something patterning the network in the observed case that's not captured by just the mixing matrix. So we need something else that isn't there. So in this case, we notice that the degree distributions don't match, so maybe we need to do something like that. And that's the kind of logic that we're going to do. We're going to say, if this works a little bit, then maybe something else like this would work better. So I'll condition on both race and gender. And if that works well, then maybe I'll find some other series of buckets that I can put people in, little compartments. If I get down far enough and I structure all the relations between it, and you of course recognize from yesterday that I stole this graph from somewhere else, but conceptually you get the idea that maybe that would work. Or I could ignore the buckets entirely and just think of something like a latent space and say that nodes, I'm going to define some space such that nodes that are close to each other have a tie and nodes that are far apart don't have a tie. And that's the mental process that we're going to go through when we think about building these kinds of models. We're going to construct sub-random graphs that we've constrained in a very particular way so that the probability mass, if you were to draw a graph from the space implied by that model, looks a lot like the model where the graph we've observed. That's the notion of fit that we're going to use. So the notion of fit and the notion of hypothesis testing is, can we generate a network for which our observed network would be a reasonable draw from that distribution in the population? So whatever constrained distribution of random graphs that are possible in the world out there, it should be the case, if we've done our modeling well, that our observed graph would be a plausible case drawn from that distribution. So that's the fit structure we're trying to go with. Please.
Just so I make sure I'm following, is this primarily for this hypothesis testing, or wanting to have this comparative
Yes.
random graph population to draw from that matches vaguely our model?
Yes. It's
It's for hypothesis testing.
It's for hypothesis testing in this particular sense. And the logic is that if I'm really clever and my theory is good, I should know how to condition the space properly. So for example, I thought that race should condition this graph. Turns out that theory was pretty wrong, but something else might be.
Condition, do you mean like you're throwing it in, using it like a linear
Yeah.
probability sample analogy? It's like throwing it in as an additional variable.
Yes.
To create that constraint.
Yes, exactly. And I'm going to walk through a step of that.
Like mapping the new words to the old words.
Yes, fair enough, yes. Thomas. We do it computationally. We simulate a whole bucket load of networks from the model and see if all the moments of our observed graph fit squarely in the middle of those models. And as you probably know, that might not be a perfectly good test, because it might be I picked the wrong moment to compare. Right. But that's the way we do it in general. All right. So the version of this version of that model is exactly what I've done here. So this is the sort of conceptually buckets turn into spaces. And so the space model was developed by Peter Hoff and Mark Hancock and Mark Krzyzewski. Other people call these Hoff models, for example. Peter Hoff is in our stats department here. We stole him from University of Washington, where they worked with Rafferty and Hancock at the time. Pavel's now in Australia, if I remember correctly. And so the model looks something like this. And I know that everyone hates the equations in this room, but it's worth having a little bit of a look at it. And so most of us as social scientists are used to thinking about a logit model or a logistic regression. That's how you predict a binary dependent variable. And so the logit predicts the probability of a tie between I and j is conditional on a set of features, some overall density features, so the number of ties in the network, and the distance on two imaginary variables between I and j. So that's all this equation says, is that the closer we are together in that space, the more likely there is a tie, and the further apart we are, the less likely there is a tie. And the beauty of the latent space model is we're going to make z up. Like z doesn't mean anything in reality. It's a variable we're just entirely going to make up. So this is an example of what this model kind of looks like. The Samson Monastery data is That's traditional old style data that comes in the network, and it's a stochastic model. And so we end up trying to find positions in the latent space that that predict the likelihood of a tie. So we just keep adjusting your assignment. In this case, I've told the model there's 2 dimensions. And so I keep adjusting the relationship between these 2 dimensions and each person's value on each 2 dimensions until I've fit the best likelihood that we have a tie is corresponding to the space in that set. The stochasticity of it is generated that each node could be in any one of these little cloud of spaces. Right? So that's what I mean by saying it's a stochastic process. The beauty of these kinds of models is that they're really, really flexible. And so in this case, I have a 2-dimensional space, and you just fit the model. I could fit a 3-dimensional space. I can add non-homogeneities to the space. So I can say instead of having just 2 dimensions that are completely uniform, I have 2 dimensions, and there's 2 groups that are built on, or in this case, 3 groups, where the distances within are weighted differently than the distances between. So all of these is built into the model, which is kind of fun. The beauty of this set is that it greatly simplifies the modeling exercise. We're going to go through in the next model, which is not a latent space model, in which you have to specify what builds into this conditioning. So the beauty of this model is that it really does just finds the best fitting imaginary variables, Z1, Z2, that distance predicts tie values. And so it almost has to fit, right? But there's no sense of which this means anything socially, right? So there's literally nothing. So it might be that this is race, it could be age, it could be income, it could be whether or not you howl at the moon in the middle of the night. Like, we have no idea what it means. All it means is it's a good predictor of a tie being there in the distance of the space. Now, if every methods problem is a theory problem in disguise, it might be that this teaches you something, that when you look at the space, you learn something. But it might also be that it just helps you control for things. You can do this with weighted or binary ties, so it's really become a very flexible modeling sort of system. My favorite use, just in the interest of time, for latent variable models is when I don't know what's driving the disruptions of the model, but I care about something like homophily. I can throw in a latent space and then test for homophily on my others. And the latent space essentially soaks up all my unknown variants, and then I can test whether or not the homophily effects work independent of it. All right. Now let's spend a little bit of time thinking about the logic of how we might build up a more specific model, where I don't want to let the latent variables define the ties for me, but I want to actually have some control over what drives the ties in a network. So this is not an exact analogy. I'm playing a little fast and loose with it, and I'll correct that in a minute. But just start with the idea that you have a standard kind of a logit model, and you're trying to predict ties on a matrix. And so in this case, we could imagine that the probability of I've observed a graph that looks like this. And so in this case, the ones are bright red and the zeros are blue. And so that's my observed data. And I'm going to say, what things can I add to this model that would predict the probability of those ties being there? So the first thing I could do is just have an intercept, right? And so this is what a simple Erdos random graph is. And so I say the probability of a tie between I and j is a function of some constant. And in this case, that constant equates to a probability of 0.24. That's just the density of the graph. So all I've done is given you an equation version of what the density of the graph is. Now, because this is a logit model, this thing is actually on the log odds scale. So the coefficient you get out of the model is going to be something that's largely uninterpretable to you in the probability space. But you convert a log odds to a probability by taking that value and divide it, you exponentiate that value divided by 1 plus the exponentiation. You should get 0.24. Right? So that tells you what it is. Now that model does something, right? It tells me if I were to draw 1,000 random graphs from this probability distribution, I would get a series of graphs that on average have the same density as the graph that I observed. But I wouldn't tell me anything else about who's there. So I can do a lot of things to this, right? Let's add a row effect. So now I say that we have a probability of ties across the row versus ties across the columns, or jointly. And it turns out that if I know a row effect, I know a column effect, right? That alone has now constrained the sample space a lot, that the probability mass is really falling. It's a high probability that this thing should be a 1, and in fact it is a 1, whereas this thing should not be a 1, and in fact it's not a 1, right? And so very simple volume effects of out degree and end degree on an asymmetric or a directed matrix like this can get you a long ways. It doesn't get you everywhere. So again, the bold ties in this case are the observed graphs, and so you can see in this case that these are real ties in the observed graph. That's a real tie, but my model, based just on volume effects, don't do enough to make those high probability ties. So we will often then add some other feature, right? So in this case, I've just magically called it dyadic similarity because I've made up this example. And the dyadic simile is something that we think socially predicts the likelihood of a tie there. And so in that case, because I built this as a toy example, it did a nice job of hitting it, but it also never hits perfectly, right? And so you're still going to have cases where the model doesn't fit and cases where it predicts ties that aren't there. So that's fine, right? Many people will argue that in fact those ties could well be mistakes. If your theory is good, if you understand the social process and you generate Q here as something that's socially meaningful in your setting, then the fact that I randomly see a tie that shouldn't have predicted to the model is kind of interesting. You might ask yourself, well, why did that tie there? Well, where did it come from? But on average, in repeated samples, this graph is really close to the graph that we would predict from the probability set. That's the thinking anyway. And so these models are, in fact, where we end up when we ask this modeling class called exponential random graph models. And so substantively, this approach asks whether the graph in question is an element of the class of all random graphs with the given known elements. And so all the elements in this set are fixed. And so in this case, we have a simple 4-parameter model, and those 4 parameters are an exponential family that predicts the probability of this set. So now that was the reason I say you don't do this is because actually fitting a logit to this is violating a bunch of the assumptions of the thing, and people get their hair all out of water. But so don't do that. So instead, we do the right thing. And the right thing, and the reason that it's wrong, is because you need to have a proper probability where all the elements sum to 1. And so the model is set up like this. The question is, what's the probability that the graph I've observed is an element of the class of all possible graphs of this given class? And that class is defined by an exponential function of some set of graph statistics times coefficients normalized by a constant. Right? Now that's all it is. Now these graph statistics would be the in degree on the columns, the out degree on the rows. Those would be your row and column effects. Or it could be the dyadic similarity, or it could be homophily on race, or it could be a whole series of different things. The real bugger is that K there, that little normalizing kappa of theta there, is that thing is unknowable on graphs that are of any particular size. And so by and large, it's really hard to come up with a normalizing constant in the form that you have here. But some really clever folks came up with this notion that it turns out that if you do a little bit of clever algebra and you think, well, I can figure out what this model looks like if I condition it on each individual cell in turn, and I hold that cell as either fixed or not, then it turns out that this whole thing that we care about is a function of the difference in the graph statistics, given that the tie is there or absent for all possible ties in the network. And so if you go through and for all possible dyads, do this little funky calculation where you take the graph statistic, calculate it with the tie forced to be present, calculate it with the tie forced to be absent, take that difference, that now becomes your independent variable. And when you do that, magically your normalizing constant disappears because they're on both sides of that feature. That's kind of fun because that allows us then to turn this into a logit model. And so when you have that, in theory, you can make this thing work. And so the steps in doing this process are that you have to specify the model, you have to fit the model, you have to make sure your model actually converged. And if you didn't, right, so if your fit is not good, you re-specify the model, you keep doing this until you get it right, and then you publish your paper, you get tenure, and you go on to life and success. Now, please.
So is the whole purpose of this just for testing your significance of your
Yes. So it is for testing the significance of your predicted variables, in the sense that if I add a variable to the model that has no effect on fit, then that variable has no social relevance to the setting, is the thing. Yeah. Exponential random graph model. Okay. It is the class of all of these models. So the exponential random graph, so this is an exponential family of models. And so it's the exponential random, the fact that x is a graph, and this is a random probability, so that's where the random graph probability. So this is the exponential family of random graph models because we're building it through. Very much. That's the beauty of this, yes.
It's actually a word that's referring to a group of things.
Yes. No, that's great. This is absolutely right. And you're going to see, like, after all this architecture, when we get done at the end of the day, we're running a logit model. So, which we know, we understand, right? So it's what all of us do, like, every day. But even the distributional assumptions are not so different. It's the way you construct the independent variables that is a little bit different. And it turns out there are two different classes of these ways we construct these variables. So that's what we're. No, the ergom, all of them are ergoms. It's just that some of the variables you construct exactly like you would construct in a logit model. These are known as dyadic independent variables, and others you have to construct to figure out things that are dyadically dependent. So the score that I have depends on the score that you have, and that's where the complication comes in. All right, so we have these models. Now, these models end up looking like a logit model. So we're going to say the probability of a tie is a function of a probability of features of the dyad, features of the subgroup, and features of the graph. And so we have a whole series of things that the probability of a tie depends on. And it turns out that there are a huge number of these z statistics that you could possibly calculate. I'm not going to go through most of them. In fact, I'm going to barely touch the tip of the iceberg of what kind of variables these could be. But the good news is at least since 2023, they now have this wonderful table that lets you go through and figure out what kind of term is in each of these models. And so it's there, it's part of the ergom cross-reference table, and you can look up for each kind of graph you have. But the standard kind of parameters that we fit in this sort of our world that we play with, so we tend to have homophily features, and so these are characteristics that you might say are usually done with either a node match or a node distance feature, depending on whether it's a quantitative or qualitative number. And so if you want to say, if you want to know whether or not race or grade or gender conditions the probability of observing your graph, you would say node match race, node match gender, node match grade, right? So these kinds of features are added to the model. We might also have this notion that we think that a friend of a friend should become a friend, and my friend of my enemy should be my enemy. And so that's a social balance process. And a social balance process you would estimate in this language using a transitivity term. Don't use a transitivity term. Logically, you would think you should. Turns out it'll crash. Instead, we use something like a transitivity term, which is known as a GWESP term, which I'll explain in a bit. And there's lots of these. So we might have other kinds of clustering features or particular path structures. Craig was nice to point out the romantic network. We had a theory there that said that people wouldn't form 4 cycles, so we can put a 4-cycle term in the model, and we should get a negative coefficient on that term. And in fact, you do. So that's the kind of process that you can play with. So I'm going to walk through an example, and this is the example that's in the .r file and the ergom data. It's a small school sample. It's a network of 71 nodes that have all 12 grades. So it's a really small rural school in eastern Pennsylvania. And it's nice because it gives you a chance to see what the network looks like and how these models are fit. So this is the what the network itself looks like. And I'm just going to go ahead. I'm not going to do that. If you want to run it yourself, go and have a look. It's in the code. I'm going to go ahead and just go through the slides to describe it now. So the, oh, are you kidding me? There we go. So the way you specify these models, once you read in the data, and it's your standard sort of StatNet object, you read in the model and you specify it as an ergom, where you take the school network in this case, which is what I named that graph, and I say it's a function of an edges parameter. So that's just an intercept-only model. So if you do that and you go through and you look at the resulting graph, you'll see that I get a strongly negative edges parameter, minus 2.72 in this case. That is a non-interpretable number by itself, except that if you convert it to a probability, you get the exact same probability of the graph itself. So that's all it's doing. So this is literally that first model I showed you of an intercept-only model. This, if you wanted to generate Erdos random graphs with a known density, you could just do this. You could flip it around. Now the beauty of these models is once you've estimated the model in ergom, you go throughout, you can then ask whether or not this model fits and you can simulate from the model. So I know the ergom model doesn't fit, so I'm not going to bother describing that to you. But instead, I'm going to define a variable on the network that's in degree, a variable on the network that's the out degree, and I'm going to re-estimate a new model, which is the random graph, so the school is a function now of the edges, plus an attractiveness parameter for in degree, and an expansiveness parameter for out degree. So this is a column effect. So the incoming ties is a column effect. I'm going to say the probability of a tie should increase the more my in degree increases, and it should increase the more ties I send. I then ask the model to summarize, I get a good enough a fit, and so forth. And so this is what that model looks like. And as you expect, we see that the higher my in degree, the higher the likelihood that I receive a tie. The higher my out degree, the higher the likelihood I receive a tie. I send a tie, excuse me. And so these are statistically significant. And these statistical significance are determined by an MC kind of change or process that are not worth going into here, but that's the model. So you can see the score that comes through on this set. Now, what you'd like to know is maybe that's sufficient. Maybe that's all that's going on in my graph is sender effects and receiver effects. And if that's the case, I can figure that out by doing these goodness of fit plots or simulating a network from the model. And in this case, that's what this little line does right here. It says, let's simulate from model one observation. And if I wanted to simulate 1,000 observations, I would just trade one with 1,000, but I was lazy, so I only wanted one. And so I look at it. And so I just plot this simulated network now, and you can see that this thing doesn't match that structure. Right? The observed structure we had those really tight clusters. This one doesn't have that. There must be something else going on. So let's keep building the model. Here's another version, right? So now from model 3, I've skipped a couple models at this point, so I'm sort of going through this relatively quickly. And so in model 3 now, I said let's have my edges parameter. Let's have my in degree parameter, my out degree parameter. And now I'm going to add a whole series of homophily parameters. So I'm going to say these kids match on grade, they match on gender, they match on smoking behavior, because I'm sure it's like Craig's network. And then I also say that there's reciprocity in the network. So you can't let these ties just fly all over the place. If you nominate me, I nominate you. And so let's have a look at that model. We run that model. It goes through and it does its thing. One of the things you'll notice if you actually run the code that's on the server is that the prior models went really fast. That's because they only had independence features. The mutuality term, that term can't be well estimated with the logit model. You have to estimate that through this resampling chain process. And that means the whole model has to be estimated by this MC-MC chain. And so the convergence time is going to be higher, a lot higher, actually. And so if we do that, we see that all of these features seem to condition the graph. That you have a higher probability of a graph depending on these various features. This would tell us our grade homophily, right? In this case, it's 2.5. Oh, wrong up. And yeah, so then if I go through and I'm on the same kind of model. I do. No, I added, so yeah, I'm going a little fast. I'm done at oh yeah, they're all the same. So they're all the same. So we have until 1. Okay. Because we eat lunch at 1. All right. So So here I'm just running them. I'm going to show you what these models look like in real time, just a little bit. So there's running all the models above. There we go. So that's now giving us this final set of models. Come on, keep going. There. So this is what you're going to see when you see the models run. And so when it's doing any of the actual sort of more difficult estimations, it's doing a series of convergent steps. And it's trying to find the best, you tell it some maximum number of total MC-MC chains that you want to run, and each process that's going to re-estimate and resample and so forth. And finally it gets to the end when it converges at the set. And in this particular case, I ended with this model that I just told you about. Right, this model 3. So we'll see if we get the same answer. One thing that you will notice is that sometimes the coefficients will be slightly different, so it's a stochastic process. In this case, I had 0.57 for that, and yeah. So you'll notice in this case, right, for example, the mutuality effect that I estimated, the other day when I ran this was 2.3. Here it's now 2.34. So they will always vary just a little bit if you really care about something to the second decimal point, increase your iteration set. But the model looks like this. And when you do these goodness of fit statistics, this is why I wanted to show this one first. What I'm doing is we're going to take this model object and these coefficients, and we're going to simulate 100 different networks from this distribution defined by this equation. And once that gets done, we can plot it. And the way the plot works is that for each statistic that you do, and there's a set of default statistics that they come up with, but you can specify any graph statistic that you could put in the right-hand side of the equation you can test against. But the standard rule is you want to test against a graph statistic that you didn't put into the model. Because definitionally, you better fit the parameters you put in the model because that's how the model was built. And so I'll show you that in a second. And so in this case, the observed network, if you look at the distance matrix, the geographic distance between all pairs of networks, about 5% of the nodes are one step from each other, about 15% of the nodes are 2 steps, about 18% or so are 3 steps, and that's the distribution of distances in the networks, and some set of nodes are isolated. And then if you look at the box plots, that's what the model would simulate. And so the model thinks that as the class of graphs defined by this model would predict a distance distribution that is somewhere in this range. And so what you want is this black line to be inside that set. That would say that this model captures the distance distribution in the network. Now, it's also, in this case, you see I don't do a particularly good job. I haven't fit the number of isolates, so my number of isolates is lower than the number predicted by this graph. And it looks like the random graph has generally a shorter distance distribution than mine does. So the actual observed graph is spread out further. Go ahead. I can't talk through that. So there's Pavel and Mark have spent untold hours figuring out the optimal solution. I think of it because the original one was a very simple Monte Carlo chain that was literally the coin flip on all possible edges in the graph thousands and thousands of times. They've now come up with a much faster method, orders of magnitude faster, which is doing something like I think you just described, but I don't know which. But look, if you go through here, so there's other statistics that are often of interest. This is the edgewise shared partners, which is the number of times 2 connected nodes share a third. This is what the distribution looks like in the real graph, and this is the distribution in the model. It's close, but it's not very good. In this case, you can look at the n-degree distribution. You can see we didn't fit that particularly well. It's kind of in the area, but you'd like to see a bit of a drop here at 5 that's not there, that we can see in the real graph. And the same thing when you go over here. So this is the out-degree distribution. Now, I'm asking it to fit, I fit a single parameter to the in degree and out degree, a linear parameter. So this model has to kind of have a smooth distribution over the distance by the way it's defined. You can put different functional forms to something like in degree or out degree to make it fit a little better. Now, this is why I say we don't fit to the model in the statistics, right? So these are the statistics that are in the model. I do a great job, right? I fit those almost perfectly. And the only reason it's not perfect is because there's a little bit of stochastic noise in the element. This is the only reason you have this plot is to make sure your model converged. If this isn't true, you have to go back and fix the convergence in your model because something's screwed up. So I was trying to figure out, so what I like to do is do these features, these plots, just like I said as well. But then because I find, especially for small networks, the sociogram is more intuitive. I like to simulate one of the graphs from the network and then plot that network, and then I can see what it looks like, just like I did a minute ago. So this is the kind of graph you see when that happens. So I was looking at this model, and this model is actually a pain in the ass to fit, to be honest with you. If you go through and do lots of things, it never really fits quite well. And I realized that part of the issue is that we were just matching on grade. We said if you and I are the same grade, there's a probability we should be a tie. But it's also the case that if we're in adjacent grades, we should be more likely to meet than when we're distance grades. So 7th graders are more likely to meet with 9th graders than they are with seniors. So we have both a matching qualitative, same grade or not, and a gradient on the distance of grade. And so when you run that model, we'll let that go. You can see, now all of these things at most 60, all of those are things that you can change as you go on and decide to do it. The model goes, it goes for a while. And it's taking time now because it's doing this search process that you have to try to find the best fit to the model. Then figures out that, the model. And as you might expect, it is the case that the further we are in the grade space, right, we're less likely to be tied to each other. And so then, if I added an H there, this is why you don't do things live. So again, if I just do that, and run the goodness of fit again, you can see I still don't quite get the geodesic distribution particularly well. I mean, it's not awful. It's a little better than it was, but it's too far. I get the edgewise shared partners pretty well. My in degrees start doing a little better. Out degree in this particular case wasn't as great as it could have been. But qualitatively, if I just simulate one of the graphs and then plot it, you can see I'm getting a lot closer. Right? So now I'm actually starting to see this segregation of the freshmen on one side, the seniors on the other, that wasn't there before. And so that process allows you to see what's going on. Now, part of the reason that this model is not fitting, and particularly the geographic distance feature, is that in a random graph, there's no closed triads, or there's very few closed triads. And so it ends up being the case that when I have a choice to send a tie between two people, of this case, of the same in degree, the same race, the same grade, or the same smoking status, I'll just pick them at random. But if one of them is tied to my friend, I should pick that one over the other, and that would lower the overall sort of set of ties, and it should sort of move all those geodesics back into this clustering set, which then should create greater distance in the network. So in order to get that, you need to add some element of a triadic closure. I'm going to point out, just because it's here, I've been fitting a homogeneous grade feature. You can say that there's a heterogeneous grade feature. That's what this diff equals t function is. So I can say that we're all going to have some matching on grade, but it might be stronger for seniors than it is for freshmen. So that's what the difference feature says. There is, in fact, a little differential homophily in this graph, but not particularly well. Now, if you go into this, you'll see I have a note here that says I tried a bucket load of things to try to get this model to fit. I built this off a graph that Jeff built earlier. And at the end of the day, it took a long time for this model to go. So I'm going to show you a little bit about how this thing ended up getting fit in the end. And so what I ended up adding was the same things we had before, so our intercept term, our matching terms. It turned out that the differential matching on grade didn't seem to make a huge difference, so I shot it off here just to get some convergence things happening. I have some attractiveness of smokers, some expansiveness of smokers. Again, the gradient on grade, I fixed the number of out-degree isolates, so the people that sent no ties, I just put a parameter in for them. And then I have this triad feature. And what this does, the triad feature says, I'm going to go and run it, and I'm going to explain it, because you're going to see it's going to take a while for this model to run. If it runs. And so what it's doing now is trying to fit all those things simultaneously. I've set up some things to try to help it along a little bit, but it's going to keep going as we go here. And I'm going to let that go in the background, and we'll come back to it if it converges. So if you go through and look at this model, as we go through for the better fit, each of these models is a little bit better. So this is the model that's ultimately, I just said, to fit. I'm just trying to run right now. And you can see that the geodesic distribution, now starts to fit. And that's because by adding closed triads, I've essentially extended the distribution of distance in the graph. So that's nice. But you'll notice I didn't put transitivity in, I put in GWESP. So what is GWESP? So GWESP is an acronym for the geometrically weighted edgewise shared partial. So what does geometrically weighted mean? Intuitively, our theory is that transitive triads are good. That if A is tied to B and B is tied to C, then A should also be tied to C. And so if you say, I'm going to have a positive coefficient on the number of triangles in a general linear model, what I'm implying is something that looks like this. That is, what I'm implying is that the more of this I have, if it's good to have some closed triads, it's much better to have lots of closed triads. And what happens, we discovered over the course of a long period of sort of field explorations of these models, is that you end up with a snowballing effect. That once you add something like a transitive triad feature, that because the model thinks that the marginal return to each additionally closed triad is equivalent, it's just going to keep adding closed triads. And so what you're fundamentally going to get are graphs that have complete cliques, everybody connected to everyone else, or completely empty. And the mean of that will be the number of closed triads you have in the graph as a whole. And so the model will fit in the global sense of the expected value of the number of triads is right, but on any given draw from the probability distribution, you either got a complete network or an empty network, and it's a mess. That's known as a degenerate graph. And it turns out that it's a problem with model specification. It's because, in fact, we don't care. It's not true in social life that networks, if you have closed triads, you get more and more and more closed triads. There's diminishing marginal returns. And that's what geometrically weighted edgewise shared partial means. It means that for my really close ties, for the people that matter the most, that I have a high probability of tied to, I'm going to be friends with them. But I can't be friends with all of my friends' friends. There's some limit at which this happens. And so there's a geometric decline in this as we move forward. And so that's all the GW means. So GW is geometrically weighted. It turns out that weight, just like it did finally finish. That's great. It didn't finish. I was running this last night. It didn't finish. I had to stop it. I was kind of hoping I could show you what that looks like. But so in this particular model, you'll notice I have a couple of other parameters. And so there's a decay function, and you ask whether or not that's fixed or not. What that decay function is the speed at which this thing curves and flattens out. So I can let that thing be close to linear, or I can stomp on it really quickly, right? And what you would like to do is let the model figure that out for you. But if you say that fixed equals false and you let it figure it out, it takes forever for the damn thing to converge. And so my experience has been pick a number that's reasonable, somewhere between like 0.2 and 0.6, and it usually works just fine. If you really find I know that's ad hoc and it's like you hate it, but it works. And it just doesn't matter because you can either put the weight on the coefficient for the whole term, or you can put the weight on the coefficient for the decay parameter. The two are going to balance each other out eventually, and so it's fine to do one or the other. That's effectively what you're doing there. So when you get that done, let's do a summary of this model. You'll see that in this particular case, that there is a positive return to closed triads. So it's the case then that as for each additional triad up into a diminishing return, which is defined by that, you end up with a slightly higher likelihood of having closed triads. if I then go into the model, set the right one, and say, let's just give me a plot of my goodness of fit. Okay, I have this already printed out. I don't have to run it again. Well, in the wrong direction. Told you I should know how to use PowerPoint by now. So this is what that model looks like that I just estimated. And so it fits reasonably well, right? Like I said, we've matched the degree distributions. The distance distribution now is what I want. That seems to be fine. And then qualitatively, it looks okay. This particular draw from the distribution, it's, I have a few more isolates, and my gray nodes are kind of spread all over the place. So my guess is there is some differential homophily there that I'd want to fit a little bit better if I really cared about that. But to me, this seems to work pretty well. Substantively, you read this table the same way you would any other logit model, right? So this is your hypothesis test. You say, my hypothesis was that there would be an age gradient to grade, and that people who smoked there'd be homophily on smoking. And in fact, this model fits best if I have a term for smoking on node matching, and that suggests that these kids are sorting on smoking, even net of sorting on grade, gender, and their distance in grade. And so there's leftover homophily on smoking, net of these other features, that adds to the fit of this graph. And so that's how you would interpret that as the hypothesis testing side. Now, there are a couple of things that can go wrong with this. There are a lot of things. I also often will test triad distributions and things like this just to get a sense of higher order features that seem to match. But one of the things that will go wrong often is with these models, and particularly the more complicated they get, is that you'll be sitting here, you'll be running your model, it'll be going fine, and it'll say, I'm on iteration, usually it's way up here, it'll be on iteration 3 of at most 60, iteration 4 of at most 60, iteration 4 of at most 60, iteration 4 of, it'll sit there forever. It's because it's got stuck. And so these things will get stuck, and it won't necessarily pop you out. Sometimes it does, it has some nice error handling in there to get stopped. And so your best solution, if you sit there, if you've noticed that the time to the next iteration as you're watching it is a lot longer than the time to the prior iteration, hit that stop button up there, start it over and try again. That's the first thing. If it fails twice, you have a badly specified model, you need to do something different. And so you need to go in and try a new set of parameters. But it turns out that one of the things that has made this thing wrong is that there is an easier way to fit the model, which is use this thing called stochastic approximation as the method that you're fitting. And this is a different optimization method than the standard chain method that they're using. And when you run this, it almost always fits, and it goes a lot faster, right? And so the trade-off, there's no free lunch, right? And so the trade-off here is that you're going to get somewhat less precise estimates. So you're going to have a little more noise in the model. But the trade-off, particularly if you're doing simulations or other kinds of large-scale models, here I added the differential homophily back in, it's just so much faster. And A, it's faster, and B, it's more robust. It doesn't just hang there forever in the way a lot of these other models do. So again, in this case now, I've added a couple other things I should have told you about them. So this is differential. This is what differential homophily by grade looks like. So now you'll notice we have a different coefficient for each grade. Most of them are essentially the same, except for the seniors. So the seniors are much more likely to be homophilous with each other than are the other grades. It turns out in the new specifications, what I could do is say have two classes, collapse 7 through 11 and fit 12 separately. So you can go back and forth and fit that. Go ahead. Yes, that's a very good point. And yes, there's all kinds of issues with that because you're only fitting to one observed case. Right? So if you're fitting in one observed case, you can tune it to be exactly right. And so this is why I like having data where you have multiple schools, and so you could do just that. The one big asterisk here is that this convergence issues get to be a real pain in the ass across lots of different schools. And so you might find that one model just won't fit in all the schools, and that the model that will fit in all the schools fits none of them well. And so that's the trade-off that So between making the model really sort of tailored to a given setting versus not, is that the models that will fit are often not the best models, and the models that fit nicely in one setting might not fit in another. And so there's a lot of work you have to go through to make sure that those things, that just doesn't happen. Okay. I've noticed a couple other features here. I added, these are opposite features. So this is the geometrically weighted edgewise shared partner. That's the likelihood that we're closing triads. The geometrically weighted non-shared partners says that I'm avoiding triads that are open. And so we're simultaneously sort of getting a double whammy here of closing triads when I have the opportunity and avoiding making ties that would create an open triad. So it's a nice feature of being able to do both of those things. So there are multiple other ways you can do this. Let me go back a slideshow from the current slide. Back to where I was. So that was the model I just showed you. Now it turns out that one of the problems with those kinds of models, and it's not just an overfitting problem, it's just a complexity problem. Oh, sorry, Tom.
So what was just to understand the context here? So you was finding a model that so decided again just this out with the exact same graph that you observed in the school, right? So you make the distribution so tight, you have so many parameters that you just always get the same number.
Right.
So what's the goal? You want to make a set of networks which are similar to the one that you observed in school, but how similar should they be? Right?
Yeah. So that you want them to be, that's a theory question. It's like what, so the model, for most of us in the context of social sciences, the goal is to figure out whether or not the homophily features or the social balance features are doing any work in terms of conditioning that graph. And so we don't actually care about fitting it exactly, but we don't want it to be wildly wrong. And so the distance between wildly wrong and fitting exactly is a judgment call. And it's entirely up to what people are doing. Now, there's one element where that's not true. And that's when you use these models. These models are currently, I'm estimating them on a complete graph. Where they're really valuable is when you're measuring them on samples of graphs, where I have lots of little chunks of networks, and I want to simulate what the whole network looks like. Then you want to do a pretty good job of fitting what your observed stats look like so that you can interpolate beyond those stats to a wider network. And so there, the goal is often, for example, in our village networks with the work with Charlie Nunn, there we've sampled about half the people in the village. And we'd like to know what the disease diffusion risk looks like for the village as a whole. So we fit a model on half the network and then extend it by simulating to the rest of the network. So we upsize the network and then change it out. And there, what you want to do is simulate networks that you think are plausible representations of the networks that you sampled. Now, they might still be overfit. It's still a judgment question, but that would be the goal in that case. Does that help a little bit? A little bit, yeah. So the reason you would do it, now, one thing that you would often do, or not often do, but I think that I recommend doing, is that if you really only care about testing whether or not there's homophily on some observable. So I have some theory that kids who smoke hang out with each other. It's not a particularly deep theory, or that there's no match by grades. Then oftentimes your life is made a lot easier by just fitting one of these latent space models to it. Let that take up all of that sort of idiosyncrasy with the model, and then only test the thing that you care about. Right? So I'm going to let the model fit with the latent space model in this case, and then I'm going to see whether or not there's, after I've given the latent space everything it can, is there anything left over for grade versus sex. And in this case, it turns out, I'll go back up, I lost my coefficient. It turns out that the grade still matters, right? There's still additional variance left over in the clustering on grade that the latent space can't capture, but whatever's going on with smoking is well captured by the latent space. So there's nothing else left over in terms of the homophily of that. Now, what does that mean? It might mean that the latent space, that one of your z variables is smoking, and you don't know it, so that's the trade-off there. But if you have a strong signal from smoking, it should still be there. It's above and beyond whatever's simple. And again, you can also go back and resimulate out of the latent space models. For some reason, the network object that's simulated out of the latent space model drops all the attributes. So you have to re-append the attributes if you want to color by it. But it's the same kind of process in fitting the models. Please.
So you both said this initial recommendation also the fact that you can reflect on the religious issue very nicely. So in some of the relations you see just from the assumptions, the basic assumption of the model. The question is, there are some general arguments that sort of methods that come in nature sort of should be of this exponential random graph type, or can you like get more just recommend any sort of dimensional networks or
So there are some, Carter has a really nice paper that came out just a couple years ago where he goes through and he asks a question I think similar to this, which is there are some underlying functional forms built into the exponential random graph model and some of the functions of the shape of that form that he's able to adjust. And when you do that, you do get different results. And so there are different ways you can tune to where you're getting at. And he's making the case that these models, sort of if left to their own device, are making a sort of hidden assumptions about the structure of the underlying graph. I think practically, for most of the work that people in this room want to do, those assumptions don't matter that much because once you add the coefficients back in, you can get to the same spot nicely, and it has a relatively nice test. But I think that if I were using this model to fit a protein structure or something like that, that I might want to think more carefully about how that's generated. David, do you have a reaction to that? I know you've thought about these. Okay. So that's the way these models end up getting fit. There are a few things to keep in mind. The models are very sensitive to model specification, so you do have to spend a fair amount of time thinking about that. Complicated models are difficult to fit, right? And so you need to have some. The package was built, I think, with a set of defaults that are not bad, and I think there's good reasons. Like Carter and I were emailing here just a couple days ago about why this is the case. But if you ask guys, I said, look, I have to give these people some advice on what to set in terms of the burn-in and the number of iterations and such to run. And this is his advice. This is literally a direct quote. I should have put a quotation mark out of it. But essentially, the default number of iterations for the chain size and the sampling rates is much too small for most of the graphs that we're fitting. And so if you were to take that same graph I was running, which I set to have a burn-in and a chain size of about 2,000 to 3,000, you could easily set it to 16,000, or if you take the really high end, over 1 million, right? So if most of us are not patient enough to wait for that kind of process, which is why I like the stochastic approximation method. But if you find that your model's just not converging well, or you're getting MC-MC chain plots, diagnostics that look really non-stochastic, then first thing to do is to make sure your model looks, is substantively reasonable. And if it's not substantively reasonable, if there's something that obvious like grade distance in addition to grade category you should add, do that. But once you've done that, I'd probably up your iteration size. Your iterations are probably too low. All right. So all of this that I've discussed thus far have been on the analogy of a logit model, and we've been working with binary graphs. Turns out that that's not a constraint. There's lots of other sorts of features that these models have now been generalized to. So the first is dynamics. So we now have dynamic networks, which are tergums or temporal ergums, or sturgums, which are separal temporal ergums. A separal temporal ergum means you have one set of parameters for forming ties and another set of parameters for deleting ties. You have what are known as a relational event models, which are ergum-like but in continuous time, so you don't have a fixed or very narrow discrete time. Scott Duxbury, who's talking this afternoon, is going to give us an overview of all of these models, and he has a great new book on this set of features. There's also a whole series of extensions to different types of networks. So we have bipartite, we have models now for bipartite networks, for ego networks, for value ties, for rank ties, for multiple classes of networks. So if you have multiple schools in your data set, for example, and for multi-relational networks. So there are now specialized models for each of these features. There are Bayesian versions of these models. And so there's a Burgum package out there now for fitting the models and then doing posterior estimation on these models. There's a whole series of features on that. More practical is that there are a series of new syntax features built into the model. The new 4.x versions of Ergom have a whole series of on-the-fly specifications that you can do to the model that makes it easier to specify models that we might care about. And so you can do things with character searches, and if you're a tidyverse kind of person, you can build all of the functional passing that you would do in tidyverse. You can do in the formula object itself. You can also do these things where you now add curves or other kinds of functional forms to the model as a specification. So if you want to have a peak grade, for example, at which you think that ties would form, then you can add that as a say a polynomial to the graph, which you do in normal grades. You can also, whoa, wrong graph. There we are. You can filter things, right? So you can sort of decide, I'm going to only apply my graph to one thing or another. I like this new S set of operators, these subgraph operators, which effectively allow you to fit different parameters to different parts of the model. So I could say that I have a general set for everyone, but then for some subgraph of the model, I allow it, the parameters within that group, to be slightly different. And so that allows you to essentially it removes what's known as the homogeneity assumption in these models. So right now it assumes that everyone who's in the same parameter set has the same, or the same coefficient, sorry, the same covariate set has the same parameter effect. And this allows you to have a little bit of variance in that kind of set. You can also add, again, there we go. You can add interaction terms. And so I can say that the probability of forming a tie based on my grade is conditional on my sex. And so you can have interaction terms by categories. These have to be dyadic independent features. You can't do this with the triadic effects or other kinds of mutual effects. But for most of the kinds of questions we care about in terms of interaction terms, these can be quite useful to think about that. All right, so those are ergoms. Questions? Any other thoughts on those before we move on to flipping it now and thinking about the network as a dependent variable? And I'm going to give you all of like 10 minutes on that before I go on to the next. Please? Is that a question? All right. Awesome. Okay. So oftentimes we're interested in using a network to predict a different kind of an outcome. And one element that, one way that people have done this is to look at this as a somewhat old-fashioned model, but I think it can still be quite useful, which is a quadratic assignment procedure. And what QAP does is it says, I want to know whether or not a one adjacency matrix correlates with another. So for example, do I tell secrets to the people I go to dinner with? So I could imagine I've collected these different kinds of relationships, and I want to know whether or not there's a correlation between my secrets network and my hang out and drink beers network. And so we can do that. We can and I've just used an example here, which is the Florentine Business Network. So we have two types of relations on these people. We have a marriage network and a business network, and so there's a tie on the one hand if one family married into the other family, and the second case is whether they did business together. And it turns out, of course, that these things are correlated, that in this setting, the correlation is about 0.37. Is that big or little? I don't know, it seems kind of big to me. And so we can figure out that by doing a permutation test. And the way this works, if you don't know what permutation tests are, is that once you've constructed sort of this correlation coefficient, you then reconstruct the data by randomly shuffling the rows and columns of one of the matrices. So this is another way algorithmically of saying what would happen if this association were generated only to chance, but we held constant the volume features of the network. So everyone who has out degree 8 still has out degree 8, but their association between business and marriage has been broken. So you've algorithmically taken that association and randomized it. And by the process of doing that, it allows you to generate a new correlation under this randomization assumption, under the assumption where there is known to be no relation between your two. And you can ask what kind of value you get. And so in this case, if you do that over and over and over again, I did it 500 times of a permutation test. You can say, let's randomly sort the network, take the correlation. On average, you get a correlation pretty close to 0. In that case, it's what you might expect from other sides. But distribution of that over the sampling set is going to depend on the structure of the data. And so in this case, you can see that our observed 0.37 is far outside the bounds of what you would expect by random chances alone. So that's the way of doing this. And so this is a standard way of testing whether or not a network affects similarity of behavior in dyadic models. And so if I want to say whether or not, Craig and I both smoke, or we both, think that Trump is a jerk or whatever, so we have a whole series of different things that are related to us as a function of whether we've written a book together or not, right? Because that's a very big process in the political polarization world, is whether or not authors agree with each other. And so we could test that. That's my test to see if you're really asleep or not, is even my bad jokes are ignored. So then I know. If I'm not even getting a groan, then I know that you really are asleep. But anyway, you can test these models, and it's a nice way to do it in terms of similarity and to get at it without a lot of the assumptions of a standard linear model or the standard regression style linear model. It makes different assumptions. It makes assumptions that this random breaking of the permutation set is a reasonable null that is happening. And you can make good arguments for why that's not the case. There's been a lot of ink spilled on how to do these models well. In my opinion, UCINet, which is an old-fashioned desktop specialized program, is still one of the best collections of tools for doing this kind of models. So if you're interested in thinking about that, I encourage you to go find some of their tools and have a look at it. That said, the one tool to rule them all, we have built a multiple relation QAP tool into IdeaNet, and so that model is in there. The nice thing about it, Gabe, I know that I bugged Gabe last night to prep a demo of it, and now I'm going to take too much time and not let him show it. So, so I apologize for that. What's that?
The scripts for MRQAP, like the vignette in the Google Drive.
Great. So if you want to do it on your own, it's in there. You can see it. But what's nice about it is that you can take, the tool has a series of functions that allow you to construct the data in the way it needs to be for these models to work. And that's where a bunch of the work is at in these kinds of models, because what you have to do is you have to convert your adjacency matrix or your similarity matrix into a series of dyadic data sets. And the process of doing that is kind of a pain in the ass, and then you have to specify whether or not it's a difference or an absolute value of a difference or a matching. Or so there's all kinds of things you have to do to get these things to align right, which is no different than you have to do in any kind of data prep. But we've done a lot of that for you, and that's the advantage of it. And so it's built into the model set. All right. Questions, thoughts, comments, concerns? I know that was fast. I know it was at probably too high a level, and I can see you're sleeping, so that's why I'm going to stop. All right, stand up, walk around, say hi to each other. Lunch is here. Grab some food. Again, use both sides of the table so we can get through. And then at about 1 o'clock, so about 10 minutes, 15 minutes or so, we will start with, no, we have a break for lunch. I take that break. Sorry, I forget how we're doing this now. So go to lunch. The sun's actually shining for your first time in North Carolina. Go out and find a cicada. and has
Still live.
literally written the book on network interventions and has a second book in the works on the same topic. So it really is very few people that we could have at a Social Networks in Health conference who knows as much about using networks to influence health as opposed to just doing it from the outside. So it's really a treat to have you here again, Tom. Thank you so much.
Thank you, Jim, and thank you for the invitation. Thank you all for being here. I'm delighted to be here. I enjoy doing this. I grew up in Charlottesville, Virginia, which is not too far from here, so it's nice to be back on the East Coast. Yeah, my email address is here. Please feel free to email me should you have any follow-up questions, concerns, or requests. This is the outline of the talk I'm going to give you. I'm going to follow up a little bit on what Craig talked about this morning in terms of network influences and behavior, and then reserve most of the time talking about networks for interventions and program implementation. And network influences on behavior, I don't need to tell you, incredibly important. That's why you're here. That's what you want to know. And when I think about network influences on behavior, I think of this little stylized egocentric network, a person that's connected to 6 others. And the first people to actually estimate exposure models as influences on behavior was Rogers and Kincaid using Bill Richards' program. And basically the idea is as your friends do something, you're more likely to do something. Network exposure being that driver for behavior change. I call it the workhorse for diffusion studies. And then we also know that the other thing that happens, of course, as your network fills with adopters, it can also end up with people you perceive to be users regardless of whether they're users or not, right? So those perceived behaviors by your alters influence behavior more than their actual self-reported behavior. And we have about 3 or 4 studies that we've done in the tobacco world and in the contraceptive world that have demonstrated that. We also know these so-called Semalian ties, right? The ties that are between alters that connect people to each other have stronger influences on ego than either individual would by themselves because the influences become reinforcing. And then, of course, we have personal network density. A person in a network whose alters are all connected to one another is going to have stronger influences on their behavior than one in which those ties reach out into the network, the so-called constraint measure that you've already heard somewhat about. And then there's tie strength, right? There's a lot of people that make a lot of noise over the strength of weak ties. Great article, great scholar, great line of work. But I argue that tie strength matters a lot for the more consequential the behavior. So the bigger decision I'm going to make, the more important I'm going to rely on strong ties rather than weak ties. And Granovetter makes the point that weak ties are very good for information flow, not necessarily for behavioral influence. And then, of course, we can look at indirect ties, right? And there's a lot of debate on whether or not indirect ties can influence ego. I argued as far back as my 1995 book on network models of diffusion of innovations that you could go out 2 steps. That's what we modeled. And we modeled the influence of indirect ties inversely to their distance from ego. So somebody 2 steps away would have their influence cut in half. And then, of course, whether or not the intermediaries need to be users or not to transmit that influence is an open question. Christakis and Fowler argued for 3 steps, and so I think it's an open research question and probably varies a lot depending on the application and the setting. We can also weight network influences by network indicators, right? So for example, in the adolescent context, you might think that popular students have stronger influences on others than non-popular students. And so we can calculate all of these different centrality metrics and all other kinds of individual metrics and use those as weights on personal network exposure. And then, of course, the insight and research track by Ron Burt to look at structural equivalence. Structural equivalence being a mechanism by which people influence one another, regardless of whether they're directly connected to each other. And of course, the mechanism that he argued for that is one of competition. You could imagine firms competing with one another. I like to argue that the minute McDonald's gave away little plastic toys, Burger King had to start doing something at the same time, right? There's competition. We model the behavior of those that occupy similar structural positions that we do. All right, and so the idea that you can have indirect influences and the idea that you can have structural equivalence influences means what you can also do is contract or expand that sphere of influence, right? So we can look only at direct ties or indirect ties or ties of ties of ties of ties, a flow matrix, if you will. When Ron Burt did his structural equivalence analysis on structural equivalence influences on the medical innovation data, he raised that structural equivalence matrix to successive powers to find the one that fit the data the best. So we can expand or contract that sphere of influence. And then, of course, my own discovery during my dissertation research was the notion of thresholds, right? Not everybody waits till everybody in their network does something before they're willing to do it. If we all did, nothing would ever diffuse. There have to be people in the system, in the community, that are willing to adopt behaviors when one or none of their partners do so, and others who wait until their network fills with adopters before they're willing to do so. I am a high threshold adopter. Why am I a high threshold adopter? Because I'm smart. Right? Why would I do something before everybody else does it? That's just plain old stupid. People that do that to me are crazy. But they like being early in their network to adopt. They like to get more information about it and then communicate that information to the people in their network. They're the ones that line up outside of the Apple store the minute a new phone's coming out, right? They want to see what the features are, and they do something I would never and have never done in my entire life, which is read the manual, right? This is what people hate me for, but they read the manual because they want to know what are the features that I'm getting in this new thing. And then here's a graph from the classic Korean family planning data set where you see you can graph people by whether they're early or late adopters, but also whether they're early or late relative to their network, right? So you can find people like number 11 or 20 that would normally be classified as innovative as early adopters, but yet they're actually waiting until everybody in their network adopts before they're willing to adopt. And we label these people over here, these late adopters, right? But they're late because where they are in the system, where they are in the communication network, makes them exposed to the innovation at a late time. And then, of course, online versus offline influences. There was a little bit of discussion about this earlier. The evidence seems to be that you can be influenced by those online, those computer-mediated communications. The magnitude of that influence is a lot less, but of course the number of contacts and communications you can have is a lot more. And then we can also weight exposures by joint participation in activities and events, the so-called bipartite or two-mode network. You know, we showed that kids who are friends that are also on the same sports team are more likely to be influenced by those friends than those that don't share a sports team, right? So you have that joint participation and identification. Then of course, you have attributes, right? Nodes are people too. They have attributes. They can be male or female, different ethnicities and whatnot. And communication theory has long argued that people are more likely to be influenced by homophilous ties than by heterophilous ones. So weighting it by that homophily can matter. And then finally, the last thing we can do, which is really cool, which I'll try to illustrate real quickly here. Here's a little stylized network of 8 nodes. The node labels are A through H. The time of adoption, in other words, the time when they adopted a new behavior, is listed there in the second column. If I reshape these data, so now each row is a person, each column is a time period, and what I'm illustrating here is that for person A, right, they are connected to 5 other individuals. 3 of those individuals adopted before A did, so their threshold is 60%. However, you'll notice that there's only one person who adopted at the time period immediately before A did. That's person B. And that is B's susceptibility. You are susceptible to the extent to which the people you're connected to adopt in the time period immediately before you do. And the converse of that is infectiousness, right? You're infectious to the extent to which people that are connected to you adopt immediately after you do. And so you can switch the direction of those arrows if you want, depending on the relation that you're looking at, but you can actually model explicitly susceptibility and influence through network diffusion models. So, and I'll just say we have a R library called NetDiffuser that makes doing all of those things as easy as toggling a switch, right? So earlier Jiten was talking about how he had done network analysis in SAS and then something else and then something else. And in fact, yes, I did my PhD dissertation writing code in SAS proc IML to estimate network diffusion models. Got to Hopkins, everybody there was using Gauss for network analysis. Great, rewrite everything in Gauss, wonderful. In the early 2000s, we get R. Now we rewrite everything in R. But fortunately, I think this is...
still runs.
Love it. So anyway, we have and we're still working on the package, but it does a lot of neat things very quickly and easily. So I like to say that's networks of behavior change, right? But what you're really more interested in, at least what I've become more interested in lately, is networks for behavior change, right? If networks are so important, how do we use them to improve our behavior change programs? And one paper we did back in 2015 was to think about social network analysis for program implementation. This has a very snappy acronym, which I like. I'm usually not too good at that, but we have it now. And the idea is basically quite simple, right? We have stages in the implementation process. These are well known. We took one of these frameworks and then talk about at each stage of the implementation process, what do we do from a network perspective to improve our programs? And the first step, of course, is a needs assessment, or so-called exploration. Then we design programs, we implement them, and then we monitor them. And so just thinking about networks during the exploration stage helps us think about, is there a network that we can work with? What's the network look like? What positions are the people in that network who are informing program development and design? So I like to look at a little network like this, right? Typically, we think we're developing a program. We think we have the pulse of those that are most central in the program, that are providing input to help us co-design and co-develop the program. But of course, we're not attuned to the isolates who may be very much in need of the program activities or services. And of course, typically what you get is subgroups that are completely almost disconnected, that may oftentimes see the development of this program in opposition of exactly what they do. So I think when we think of the community as network, we get much more explicit about finding who's providing input to the program, who's designing it, and whose voices are we listening to. Now, what's more exciting to me is using networks for program design, right? And so here we talk about, bless you, network interventions. And a lot of this work stems from a paper that I published in 2010 in Science on network interventions. And I give, not surprisingly, a very broad definition of what they are, right? So any purposeful efforts to use network data to try to accelerate behavior change, improve performance, achieve desirable outcomes across all different levels of analysis. And before I jump into networks interventions, there are a couple of principles that I want to highlight that are critical for all behavior change programs, but become heightened in the context of network data. And that is that our program goals matter, right? So often when we're working to promote physical activity or try to reduce substance use, we have a straightforward kind of goal. But when we think about it in a network context, it actually drives the kind of network intervention we may choose, right? In some settings, we want to accelerate behavior change, and in others, maybe the same setting, but we're working on a different goal or objective where we're trying to slow the spread of something. So that matters a lot, and I like to say that network interventions are not agnostic to the behavior under study. The other thing, and this was the hardest lesson for me to learn, my original training was in math. I didn't have social science other than a cultural anthropology class as an undergrad. And when I got to the social sciences, I thought, we can't explain what people do. Some days I sit on the couch all day. Other days I get up and go play frisbee, ultimate frisbee or something, right? So people are hard to predict. But I do believe at this stage of the game, we actually have a pretty good understanding of what drives people's behavior, what the motivations are, and what the barriers are. Do we invest enough money in doing it? No, but I think we know how to do it if we were given the resources. And then finally, my original goal with network interventions was to create a program that people could go out in the field, push the lever, change the community, send me the bucket loads of money, give me glory and fame, and I'd be done, right? But that's actually not how it works. You end up learning a lot. You use the networks to learn from the community. What's working, what's not working, how do we assist them in their behavior change activities. So here's the table. If you get nothing else out of this lecture, this table's become relatively famous. It's liked more than I am, by the way. So we have different strategies, and this comes from political and marketing campaigns. Strategies, your highest level, then you have your tactics, and then you have your operationalizations. And you'll hear in this political season, right, the Biden strategy for getting certain kinds of vote populations, or the Trump has no strategy, actually. So you have at the highest level, you're going to identify people to be change agents that you're going to use to change your program. And typically when we do that, we think about identifying the leaders, right? That makes the most sense. And when you go into an organization and you tell the boss, We're going to collect network data to find out that you're a leader in this organization and what you can do to change. He gives you the contract money, and then you collect the data and find out he's not the leader. That leads to a whole other conversation. But typically, that's our goal. And now you know from network analysis, we have lots of ways to find the most central node in a network, right? Degree, closeness between this, eigenvector, power, you name it. In fact, David Scotch has a website with 100 different centrality measures. But we always use in-degree centrality, which I'll talk about in a second. But there are good reasons you might want to choose other kinds of change agents or champions, right? If you've got a highly fragmented network, maybe you want to identify the bridges to make that network more cohesive, or identify key players, a la Steve Brigati's algorithm. Or if you know the low thresholds, if you know what the threshold distribution is, find those low threshold people and have them be your first adopters. So, typically, we do network identified opinion leaders. We have a lot of experience with this. It's easy to measure, right? And it's very intuitive. You just go tell people, I'm going to count up who gets nominated the most. They're popular. We're going to use them. It's been proven effective. In 2008, we did a review paper. And my goal in that paper was to find out the way we use opinion leaders and community members to assist in behavior change programs. And I was pretty convinced that we didn't use networks at all. And so my intention was to show that we don't do this and we should do this. And I'd even written the first draft of the discussion of the paper before we got all the data. Sure enough, what happens? We find 20 studies across a number of different applications that have all used network data to identify opinion leaders, use them as champions, and bring about significant changes by doing so. Nothing different than collecting network data and identifying the opinion leaders. Now, why was this unknown to me and why was it unknown to most people? Because those studies had all been conducted in different application areas. HIV prevention in bars and communities, HIV prevention in low-income communities, treatment of acute myocardial infarction, treatment of vaginal birth after first C-section. They were literally spread all across the NIH, basically. And as you know, NIH is organized by organ and disease, not by health. And so, as a consequence, none of these studies were aware of each other. Oh, and this is the table. See, my thought was we're going to get to here and be done, right? But it turns out we also had all that as well, which worked really incredibly well. We've run simulations. You see the network with those highest on in-degree centrality. You get faster diffusion and more prevalent diffusion compared to opinion leaders selected randomly. And we also tested the marginal condition. Why the marginal condition? Because in fact, many innovations originate on the margins of the network. People that are on the periphery are free to innovate. They're not constrained by the network, and in fact, they don't even like the network because it's not doing anything for them. So they're happy to turn it upside down. And then this Cochrane review came out in 2011. They end up showing a 12 percentage point increase in compliance just by using network identified opinion leaders across the same interventions compared to other interventions. This is a huge effect. When we power our public health interventions, what do we power them for? 3%, 5% at best, right? If you can get a 12% uplift, man, back the truck up, take the money. So why do we use in-degree centrality? Well, it's very easy to calculate, right? All I have to do is, put the sum at the bottom of an Excel spreadsheet, and I've got my numbers. It's easy to explain. And you can compare your in-degree scores with other centrality measures and along with key player to find out how well they work. And why are in-degree opinion leaders so effective? Well, if you just basically look at the data, right? If I take the top 5 people who receive nominations in this network, they account for 37% of the incoming ties. If I take a random 5 people from the network, they only account for 10.5%. So just by selecting those opinion leaders first, in the first time period of data, I've got 3.5 times as much network exposure as I would otherwise. That's a lot. Right? And we know that a lot of networks have scale-free centralized structures, and so as a consequence, it's generally always going to be the case that those opinion leaders have an undue influence in the network. Other reasons we use in-degree centrality, it's robust to missing data, right? Jim was talking about some results earlier from their work. We did work earlier. It turns out in degree centrality is incredibly robust to missing. Other centrality measures, not so much. And then, of course, we've done simulations and prior work and whatnot, and it works really well. It's incredibly flexible. And then finally, there's a whole area of science to be done about what do we do with these people once we identify them, right? And if you look across a lot of the studies that we reviewed and even the different ones I've been involved in, sometimes it's, let's just find those people, give them a button and say, you're off and away. Or we go all the way over here and say, you're doing grand rounds, you're going to start going on a book tour, we are going to make you an amazing individual. So there's a broad range of implementation issues to be worked out in terms of what works and what doesn't. Then, of course, we can identify bridging noses, and I like to bring this up because we, I'm guilty as anybody on this, we have a central preoccupation in the network field for identifying central nodes and creating centrality algorithms, right? You publish a centrality algorithm, you've got a badge there. You know, it's like a stripe in the military or something. And as I said, Scotch has already identified 100 different ones, but we don't spend very much time identifying bridges. And there are good reasons that bridges may be very successful, right? For one, they're not packed in the middle of the network, and so they're not having all of this constraint on them. They're actually free to innovate. And because they're bridges, they may be more amenable to change because they're connecting to different subgroups and different communities. There are 3 ways to, and this is one of the reasons I actually like this, to talk about this, because I get to talk about my own work on coming up with algorithms for identifying bridging nodes. So BERT's inverse constraint works incredibly well. And then we've introduced 2 others using sociometric measures of bridging, which are still not quite coded up entirely, unfortunately. And then you can identify isolates or peripherals. And again, if you know the threshold distribution for a community, finding those low threshold individuals to start your cascade process makes a lot of sense, right? Because they're used to adopting before their peers do, and probably are familiar with being an early adopter relative to their peers. Okay. All right, and then very simply, it turns out doing this stuff is not very complicated. All you got to do is collect your network data, count up your nominations to identify your opinion leaders, recruit them to be champions, and then here's where things can get tricky, right? Because sometimes they're not on board with what you want to do. You know, we've done smoking prevention programs, and sure enough, you're going to identify leaders for subgroups that are already smoking, doing dope, getting drunk, you know, like my son did in high school. And so you've got to work with getting them on board for whatever you're doing. Now, a lot of times they will. Like when you're working in clinical settings, the identified opinion leaders are already on board. They know that this is something that they care about and people are excited about. And then your job is to just help them get their job done. And again, back to that slide on learning, and learn from them. What's working, what's not working. So when you go to the next setting, you're able to do that. So the next strategy is segmentation. I won't spend much more time on all these different strategies and tactics, but one approach which makes a lot of sense is to direct the intervention towards a whole group, subgroup at the same time, right? There are some ideas, some behaviors that can only be adopted when everybody adopts them. But Facebook is a classic example. Interdependent innovation. It takes everybody to do it. Facebook got a good start by getting everybody at Harvard to log on and join the system at the same time. So it immediately had value, right? You know, if you get join a social media, social networking site, and none of your friends are on it, you know, yeah, you can post your own pictures and look at yourself, but there's really not much value to it. You have to have other users in your system. And now I won't go into all the details on groups. I will say, though, that when they started introducing the community detection techniques that Jim talked about earlier, that was a godsend for interventions, because now you get mutually exclusive groups and you get a modularity index that tells you how important those groups are. And if you're working in a setting where that modularity is very high, that tells you that the group structure is going to make a big difference to your intervention. Okay, that's just a pretty diagram. Again, implementation issues for that. And then the other strategy that's really interesting is this idea of induction. And both strategies 1 and 2 are a little bit descriptive and a little bit static. But what induction strategy tries to do is actually use the network, excite the network, and build on that network structure. And the classic induction strategy, a tactic was always word of mouth, right? Going back to the very beginning days of advertising, the idea was to get people to talk about your product, make it exciting, and so on. Try to get it to go viral. And what's interesting now is this has actually become instantiated with online platforms, right? Whenever I buy a ticket to a football game on StubHub, they're like, hey, tell all your friends are going, invite them, make it a party. And then there's a bunch of studies on snowball sampling and respondent-driven sampling. Some people push back a little bit and say that respondent-driven sampling is not an intervention technique. It's merely a technique to get parameter estimates for typically quote-unquote hard-to-reach populations. But actually, a lot of respondent-driven studies have an intervention component built into it. And I would argue the fact that they're participating in the doggone thing is an intervention in and of itself. And then the third one is network outreach. Carl Latkin at Johns Hopkins University has done a lot of this work where you grab a piece of your network, bring them into an intervention, and have the intervention together as a group. The idea is that that group is going to reinforce the behavior change. And again, many behaviors, particularly in the health domain, require your network to be supportive of it because you're trying to change habits. You're trying to change eating habits and exercise habits in a household. So it helps to have the whole household on board. And then the last tactic I'll talk about is one that we created a while ago, which is this notion of identifying opinion leaders, but not thinking that they're just going to go off and do their thing. We can actually identify peer opinion leaders and match them to the people who nominated them. And I thought this was a rather clever insight, right? So you take a network like this and you go, okay, who are the most important nodes? 23, 32, 26, 29, and so on. Well, rather than just identifying them and handing them batons, let's go ahead and match them to the people who nominated them or were closest to them sociometrically. So now I'm influencing the people that nominated me, right? Right? Us Biden supporters are not going to all of a sudden listen to something that Trump says. It's just not going to happen. Our networks break up into tribes and clans, and we listen to our peer opinion leaders. And I think of this particularly in the adolescent context, where you go into any decent-sized adolescent high school, you're going to see lots of different subgroups and kids who are leaders for different subgroups. And you know, I won't go into this in detail. I like this study because I learned so much about it, but it was basically we were testing a culturally tailored smoking prevention program against a standard social influences one, and we were able to test this network matching algorithm to see if it did better compared to finding groups. So we identified peer opinion leaders the way we always had in school-based programs. We had teachers identify leaders and put kids in groups, and then we used my network algorithm to identify the most popular kids. They would be the same ones that you'd find here, only constructing the groups through the network ties. And just real quickly, I'll show you, we ended up getting significant, weak, but significant effects in the network condition. And mind you, all we did different, the only thing we did differently is construct the groups using the network data. No additional costs. And when we looked at outcomes, we found out that it really knocked down susceptibility to smoke, which is incredibly predictive of eventually becoming a smoker. And then in our one-year outcomes, we got a finding that said, wow, the teachers did better than my algorithm. Nobody was surprised by that. I'm not a great mathematician and certainly not a great programmer. But the teachers did better. And the teachers did better because they knew the kids. They did this in April, right? And so they knew, and they did it along ethnic lines more so than the network did. And it was so funny because when I got this result, I thought, oh, Journal of School Health, that's got like an impact factor of 500. This is going to go in there. They're going to love it. I send it off to School Health, and they're like, nah, desk reject, not interesting. You got to be kidding me. Okay. So the network algorithm, it was more appealing when we asked the kids about whether or not they liked the program. It reduced pro-tobacco attitudes, it reduced susceptibility, but its effect was dependent on curriculum. And this is a point when I do a workshop on this that I hammer home. We never think about how people consume our programs. And I guarantee you, if I watch a movie or a TV series with some people, I'm going to react differently than when I watch it with somebody else, right? That network context of program delivery and program consumption is actually critically important that we generally tend to ignore. Okay, and then finally, originally I called this manipulation and realized that this is probably not the right label I want to use for this strategy, and so I thought alteration sounds better. You know, I'm a tailor, just going to take in a tuck here or there, let something out, make it more comfortable. So there are different kinds of alterations that you can do, right? You can delete or add nodes to a network. You can delete or add links to a network, or you can rewire the entire network based on some properties. And so the way we do this is we calculate a network metric. I generally use cohesion. A lot of people use that, basically the inverse of the average path length. Delete a node, recalculate the metric, calculate the difference. Those with the largest difference are the most important, and this, of course, is the vitality centrality measure that you will find. And Everett and Borgatti expand on this a little bit in their induced centrality paper. More interesting is the idea of adding or deleting links, right? It's the same process. You calculate your network metric, delete a link, recalculate the metric, calculate the difference. The links with the largest difference are the most important in the network, right? And this really was Granovetter's insight. If you go back and read that Strength of Weak Ties article, his argument was those ties, when removed, increase overall path lengths the most in the network, are the most important. So really just building exactly on what he said. And in fact, so you can do this at the same time for both deleting existing links and adding non-existing links to find out which links make the most sense to add to the network. You can put all this in a change matrix, and then you can start to analyze this change matrix as a way to understand the network structure. And you can, in fact, do this for lots of different metrics, right? You could do it for centralization measures, transitivity, modularity, and whatnot. Put it all into a gigantic array and just have the time of your life analyzing network data. There are implementation issues with alteration. It's not clear which network metric to maximize. And of course, getting into the business of deleting and adding links in a network is a little bit tricky, right? People have friends because they like those people. They have enemies or people they don't like, and they don't associate with them. And those things are hard to change. And I don't think we're going to get much perch on making these kinds of changes, but I think if we did, we'd learn a lot about human behavior and human social systems. Okay. And then finally, we can rewire networks to have global properties, right? We can take an empirical network and make it a small world network. We can make it a centralized network. And most importantly, and this is something that actually happens all the time, we just don't document it, we can rewire a network to match users with non-users, right? That happens all the time, a buddy system that you have and whatnot. And so this is a very logical thing to do. And teachers do it in schools all the time, but we never document it. And there's that. Okay. So back to this table. It's a beautiful table. It's been expanded a little bit by a couple of other folks and adapted to different applications. I always like to say we have an R script. Yes? Vitality. So it's the name that they gave to this centrality measure in which the person whose removal increases path lengths the most in a network. It's in a very obscure edited network book. Okay, so after you've now done your network exploration, you've figured out what's going on, you've designed a network intervention, oftentimes network interventions are being implemented in group and different kinds of settings. And so a number of years ago, we came up with this idea of developing network diagnostics. And the idea is quite simply that while you're doing an intervention, you can keep track of these different kinds of metrics. And we wrote this paper up and put these metrics into a table and sent it off to a journal. And all three reviewers came back and said, where did you get these values from? You know, who says it has to be greater than 0.5? What do you mean it's supposed to be 0? Where did you get these from? And I thought, well, here goes. I just made it up. Nobody's done this before. I've been doing this stuff for a while. I have no idea. And it surprised the heck out of me. All three reviewers came back and said, yeah, it seems fine. It's like, when do they ever do that? It's funny as heck. So, and then I want to just segue a little bit into the notion of different networks. A lot of times we talk about networks and we don't talk about which networks we measure. And evidence has certainly emerged. Bria Perry, who was here earlier, talks about the network episodic method model where, you know, they know that people go to different kinds of people for different kinds of resources and activities. And usually with a lot of the work that I do, I tend to measure advice and discussion. Advice tapping into expertise and discussion tapping into trustworthiness. Now this goes all the way back to the Coleman, Katz, and Menzel study that you heard about before. They measured advice, discussion, and friendship amongst the physicians in the 4 Illinois communities that they measured the adoption of tetracycline. And different networks may require different strategies, and I oftentimes think that if you're looking at advice networks, you're probably going to be thinking about identifying opinion leaders, but if you're going to be working in groups and segmentation, you may be more inclined to work with discussion networks. And I argue that, in fact, many people, this behavior change process and the effectiveness of leaders depends on their expertise and their trust. And ideally, you find the folks down here that know what they're doing and people trust that they have the community's best interests in their heart. High in expertise, high in trust. And you can find people, I've done lots of studies where you find people that are very high in expertise, but not trust, and vice versa. And I like to think of these along these 2 dimensions of vertical versus horizontal, right? Advice seeking is expertise. It generally tends to be much more hierarchical, much more asymmetric, whereas discussion and trust are horizontal, right? It's going to be with your peers. That's who you discuss matters with. And if you're in a situation where the barrier to change is technical, then expertise becomes critically important, right? People don't know how to do it. They need to be taught how to do it. On the other hand, in many settings, our behavior change barriers are cultural. People don't know what to do or even why they should do anything. Then trust becomes critically important and is an important network to work with. So the advantages of network methods are they capitalize on existing interpersonal relationships. They use community input. I argue that many of them will be effective simply because you've solicited input from the community to participate. People feel empowered, emboldened. You establish a learning organization and a learning community by identifying opinion leaders and matching them to those who nominated them. It's directly linked to all these concepts of social capital that we talk about. And from a scientific perspective, it gives us something that can be replicated. And we can measure the fidelity of our interventions, right? How important were the opinion leaders relative to other people in the community? How much modularity is in the network, and therefore it made a difference for us to identify subgroups. It really expands our array of intervention options, and of course, most critically, it creates data. I was telling somebody the story earlier yesterday about how school-based prevention programs, the teachers would oftentimes put the roster up on an overhead, back in the days when we had those overhead things, and give numbers to the kids in the roster and then tell the students, write down the numbers of the top five you think would be a good leader for a project in class, right? So then the teacher would collate all those papers, she'd tally them up. When she saw that Tom got a lot of nominations, she would immediately edit out the data. And then she would pick the top 5 that she liked, and then what would she do? She'd throw the data away, right? And that's network data. It's like, oh my God, all of that network data went into the waste can that we could have had and used so well. So I tried to do that quickly because I had a lot of slides, and that gives us about 5 to 10 minutes for questions. And if you're wondering, there is a draft book that covers all of this and how to do it that is almost through the wickets. Yeah, my pleasure. Yes, Pooja.
I couldn't help but think about how much overlap there is between designing network-based interventions and participant or community engaged research.
Right, yeah.
So I guess one question I had, because I think you mentioned with opinion leaders, sometimes they may not be on board with whatever program or agenda that a researcher has. Have you found in your work, or is there literature describing how to kind of engage opinion leaders in designing interventions?
No, that's a really good question, because every time I've done this, when we identify the opinion leaders, they're like, oh, this is great. Because they're already doing it. They know that they're an opinion leader in that domain. And now you're going to reward them right? And you're going to acknowledge it, and you're going to give them resources to do it better. So unfortunately, I don't run into very many situations where you have that resistance. It's out there, you know it's out there, but I think most of the time they're just going to fly under the radar, right? They're not going to be confrontational about it. They're just going to go, yeah, I can't show up that day. Yeah, something like that. Yeah, but there isn't a literature on that. There isn't a literature, to my knowledge, of how you get them engaged. It is. And engagement is the key word that I've really latched on in the past couple of years, because it is getting people engaged in bringing about change. And a lot of people, it's a frustrating process, right? I mean, a lot of times we're working in settings where it's not easy to get people engaged because of all the barriers and time and resource constraints. And that's probably the biggest thing, is give them resources. Yeah, yes.
Okay, over the last few months, you had a slide up there about like, if this is the barrier, then this is the solution, and if this is the barrier, but what if resources are the barrier?
Yeah, rob a bank. I mean, that's what Jesse James said. You know, why do you rob banks? That's where the money is. But I think, yeah. But it's a really good point, and it frustrates me, and I'm sure it frustrates many of us, because we work in a capitalist country, right? And so everything is all about the money, but it's really all about the people who have money keeping the money and not investing it in communities that don't have the resources. So I think, unfortunately, a big part of the equation is the political policy process, which, you know, is not something I really feel like getting involved in, but there are people who do, and it's important that they do. But yeah, I think resources is a big part of the equation. Yeah, you can move a lot with a few dollars. Yeah. Jim. Oh, Gabe. Gabe, standing in for Jim.
I was wondering if you could talk about the way that intervention, you know, might transform the positions of, say, the leaders that are in that network, and then how do you work to track that transformation of this, you know, the network system as a whole, and do you sometimes, in preparing an intervention, think about how it's going to transform?
Yeah, and there's ethical issues there, right? We're tampering with a system, and we're reifying an existing hierarchy, perhaps, that we may want to be conscious of. And there isn't research done on what happens when we get people into an intervention, and down, you know, 6 months, a year down the road, has their network position changed? And a lot of times, you know, opinion leaders may be hesitant to get involved in intervention because they don't want to take a chance. If you're proposing something that's incompatible with the community, opinion leaders are going to delay adoption behavior, and they're probably going to be resistant to getting involved. So there's a cross between getting them involved in doing it, but also the fit of what you're trying to do, the cultural compatibility of it. There's a great study that a guy named Becker did back in, published in 1970, showing that for an innovation that is not compatible with the community, opinion leaders delay their adoption. Many people make the mistake of equating early adoption with opinion leadership, and those are two different things. They sometimes cross because once opinion leaders adopt, the innovation starts to spread rapidly, but that's just a mirage, right? If it's not compatible, they are going to be resistant. Now, I think there's a huge research opportunity to actually look at this. What happens when we tamper with networks for interventions, and how does the network change as a consequence? There's a really nice paper that a Dutch researcher did that I reference in the book. Waes is the last name, W-A-E-S, where they had kids in elementary school report on who they liked and disliked in the class. Then they rearranged the seating to put the dislikers near one another, and they started to like one another. Go figure. You talk to somebody and they turn out to be okay. Yeah. Yes. Sir. Oh, nice. Yeah. Well, Carl and I were at Hopkins together. Yeah.
And so I don't know if it's about the knowledge network thing, but I know something that if there are different things that assessing acceptability for the ideas,
Mm-hmm.
there's 500 million things that are working on, but what is the most acceptable, what's not the most exists, and then designing communication means based on like involving the community to see what can they share with their peers.
Yeah. Yeah, people who inject drugs. Yeah, yeah. Yeah, no, and he's done such a long career of really great work in this area, and he really embeds himself in it. And the one thing I found funny about working in Baltimore, though, the injection drug users there were so sophisticated, they would tell you what the going rate is for an incentive. It's an overstudied population. Yes, Jim.
Yeah, so we just finished a study of innovation of fishermen in Victoria, and one of the things that we're struggling with trying to understand is that with an in-degree-based selection, we got people with in-degree, we gave them some training and told them they were leaders, and they recruited their friends, and it worked great. All is fine. But then we're trying to understand why. And in talking with people at the end, there's sort of two stories. One is that they're real opinion leaders, they really are sort of the most popular, and people respected them and did what they said to do. The other option was that once they learned they were opinion leaders, they took pride in being opinion leaders, and then worked harder at convincing their peer group who told them, said they were leaders, to do it. And so we don't know which of those two mechanisms is true.
They're both true.
But do you think that if you randomly picked people and told them they were leaders?
But you wouldn't get as much of a lift, right? I think it would still work, right? Because it's community-based. But I don't think you'd get as much of a lift.
It would be a lot cheaper.
Would it though? So it might be cheaper, but it might not be more cost-effective. Look, I'm telling you, pharmaceutical companies are spending a couple $2 billion a year doing this stuff, and they do it for a reason. Yeah. So I think you're right. If you just built some people up, but see, the people that you've identified through the networks, we know from research on what's correlated with high in degree. More personable, better communicators, taller, handsome. But these things, these personal characteristics as well as both physical and personal characteristics matter. And so I think, yes, they become better at doing their opinion leadership, but they're also naturally good at it, right? If I pluck people at random, some of those people are going to be good at it and take pride in it and say, yeah, I'm a leader. Others are just not going to have the skills, the traits, the talents to do it, right? So I don't know that it would be cheaper. I don't know that it would be more cost effective. It would certainly be cheaper, but then let's go back to how much of a lift we get, and is it worth it? And I argue for a lot of the things that we do in public health, that lift is critically important. Yeah, there's one in the back.
So building off this a little bit, Erickson wrote early in his path about the Buffalo Creek flood, and what happened was flood came through and basically destroyed a community, and the government rehoused everyone into a more regimented community, and it didn't work. In fact, that's one of the main points of the book, is that it destroyed the community. And the point I take away from that is that it's very difficult to rebuild, or reconstruct a network.
Absolutely, yeah.
That you can't just kind of take a group of people and rewire them.
I totally agree.
Yeah. So can you say a little bit about that?
Because I think we don't have many examples of this, if any at all, or any that I know of that have been published. Because I think networks, some people argue that any network you measure is at its optimal shape because people have made choices. And we have that deliberately built into a lot of our network statistical models, that people are deliberate in the choices that they make of who they connect with, who they like and who they don't like. And characteristics such as sex and ethnicity also play a role in those things. So I don't think we'll be very successful rewiring networks unless there's a real critical reason and need to do so. Now, some architects try this, right? They rearrange offices to get people to, and they design offices to create more opportunities for interaction. But to my knowledge, I don't know of any study that's done that has demonstrated that it's been particularly effective. So I agree with you. I think rewiring communities and building communities is a difficult thing to do. Yeah.
Arguably, Facebook, Google, YouTube, all of these algorithms are doing exactly this.
Yeah. And I would say they're doing it in a poor way. Yeah. Yeah. They're reifying all our poor tendencies in terms of networks.
But it strikes me that they have the opportunity to do just the opposite.
And that big LinkedIn experiment that they did demonstrates that. It has other ethical concerns, but that was a different approach, and it had incredible outcomes. So they I think it was 70 million users, and they randomly selected some to receive job recommendations or links from weak ties rather than strong ties. Right? And those weak tie, the people who received those weak tie friend connections were more likely to apply for new jobs and get new jobs. That's a summary. Yes, Justin.
I'm curious about like the dynamics and these networks and like especially with interactions. I noticed like we'll roll something out, and just as soon as it seems to be working, people like adapt to that language, and then it's like well, like even with like social networks, like and people leave the networks or start using that network, and like they reshape things, and then people react to that. I'm wondering about. I know there are some people with complex intervention space that like I'm trying to study the dynamics ahead of time so that you can compare those things. I wonder if you know anything about that.
You know, I haven't. It's always a caution that networks are constantly changing, but it's my impression they don't change a lot, right? And I think we have evidence for that in a number of settings that they don't change a lot. They change some. But I also don't think people's position in the network changes very much, right? So there may be some swapping, dissolution, addition, and change of ties, but popular people remain popular, right? And I know Jim's done some work on this. I mean, I think they maintain their popularity for that simple measure, for example, over time. So I think it's a concern. I think it'd be a great thing to measure. I would love for people to start giving us money to do network interventions and track them over time. I can tell you when I was early on doing this, we did an intervention to try to get clinicians to diagnose and treat people with co-occurring disorders. And we had, treatment sites and control sites. And about a year and a half after the study, even after we published the data, we were doing a panel. This was in Florida. And one of the guys who was an opinion leader in one of these clinics, bless you, was there. And I said, oh, so how did it go? He goes, you wouldn't believe it. People are still asking me about co-occurring disorders. This is a year and a half later, after the intervention. And so, yes, the networks are changing, but network interventions, in my estimation, are way more sustainable than most everything else we do because the intervention stays there, right? Long after we leave. Even if other people have left or come in and out of the network. If you've trained opinion leaders to promote some kind of behavior in a setting, okay, some people leave and some new people come on. You still have that opinion leader doing what they're supposed to be doing, right? And then I'm new to the organization. It's like, co-occurring disorders, who do I talk to? Sam, he's the guy. Boom, it's done. Yes?
In understanding network interventions, has there been any type of coupling with conjoined choice experiment to understand, like, say, like membership, group membership? Because I can see where there's potential room if you conduct a survey and you know your network originally, and then you take those people and then ask them to choose between people 1 or 2 and just kind of continue with options to see their
Who they prefer to learn from?
Yes.
Huh. No, I hadn't even thought about that.
I didn't know if there was any literature.
I hadn't come across anything like that. Sounds interesting. Also sounds a little labor intensive, but yeah. Yeah.
I mean, first row of anything.
Yeah, right.
Before we go into criminality here, let's take a break.
Yeah.
Stretch your legs, get some more coffee or something sweet, and we'll be back to Scott.
I'm not as panicked as I sound. So I think you're on the committee of a student at my school, Alan.
Oh, yeah.
Yeah. So, do you know Rebecca Moore?
Yeah, I see a lot of messages. Yeah, I know. I see because I asked for my friend. I remember I have that kind of job. So I'm taking
Once you submit it, and remind me.
yes, yeah, with like disappears.
Yep.
I left my charger here,
I'm glad I remembered my phone. I just left it charging just now.
But at some point, I would love to get very yeah. Yes.
And so we'll do like the fire, it hasn't gone very far. It's still a pilot, but there's lots of studies that have provided lots of different things. And then, of course, the Texas.
Yeah, it makes a lot of sense. Wait, hold on. I know, like, I know there's work in vaccinations. I know there's stuff in vaccinations.
Right. Yeah, supports it. But I don't know what they're not saying.
Or even like access to care.
Yeah, there's a lot of that. Yeah, a lot of that's in that RDS space. And you're reaching out, you're trying to snowball out. Oh, man, nice to meet you. Yeah. All right.
Thank you for doing this.
Yeah, no worries. Yeah, always happy to come out here.
Done with your semester, so I'm assuming?
Yeah, well, the chaos ends today. Is that my tenure case is being voted on by the Board of Trustees today.
Oh, yeah.
So,
Awesome.
see how it goes.
I can't imagine there's any problem.
I'm not too worried, except that the board's been a little weird lately. Not about tenure cases, just in general. So it's, we'll see. Yeah. No worries. I tried to include a lot of workshop information, so it should. Long way of saying I'm not totally sure how long it'll take, but it's got plenty of flexibility.
It's me and Gabe after you, so we're flexible.
Cool. It's good to know.
We're just talking about drawing pictures. So.
Yeah. Did Alessandra end up committing to Duke?
What's that?
Did Alessandra end up coming to Duke?
No, she did not.
Oh, yeah.
She disappointed us deeply. Decided to go
Us
off.
too, yeah. The fact you would even come to the area. No, I'm kidding. Where'd you end up going? Princeton? Nice, good choice. I mean, second best choice. Third best choice. But it's a decent one.
If you're going to make a mistake. Fine.
Yeah, we can live with that.
Well, there's always next year.
Always next year, yeah.
You put your name back in the hat. Can't make any promises.
Yeah, so how are things on your end?
Good. We finished the PIP review last week. So that's done. This will be done on Friday.
Yeah.
And then,
taking a vacation, heading to Montana.
Exactly. So I get to sit in the audience side of the office, for Steve's conference next week.
Nice,
And then I'm hitting the road.
Yeah. Yeah, it should be a good conference. I'm looking forward to it. Yeah, it does. Yeah, it'll be interesting. It seems like a very exclusive group of people.
Yes. All right, folks. Wrap up your friends, colleagues, and countrymen, and we'll get started in just a moment. I'm really pleased to have Scott Duxbury with us today. Scott is one of the leading experts on dynamic network analysis models. He's substantively, he works in health and crime. He has some of the most fascinating data on like where to buy drugs on the web. Hopefully no one in here has done any work to get you in the data set, but otherwise, it's really remarkable work. And for a long time, the critiques about statistical models of networks have been binary, it's static, and you can't infer sort of causation or these types of things. And that's just no longer true. And the kind of work that Scott has done to help make it possible for us to think about dynamic networks, to interpret these models using things like interaction effects and marginal effects and other sorts of micro macro variations in the network effects. It's really been sort of a game changer in the way we can get work done that's meaningful and estimating mathematically and methodologically the kind of intervention effects that he's also just about to hear about his tenure decision from the board of trustees tonight, I think.
Tonight.
So,
as a matter of fact, I think they're live streaming, so if people want to pull it up and see what the vote is.
So we won't say congratulations yet, but hopefully by the end of the barbecue tonight we'll be able to do it.
Yeah,
so
hopefully
anyway,
we'll
we
see.
won't jinx it.
Thanks, Jim. So thanks so much for having me out here. This is really great. I am going to be talking today about temporal exponential random graph models. So in contrast to the talk that Tom just gave, this is going to cover less material. I am not quite the engaging and concise presenter Tom is, so I cannot cover a whole book in 45 minutes, unfortunately. But what my hope is today that we're going to be able to take a deep dive into a temporal exponential random graph model, or a TERGM, talk about what it is, learn how to implement it, learn how to interpret it, learn how to figure out if it's any good, and then figure out how you might want to apply it in your own work. Now, you heard Jim use the word crime and methods a lot. What you did not hear him use talking about me is health, and that's because my background is not in health. And so what we're going to be doing today is talking or using an example data set, which is actually a conflict between nations and the evolution of alliances between nations over time. And the reason we're using this data set is partly because network panel data is hard to come by, and partly because it, in my opinion, shows the extreme generality of TERGM, that we can use it for a pretty widely defined type of node set, which distinguishes it from alternative network panel models like the Siena models you'll be learning about tomorrow, which are restrictive in some ways, but actually really liberating in others. And so we'll be talking about why that's the case. So before we jump into it all, I do want to warn you, one of the models here actually takes about 10 minutes to run. And that model is right down here. And so if you want to run, if you're following along today in the R script, I encourage you to actually start running everything through line 166 right now, so, which I've already done ahead of time, and that'll allow you to kind of keep up as we're going through. OK. So the fundamental idea behind TERGM is that what we're trying to do is create a model of network change. And we're trying to create a model of network change that captures interdependencies between data points. So my understanding is you all have talked a bit about ERGM today. And what the temporal exponential random graph model is trying to do is take the ERGM framework, specifically its generality, its ability to account for exogenous edge-level processes, node-level processes, dyadic processes, and endogenous statistics, and extend it to a longitudinal framework. So the fundamental question, stated in its most general form that TERGM is dealing with, is why do ties change? And so we can think about these tie changes as relating to a large type of relational phenomena. It could be, why are people getting married? What creates structures and kinship networks? Why do people become friends? What shapes social cohesion? Or what causes somebody to buy drugs on the darknet from a specific seller? These are all very general ways of talking about relational phenomena that we can treat as the dependent variable in TERGM. So what makes TERGM distinct from some other types of longitudinal network models is it's specifically concerned with network panel data. What we're assuming is that we have at least two measures of the same network at different points in time. We can allow for the node set to change, but we're assuming that the fundamental network we're trying to measure is not constant, but is the same phenomenon measured at distinct points. Now, there's some interesting features of network panel data that are important to get a handle on before we jump into applying a TERGM. The first is that there's an implied assumption here that tie changes are coarse. And what I mean by a coarse tie change, it means that the tie we're looking at, or the relationship, is assumed to be relatively stable. And so if we're talking about something like a friendship, I mean, we're not kind of like saying, I will be your friend between 1:15 today and 1:30 today, unless we're very strategic at conferences or something like that. Then that might actually work out. But in the most part, ties are assumed to be relatively stable and move when something moves upon them with kind of ambiguous timing of a tie forming and a tie dissolving. This makes it actually distinct from other types of longitudinal network data, such as relational event data, where timing information tends to be extremely well-defined and easily ordered. The second consequence of having a relatively coarse measure of tie change is that it means that when we have multiple measures of network data through panels, we don't know exactly when ties change. And so in this example here, that's put up on the panel or on the screen, we can see that there has been some momentous change in the network. We went from, well, these are actually two different simulated networks, but if they are the same network, we went from something that was a small worldish structure with high levels of localized clustering and relatively low centralization to something that is relatively consolidated, follows kind of a chain link structure with preferential attachment to two highly connected nodes. So we know there's been a massive change in topology, essentially an elimination of clustering, higher amounts of connection to central nodes, but we don't know the order of those changes. And we don't know exactly how that change process unfolded in this unobserved moment in time. Now, this problem in itself isn't actually unique to network data. If we think about panel data in general, if we're measuring something like, are you a smoker? What this is implying is a sequence of kind of events in the past 6 months or something like that. How many cigarettes have you smoked? And now people are reporting information about whether that behavior has changed. So we still, in this instance, don't know when the smoking behavior changed. But what we're able to do is make some assumption that our unmeasured component is uncorrelated with the change process and whatever effects we're trying to identify. In the case of Turgum, we're actually going to be making that same type of assumption, and we'll talk about it a little later. But the assumption comes with additional caveats because everything we don't observe is actually interdependent, right? It's a network structure where some endogenous processes, such as when does a triad form, are actually contingent on other ties existing before that next tie. And we can't measure any of this directly. And so the way Turgum deals with this and the way stochastic actor-oriented models, which you'll learn about tomorrow, deal with this are quite distinct and make them competing in terms of some of their assumptions and in terms of some of their modeling capabilities, but ultimately designed to handle the similar data structures. So we'll be focusing today on Turgum, and the heart of Turgum is an autoregressive framework. This approach is easy to implement and is actually a relatively small extension of cross-sectional ergom. And so we'll start today by kind of doing a quick review of cross-sectional ergom, hopefully trying to anchor it in a very familiar model, which is logistic regression, before introducing additional complexities, and then moving on to extensive cases. So we'll start with the most kind of earliest, simplest form of Turgum, and then we'll move to separable Turgum, and also kind of what I call between within Turgum, which allows you to account for stability and change at the same time. One of the benefits of Turgum that we'll talk about is the assumptions it makes tend to be relatively flexible in terms of it's not making explicit assumptions on what drives network change, in contrast to Siena models. But the trade-off of this is that in many cases it actually provides a less realistic representation of the unobserved change process. Now the trade-off here is it enables us to actually model some social or health context that we could not model with alternative panel data models. However, it also means that we have to be very careful about what exactly we're trying to specify and whether it's reasonably captured, because Turgum does not adjust for some of the things as its competitors. And if anybody needs a clarifying or a quick question point, just interrupt me. This is my second lecture today, so I might just be going ahead with it. OK, so we'll start with a quick review of the most general case of a binary exponential random graph model. We're assuming that we are observing some network out of a distribution of potential networks that could be observed for a fixed set of nodes. And what we're trying to figure out is what increases or decreases the probability of observing our network as opposed to all other networks that could be observed on a fixed set of nodes by perturbing the ties. So we have our binary realization of the potential network, which is just denoted by Y. We also have our sufficient statistics in the network lingo, which are essentially counting how many triads or endogenous structures we observe on the network, and what is the sum over whatever exogenous attributes we might want to include, such as race, smoking behavior, gender, any other kind of node-level dyadic characteristics. Theta is our parameter vector. It's just telling us what increases or decreases the probability of observing our network. And this ugly Greek symbol eta is telling us that we can actually specify an arbitrary nonlinear functional form. And so this is the most general case of ergom, which we refer to as a curved ergom, which counts for nonlinearity in the structural component. This is not the most intuitive way to think about ergom. This is the most complicated way to think about ergom, and it's the way we typically talk about it in the literature because it has very desirable properties for estimation. The easiest way to think about ergom is, found the markers, is as a logistic regression. And so in the simplest case of ergom, what we can write, that one's dead. We can write the model as a logistic regression. That one's dead too. Let's see. There's a whole arsenal back here. You know, over at UNC, they're always like, Duke has money, but apparently not for Marcus.
We use our markers.
Oh, sweet flex. Thanks, Jim. So the simplest way, there we go. Now you have to deal with my handwriting. The simplest way to think about ergom is simply as a logistic regression of the probability of observing some tie at a dyadic level. And so this functional form should look relatively familiar. Because what it is the exact functional form of a logistic regression. What we have here is the probability of observing whether a tie exists or does not exist, divided by the probability does not exist. So this is just our log odds ratio. And over here, we have our coefficients. We're using theta because we like to be fancy, but we can call them beta if it makes it feel more familiar. And then over here, we have our change statistics or our input variables that are increasing or decreasing the probability of observing a tie. And so our data structure, if we arrange it to fit into this, go ahead.
Is that just a fancy way of saying covariates?
Yes. Okay. Yes. Covariates, if that works better. Absolutely. We like to be fancy over here.
I was like, that was set words.
I know. Yeah, you get a lot of verbiage from me. I'm sorry about that. So what we're doing here essentially is what we're predicting is the probability of observing a tie given all dyads that we actually observe in the data. So say we have a simple triadic network that looks something like this. We have 3 nodes. Our data set is essentially going to be each pair of dyads arranged here with the ties we observe written in terms of 0s and 1s, and then any predictor variables we want to include over here on the right-hand side. So in this case, let's say these two are boys, this is a girl, and what we'll have here is some covariate for sex, and we'll count up how many boys are involved in the connection as opposed to girls. And this is in essence what we're going to estimate. Now, in this limiting case, what we're essentially saying is that the sex covariate, whether a node is a boy or a girl, is exogenous with respect to the tie. And so what this means is that actually, if we just took this very simple model, where we have one independent variable assumed to be exogenous, and a dependent variable that is a tie, we just fit a logistic regression, and we call it ergom. And we can interpret the results as essentially saying the log odds of observing a tie increase by theta depending on whether a dyad includes one or more increasing number of boys as opposed to girls. So this is the simplest case, and the reason I like to emphasize the simplest case is because our fundamental interpretation of ergom and tergom results can still be brought back to this kind of logistic regression-esque type of model, even when we get to more sophisticated cases. But the difference is, as soon as we start including endogenous stuff, we actually can't simply estimate the model as a logistic regression. Once we include anything endogenous, now we have to use this model, this representation for estimation. And accordingly, if we try to fit a logistic regression, we get what we call pseudo-likelihood, meaning our estimates are biased. Specifically, our standard errors are worse biased than our estimates. I swear that's a phrase. Meaning that we tend to get relatively small to moderate bias in our coefficients and bad downward bias in our standard errors. So what does this actually look like? Well, if we are to include if we are to include an endogenous component to this model, what we're essentially going to be doing is trying to situate the model in what I think of as a potential outcomes framework. And so rather than simply modeling the probability of a tie, whether it's a 1 or a 0, we are going to model the probability of a tie conditional on y minus yi of j. And what this minus sign is indicating is that the rest of the network is held constant when we calculate our endogenous statistics. So what this means is we can think of a focal tie. We'll start with a 1-2 tie. And what we want to figure out is, does this tie actually close a triad? Now, if we were to simply predict the presence or absence of a dependent variable conditional on whether a triad exists, we're going to get an endogeneity problem. We can't ever see a triad without a tie being there. And so instead, what we do is we model the change in the triad count as a function of the network that could exist if we were to change a focal edge. And so this is why we use this delta plus sign. It indicates the change. So what this means, say that we induce two potential outcome networks. One is the potential outcome when the 1-2 tie actually does exist. This is the network we observe. And what we want to figure out is how many triangles exist in this network. Now, for those in the back who might be like on their tippy toes by now, the answer is none. We don't see any triads. When we remove that tie, we also don't see any triads. So what we're going to do is subtract the difference to get our change statistics. And for this 1-2 tie, we're going to say the number of triads that are formed when this tie is created, conditional on all else constant, is 0. We're going to do the same thing for the 1-3 tie, which gives us no unique triads. But now we're also going to do the same thing for the 2-3 tie, which for in the back currently does not exist. When we create that tie, holding the rest of the network constant, it actually creates one triad. And that's our predictor. And so if we get a coefficient for our triadic closure model, what we are essentially saying is if a focal tie closes a triad or increases the number of triads that would not otherwise exist, it is more likely to form. So I'll say that again because I'm getting some squints. If a tie closes a triad that otherwise would not exist, it is more likely to form. Why is that? That's if we get a positive coefficient. In this case, we might get a negative coefficient, in which case we could say if a tie closes a triad that otherwise would not exist, it's less likely to form. Why? Because we don't observe any triads in this network. Right? So this is how ERGM deals with an endogeneity problem. And even though the complexity of this representation and the potential outcomes written here are a little fuzzy or kind of strange to think about, we're still essentially providing an interpretation in the form of a logistic regression-esque model. It's still an increase or decrease in the log odds. We can still exponentiate theta to get an odds ratio. We can still feed our predictions through a logistic link function to get predicted probabilities at the tie level. Or, if we want to be really fancy, we can actually do the macro interpretation too and talk about what networks are more likely to be observed, conditional on specific features. Okay. Mm-hmm.
So for the rule about, like, you're saying that the ties more likely to form, is that a kind of like rule that you impose, or that's a mismatch?
It's a rule I've imposed. So yeah, let me reiterate this. So if we're saying if the coefficient for theta is positive on a triadic closure, then we can say a tie that closes a triangle is more likely to form as compared to a tie that does not. If the coefficient is negative, as would probably be the case in this instance because we see no triads, then we can say that a tie that closes a triangle is less likely to form compared to a tie that does not. Mm-hmm. Do we need other clarification questions before we jump into the dynamic setting? Cool. All right. So ERGM adds a lot of complexity. It's a different way of kind of thinking about tie-generating processes. But one of the really desirable properties of ERGM is it allows for a lot or an extremely wide range of possible specifications. We can count for things endogenous to the network structure, as well as kind of the classic exogenous attributes like sex, race, smoking behavior, whatever, that we want to include to predict tie formation. When we get to the dynamic case of TURGM, what we're actually going to do is extend this basic framework for cross-sectional data to the longitudinal setting. By really, at its heart, we're just expanding our adjacency matrix. And so what we're doing here in the world of ERGM is we're arranging our data into an adjacency matrix with, if we have this limiting case of a triadic network, it's going to be a 3x3 adjacency matrix. And in a TURGM, what we're going to do is essentially expanding this to what's called a block adjacency matrix. So what we have here is, rather than taking one simple network representation, which is the triadic network, and I actually did not plan this out, it's the same network as on the board, which is great, but it also shows I don't have many unique ideas. So we start with this representation, which in this example of a classical ERGM is a cross-sectional single measure of a single network. But now what we have is multiple measures. So now what we have is 2 time points of the same network where one new tie forms between the 2 observations. So our single adjacency matrix that was represented here now gets expanded to be a block adjacency matrix where we have multiple measurements of the same network at distinct moments in time. So rather than the dimensions of the matrix being n by n, or in this case 3 by 3 because we have 3 nodes, it becomes nt by nt, meaning we have distinct adjacency matrices for each time period and each set of nodes at that time period. And so we call it a block matrix because we get blocks. So we can break our block adjacency matrix into square components which represent the distinct network panels. So in this case, we have this diagonal entries representing the distinct network measurements. Here, the network before the tie changes. Here, the network after the tie changes. And then the off-diagonal elements are simply zeros. And the reason they're zeros is this is essentially a tie here would indicate I have a connection to somebody in the future. And so we're fixing these at zeros and only estimating the tie changes that we observe. So the basic idea behind TURGM is once we arrange the data into this format, we can actually fit an exponential family random graph model, some specification of ERGM, to this data structure, and then try to deal with whatever autocorrelation that comes up because of the sequential measurements of the same data. And one of the things that's really, really cool about TURGM is this, because the data structure is so flexible and the model is such a minor extension of traditional ERGM, is it actually allows us to fit generalized cases of ERGM to longitudinal data as well. And that means we can use TURGM for things like weighted networks. We can do TURGM for very long time periods as well. It's an extremely flexible specification. So one of the issue that we do get if we try to fit a TURGM to this exact specification is what we would have is essentially a dependent variable that looks like this. And what we would get is a model that is predicting every single tie we observe at any point in time. But usually what we're trying to deal with, though not always, and we'll talk about cases that don't make this restriction, is what we're usually trying to deal with is tie change. And so what we're going to do to handle the problem of autocorrelation, or essentially the persistence of some ties across time, is to simply control for a prior version of the network. And so what the TURGM does, at least the first version introduced by Haneke, Fu, and Xing, is we're simply controlling a lagged version of the network into the model as an independent variable. We're going to specify it with an offset parameter equal to 1. And what that offset parameter is doing is essentially holding constant all prior tie observations without actually predicting their effect. And so it's treating these as a nuisance or a noise parameter. As a consequence of this, when we're using TURGM, we usually, again, not always, means that we're using t-1 observations. And so what we're essentially doing is conditioning on the prior network to predict the now network. And that's providing one burn-in period. So even though ERGM is extremely complicated, when we get to TURGM, we're really just adding this one term. And that term is the past value of the network. So we still have this extremely general functional form, but now we're conditioning on our prior network observation. We're predicting the next observation as a function of now and anything that changes in between panels. So we have yt minus 1 on the right-hand side of the equation to account for autoregressive processes. We're treating it as an offset, so we're not actually trying to absorb the effect of that prior time panel, though we could if we actually wanted to, in the traditional model, but instead we're just trying to hold it constant. And we'll talk a little bit later about what that implies for the change process we're examining and why that's meaningful to think about in the case of TURGM. We can interpret theta similarly as before. Again, what I really want to emphasize is we're still working within a framework that is very similar to logistic regression. But now what we're talking about is the increase or the decrease in the log odds of a tie forming. And so if we, for example, were to model a tergum with this type of functional form, and let's say we just have sex as the independent variable, a positive coefficient for sex would tell us that boys are more likely to form new ties between panels as compared to girls. A negative coefficient would mean boys are less likely to form new ties between panels as compared to girls. Or if we want to state it in terms of log odds, positive coefficient would mean boys have higher log odds of forming new ties between panels compared to girls. Negative coefficient, boys have lower log odds of forming ties between panels compared to girls. Again, we can exponentiate those coefficients for odd ratios, feed them through a logit link function to get predicted probabilities. It's all good. We're still working within a general logistic link function. Okay? Okay. Do we need clarification questions before we get into the first R component? Yep.
Just so I'm understanding, like, if you were interested in, might be like interested in the network at time one and do an ergon, and then like use ergons from there to understand how things change. Getting that conceptually right.
Sorry, you trade off at the end there.
Am I getting that conceptually right? Like you would initially just do an ergon to understand like the base network, maybe, and then the turbines would play just like change from that.
If you want to, yeah, so it depends. So if you're interested in both the base network or the stability and the change, you could treat it like that. We'll actually talk about cases of tergum later if we have time that can model the change and the stability separately. And so you could actually do it in a more general case of tergum, which we haven't gotten to yet, if you wanted to. But it could also be the case that your research question is fundamentally about change. And so one of the advantages of the network panel data is similar to panel data in general, which is that we're able to account for causal order if we want to, including like lag covariates, things like that. We're able to account for unobserved unit level heterogeneity if we want to stratify. Random effects are a little more complicated in the ergon framework, but if we want to stratify, we can do something like that. And so by going into the longitudinal framework, we get a lot of the same types of advantages we get with classic longitudinal data. But if we wanted to focus on what is the starting condition in addition to the change process, we're also able to do that. Do we have other clarifying questions?
Just about something you just said, you can also have random effects within there, and like, does that mean like testing and things like that?
You can. You hear my pause, it resonates. It's because right now we have two frameworks for dealing with random effects in ergom and tergum. One is a framework that only provides pseudo-likelihood, so we don't have exact likelihood estimates. Simulations suggest those standard errors and point estimates are a bit more conservative, and so some people like that, but we haven't derived maximum likelihood estimates for a frequentist tergum. We can get random effects in a Bayesian framework if you want to estimate this as a Bayesian model, which is also possible. And so my big pause is because it's not that we can't do random effects, but the random effects we usually like, which are like restricted maximum likelihood, empirical Bayes kind of things, gives us p-values as frequent as mostly, we haven't got there yet with tergum. Good question. Okay. So what we're going to do is we're going to switch over to R, and what we're going to start by doing is introducing a dyad-independent ergom, or tergum. And a dyad-independent tergum is a way of saying that our tergum is going to be reducing to a logistic regression. We're going to estimate the model without any endogenous stuff, because endogeneity gets weird in tergum. And we're going to interpret these results as reflective of some exogenous process. So we'll switch over to RStudio. And the three packages we'll be relying on today are StatNet, BT, ergom, and we'll do a little bit with ERG margins, but not a ton. So most of the estimation that we'll be talking about today and most of the tergum utilities we'll be using are implemented in the StatNet framework. StatNet is extremely flexible and has done a lot of work on developing tergum and ergom, but there's a specific estimation routine in BT ergom that can be very useful when you're dealing with large data because tergum can get computationally intractable very, very quickly. So to start, what we're going to work with is the alliances data. So this data are loaded from the BT ergom package. And what the data represent is a list of networks where every node is a country and each relationship is an alliance between those countries. And so the network is non-directed. We have 164 observations. We have 767 edges. And what we have here in terms of what the AllyNet is actually representing is a list of network objects. And so this goes back from the year 2000 to 1999 to 1998. I think it goes all the way back to 1980 or 1970, 1981. And so we have 20 observations of the same network here. Now, for simplifying purposes, what we're going to do is limit this just to the 1990 and 2000 network. And that's just because, again, the more panels we add to a TURGM, the more computationally intensive it gets. And we're trying to work with something that's a little more tractable. So usually in terms of data structure, when we're working with TURGM, we don't always have to, but it's often easiest to work with lists of network objects. And so all this code is doing is saying, take this first network object and the second network object and collate it together in a list that we can query with square brackets. So we can use the basic StatNet functionality to do some simple visualization with the gplot command. And so all this AllyNet square brackets 1 is saying is let's plot this very first observation of the network, which is what the International Alliance Network looked like in 1990. And so we can see some amount of clustering over here. There seems to be relative consolidation among what we might expect to be a few key factions. Maybe I'll blow this up a little bit. I have a bad habit of not zooming in on network plots. So we can see we have a ton of isolates around the perimeter. We have one kind of cohesive group over here. It looks like if we were to use like community detection lingo, we probably have about 4 or 5 major communities and then a ton of little isolates. Everybody's kind of connected over here through a couple of influential countries. We have one kind of brokering country here, relatively distinct factions here and here, and then a couple of alliances spanning. We can do something similar for the second network, which is just the alliance network plotted 10 years later. And so all we're doing here is extracting the second network and plotting what it looks like. And what we can see is it actually looks like there's been kind of a shift in these little factions. So we had this kind of removed cohesive community that was off in the margins. Now it appears to either have totally splintered or been integrated into this main network component. Previously, we had about 4 communities in the main component. Now it looks like we're up to about 6 communities in the main component. And so we've seen some amount of integration happening. So we can start to think about several hypotheses about what's driving network change or why do nations form new alliances with one another. And one argument could be it has something to do with polity or the level of democratization. So this polity measure is simply a measure of democratization that, don't quote me on exactly what it means, but the higher values mean more democratization, lower values mean more authoritarian tendencies. And we can measure it at both network panels, where we see kind of an upward or kind of a bimodal distribution with some strong state centralization, some high democratization, and then some folks in the middle. And at the second time period, or in the year 2000, we actually see a pretty strong lurch towards democratization in general, with a decrease in kind of the authoritarian side, a decrease in the middle people, and then a high level of democratization on the right-hand side. We can also think about alliances as being about capacities for defense. And so in this sense, the C-Inc measure is again capturing how capable a particular nation is at defending or sending troops if another nation were to be invaded. And so higher values we can imagine being especially influential alliances because people want to be protected, especially if they don't have standing militaries of their own. And we can again see that there's a somewhat shift in the distributional shape here. This one's a lot less dramatic, but there's a bit of a kind of a nudge away from a highly zero concentration in the prior panel. So in the language of TURGM, these are all exogenous attributes because they are not calculated on the network itself. What they are is provided as aspects of the nations, the level of democratization and the capacity for defense. And so now what we'll do is actually get into specification. So we can pull up the help page to get a sense of what the TURGM command is actually doing. And what we'll find is a lot of really extensive details about the potential estimation strategies and specifications we might want to use in order to fit a TURGM. In this case, what we're going to be doing is using the simplest instance of TURGM, which is one that reduces to a logistic regression, because we're only providing stuff that is assumed to be exogenous. Because TURGM is implemented literally using the underlying machinery of ERGM, we can actually find all the specification terms we might want to use in TURGM through the ERGM help pages. So Tergum doesn't actually have a separate suite of sufficient statistics or change statistics or endogenous covariates to include. What it instead has is an overlapping help page that aligns with the ERGM help pages we saw before. And so if you spend a lot of time in these help pages, like many of us, I was going to say enthusiasts, but maybe nerds is a better word, then you can find that we actually have a ton of support for a wide range of potential sufficient statistics, change statistics, endogenous and exogenous processes we might want to include. The StatNet group has also recently implemented a lot of utilities to specify your own interactions and your own endogenous statistics. So if there isn't something provided here that you want to include, you can write it yourself, and include it that way. So we'll use this pretty simple specification of Tergum, and we're going to talk about a handful of key quirks for the specification. So the first is, rather than using the ERGM bracket, we're using the Tergum bracket. The second is that we are specifically modeling the dependent variable. Again, recall that the dependent variable is not necessarily a network in itself, but is a list of networks with 2 entries. And we're modeling it with a wrapper here that says form. And form is short for formation. What it means is that we are predicting why new ties are created. So this is the simplest case of Tergum. But what we're going to talk about shortly later is how we can also account for asymmetric processes, including tie dissolution and tie stability. So right now, we're only modeling why new ties form, and we're representing it as a function using the formation wrapper. Everything we include in the formation wrapper are our covariates predicting why ties are more likely to change. So the edges term is acting as the intercept. This is the conditional baseline probability that a tie will change by random chance after we've included everything else. The node cov stands for node covariate. It works for undirected networks. And this is how we specify a continuous variable on the node level. So the node covariate for polity is telling us, is there an effect where alliances are more likely to be formed if it includes a node with higher, or a country with higher levels of democratization? The absolute difference in polity is how we capture homophily, or similarity in levels of democratization. Absolute difference takes larger values when 2 countries are further apart on their level of democratization. And so the lowest value that we can get, 0, indicates that 2 countries have the most similar level of democratization, and therefore might be the most likely to form an alliance. C Inc, again, is our defense capacity. The node covariate for C Inc is telling us our alliance is more likely to be formed with nations that have more capacity for defense. And the absolute difference is the corollary. Our alliance is more likely to be formed among pairs of nations that have similar levels of defensive capacity. We'll specify our estimation routine. One quirk about Tergum is we actually have to declare how we want to estimate it. The default most common practice is CMLE, which stands for conditional maximum likelihood. But because Tergum can often get computationally intensive, we have more flexibility over how we might want to specify it. In most applications, CMLE is kind of the benchmark we go against. So we'll run this first Tergum. And as you can see, despite all my complaining about how computationally intense Tergum gets, it ran in a second. And that's because right now, it's just logistic regression. So if we look at these results, what they're telling us is simply the logistic regression, bless you, results of tie changes. And so we have a baseline estimate of the conditional probability that a tie will change at random, which the negative 2.9866 is telling us it's extremely unlikely. We could feed that through a logistic link function if we wanted the exact probability, but it's going to be very small. The node cov polity is negative, and it's 0.04. And so what we can do is exponentiate this coefficient, and we get the odds ratio of a tie forming per unit increase in a nation's polity. So the odds ratio of 0.96 is telling us that each unit increase in the polity measure reduces the likelihood that alliance will form with that nation by about 4%, or I should say the odds that a tie will form with that nation by 4%. We also get this absolute difference parameter. This is how we're capturing similarity. And so this measure is capturing how close the polity scores of 2 nations are. The negative coefficient is telling us that as the absolute difference between nations increases, as one nation gets more democratic and the other gets more authoritarian, the likelihood of an alliance between the two goes down. By inverse, as two nations get more similar, democracies and democracies, authoritarianisms and authoritarianism, alliances tend to form more frequently as well. Below it, we also have the node covariate for conditional for the defense capacity. And interestingly enough, we're actually not seeing an effect from this covariate at statistically significant levels. If you're fine with p-values, that you may be skeptical. And we also aren't seeing a coefficient or at significant levels from the absolute difference in national defense capacities either. And so what this is suggesting, at least from our very, very simple model, is that nations tend to be choosing alliances based on kind of governing philosophies, authoritization and democratization, as opposed to necessarily strictly strategic interests, such as defense capacities. It's kind of interesting. So, we'll wait momentarily before we get into the marginal effects stuff, but we won't have to deal with that too much. Do we have questions about interpretation before we go back to the slide? Go ahead. Yeah, absolutely. So this is essentially the intercept in our model. And so what it's telling us is how many edges change between panels by random chance alone. And so if we were to take the logistic link function of this, it would tell us the probability by random chance that a new alliance will form, conditional on everything else. Good question. Yeah, thank you. Do we have other questions about interpretation before we keep going? Cool. This is where we can start to get a little weird in terms of thinking about endogenous processes. So what we've talked about so far is how specific cases of ergum and tergum reduce to logistic regressions. And these are things that we can handle in a very kind of straightforward kind of way. But a lot of the complexity and where the assumptions of tergum really start to shine is when we start trying to account for endogenous change processes. So let's think about, can I do two blackboards? Maybe not. I don't think we have the space anyways. Okay. So let's think about a change process that looks something like this. We have a network at t equals 1 of 4 nodes, and we have a network at t equals 2 between 4 nodes. And what we've seen is we have two old ties dissolve and one new tie form. And so one way of thinking about tergum in the context of two-panel data is that the network that we're actually modeling is the change network itself, meaning what is the network of new ties forming. And so in this way of thinking about it, our dependent variable is actually this network. It's the single tie that emerges between waves. And this is the network that we're modeling, because this is the only new formation we see. Now, the reason that's important is if we think about how endogenous characteristics are included in tergum, we are essentially saying that the characteristic is endogenous to this change process. So another way of stating it is that tergum assumes that ties form in parallel. There's one moment in time where all these tie changes essentially emerge in unison. Another way of saying it is that when we're capturing an endogenous statistic, the probability of a focal tie forming is assumed to actually contain some information, or at least is treated as containing some information on the ties that will form after it, which is strange. So this is often a reason why tergum is critiqued. So we can think about this as both a strength and a limitation of tergum. Because on one hand, this assumption of one of discrete time processes, meaning that we're assuming that we're containing all the relevant information for tie change within a single moment of time or in the past network panel. And that's a very limiting assumption because we're not actually accounting for the order of those tie changes. It could be the case that I form a tie with somebody, I withdraw that tie from somebody, but before I could withdraw it, somebody else formed a tie. All that information on what the structure looked like when the network changed is lost in Turgum, or at least dealt with by assumption. And that assumption is any measurement error we're getting is not correlated with what we're trying to estimate. That's a limiting assumption. But we also get an important utility. Because when we talk about Siena models tomorrow, actually I won't be here, when David and you guys talk about Siena models tomorrow, what you'll be talking about is how networks unfold as sequential changes occurring in a single moment of time. And what that means is some tie changes that are by definition occurring at the same time can't be captured by Siena. So if we're thinking about this in an alliance network, does a single nation enter into alliance by itself at once? Sometimes. But frequently there are coalitions between alliances. The UN formed because multiple nations were negotiating for some type of agreement to protect their national interests. By definition, those ties were negotiated and created in the same temporal moment. That's not something that's dealt with by Siena models. And so even though we get error on one side with a Turgum, we also get utility because we can actually capture that endogeneity in an explicit way. So this is not to say that either model is better or worse. Different capabilities, and in some cases, different assumptions driving those capabilities. So this gives us the two differences, which are the distinction between how we're thinking about a network change process, and specifically the effect of endogenous statistics. What I'm calling here between panel dependence and within panel dependence. So between panel dependence is essentially saying, am I forming a tie because the network structure looked a certain way in the past? In other words, am I essentially forming a triad or closing a triad because it was opened at a prior time point? And so the idea here is that individuals or other types of actors are nested in some type of network and are updating their tie change decisions based on prior network structures. That's kind of like a Markovian way of saying it, but we actually don't need it to be a Markov process if we don't want it to. And in this case, one of the things that's really nice about Turgum, when you're only doing a between panel model, it's still a logistic regression. And the reason is because we're meeting a sequential exogeneity assumption. My tie now is independent of my tie in the past. Where we start getting estimation problems is in the second waves of specifying endogeneity, and that is within panel dependence. Within panel dependence is, again, referring to ties that form as parts of complete structures in the unobserved temporal moment between panels. In other words, we are talking about the ties that form as parts of complete structures endogenous to this change process. So in a hypothetical account, say we see a triad emerge between panels as we have on the graph right up on here. What that's saying is the tie more likely to form when it emerges as part of a complete triad between moments in time? So it's not simply that a single tie is forming in an unfolding sequential order. It's that ties are forming in unison as parts of complex substructures. Again, this can be a very powerful utility. If we're modeling coalition formation, that might be what it looks like. We had no group in the past. We have a group now. Why? Because we got together and we organized. But it might not be capturing what we're often interested in, which is the sequential ordering. I am forming a tie with you now. I am saying you're a friend with me today because you said I was your friend in the past. That's a between panel dependency. Okay? And so these two processes are often conflated. And part of the reason is because as the time duration increases between two network panels, it becomes harder and harder for Turgum to accurately account for the between panel dependence. And that's because more and more tie changes go unobserved. But as our tie durations get smaller and smaller and smaller, our between panel estimates get more accurate. So we'll switch back over to R to illustrate what each of these processes look like. So now we're picking up right where we left off. And what we're essentially saying is there are a various number of ways where alliances between nations are created in the year 2000 or between 1990 and 2000 because of what the network might have looked like in the year 1990. And so one of the easiest, or one of the probably relevant ways that this might occur is because there might be a conflict between nations in the past. So two nations that are at war with each other are probably less likely to form alliances 10 years later, or within a 10-year period. So we can control for this network, which is the network of military conflict in 1990, by querying the 1990 value from the list of networks called WarNet in the data. And we'll create a new network called ConflictNet. If we peek at it, I think it's an adjacency matrix. Yeah, it is. We get a bunch of zeros and ones for the different nations that are at war with one another in the year 1990. Now what we're going to do is we're going to run this second TURGM, including a new parameter, which is between panel dependency, because it is representing what the conflict network looked like in the year 1990 and the effect it has had on alliance formation between 1990 and 2000. So we'll run this. And interestingly enough, or surprises me, I'll say, is we actually don't have an effect from two nations being at war with one another. And so this is suggesting that we don't actually have evidence that new alliances are going to form between 1990 and 2000, more or less likely, conditional on whether two nations were at war with one another in the past 10 years. So the other way we can specify between panel dependencies is by including lagged versions of the structural characteristics of the network we're actually modeling. So on line 108, what we're actually going to include is a second matrix called LSP. And what LSP stands for is lag shared partnerships. In other words, it's the number of mutual affiliates of two nations have in the past. So this is our specification of between panel triadic closure. Are two nations more likely to enter into an alliance if they share a greater number of mutual affiliates or other nations that are allied with one another? So we'll include this similarly to how we included the conflict network, which we specified above as an edge covariate. And what we'll also do, just for illustrative purposes, is demonstrate how you can calculate between panel dependencies in your own work if they're not provided neatly like they are with the AllyNet data. So here, on line 113, what we're specifying is a lagged effect from degree centrality. And so this is the number of alliances a nation has entered into in the year 1990. We're calculating it by simply using the degree command from StatNet on the first network we're observing, the 1990 network. And we're including it as a vertex attribute called lagged degree. Now the reason this is important, and I want to pause here to emphasize this, never do this with an endogenous statistic that is endogenous to the change period you're examining. If you include this, a degree centrality term, for the second panel wave, that's going to bias your ERGM estimates because we are no longer properly sequentially ordered. If we want to include that effect, we need to do it through the StatNet under the hood endogenous terms. We can do this only when we are properly lagging the temporal order. Okay? So we'll calculate this, and now what we have is actually a node covariate in our model called lag degree centrality. We can now run our TURGM3, as it's elegantly called here, to capture the between panel dependency of not only military conflict, but past shared partnerships in the alliance network and the overall number of alliances a nation was involved in the year 1990. So we'll run this. And again, very fast. And so we get our log likelihood very quickly. We've preserved sequential exogeneity, which means this is still estimated as a logistic regression. So we can summarize the model. And now what we can see is that we do have some evidence of between panel dependencies down at the bottom here. What we first have is evidence of our lag shared partnership with a coefficient of 0.49, which is telling us, if we exponentiate, forgot what I was doing for a second there. And what we get is an odds ratio of 1.63. And so this is telling us for each shared partnership that two nations shared in the year 1990, the odds that a new alliance will form between those two nations increases by about 63%. So for each nation, each mutual affiliate or mutual ally in the alliance network in 1990 increases the probability or the odds that a new alliance will form by 63%. Go ahead.
people I found, people have sort of told me to shy away from talking about their log odds because it's harder for people to grasp that idea, but I'm just curious about best practices.
Oh, this is like a slam. This is what I'm going to next. If we can pause this for a second, because I also happen to have written the paper on this, so in the ergon. So don't worry, I'm about to push my own agenda, and I feel like I've got the right crowd for it, so this is great. Did we? So we're going to get to this just in a second with the marginal effects framework. But the second coefficient we have here is the lag degree. And so what this is telling us is that each unit increase in the number of alliances a nation held in the year 1990 is associated with a reduction in the probability that a new alliance will be formed between 1990 and 2000. And so what we're essentially seeing is a tendency for nations to rely on triadic closure or mutual affiliates in the past to inform new alliances. But they're also, strangely enough, avoiding the nations that had consolidated alliances in earlier periods. Okay, best practices. Go ahead, Jim.
Is the avoidance effect, I'm just trying to wrap my head around some of the substantive pieces here. So do you interpret that substantively as because of an addition model, and so there's no additional ties among people you've already connected?
It could be the case. I think that's the analytic sociology way of saying it. My way of thinking about this is between 1990 and 2000, we had a major political realignment between Western nation powers and the dissolution of the Eastern Bloc and formation of African Union alliances. And so I think part of it is because all the prior ties in 1990, right after the Cold War, or the Berlin Wall fell and the Soviet Union collapsed, a lot of it is kind of restructuring over here, and the prior alliances existed primarily in the West, which were essentially at the threshold you're talking about. That's my interpretation, but I'll be honest, I have not dug into it. Good question. Okay, so interpreting effects. So I will caution you by saying this is me pushing my own agenda. So not everybody agrees with me, but I think some people do. So what we've talked about so far is log odds and odds ratios. And one of the weaknesses of odds ratios is it's all on a multiplicative scale, right? So if we have a very low probability to start, we can have a massive odds ratio of like 100. And it's not actually that much of a change in the probability of a new tie because we have a low base rate. So one way of handling this is by estimating marginal effects. And so the ERG margins package I developed with the idea of trying to make marginal effects interpretations more plausible in TURGM and ERGM more generally. It also dealt with what's known, the second advantage of marginal effects is not just interpretation, but it deals with the problem of scaling or non-collapsibility. Have people encountered this before? Okay. What it refers to is any nonlinear probability model, including a logistic regression or a probit regression, ERGM is just one case, the variance of any unmeasured term or model specification gets absorbed into the coefficients. And so what that means is even though our Z statistics and our assessments of significance are not being affected, the size of our coefficients is either being inflated or deflated in proportion to whatever the variance of the omitted term is. And so when we want an effect size interpretation, we need to do something to account for that variance inflation or deflation. Marginal effects is one way. The other reason this is helpful is because the scaling and non-collapsibility problems can bias your interactions, and they can prevent you from comparing coefficients between models. Marginal effects are robust. And so if you're interested in looking at the change in the effect of a variable or the change in a coefficient between models, marginal effects can do it, coefficients can't. Average marginal effects as well, yeah. So either the marginal effects mean or average marginal effects can do it. Or if you're looking at an interaction, marginal effects can do that as well. Oh, I need another whiteboard. Okay. So for those of you not familiar with, so that wall is a whiteboard? Duke. Okay. Okay. So the idea behind a marginal effect is we have some probability of a tie forming as a function of some input variable. And the issue we have with the coefficient is in a logistic family form model, this is a nonlinear function that plateaus at higher levels. And so with the marginal effect, what we're trying to do is figure out what is the slope at a particularly representative point. And so rather than summarizing the effect on a multiplicative scale, which is what the odds ratio is doing, what the marginal effect is doing is simply saying, what is the change in the probability of a tie forming at a given location in the distribution of variables? Now we can pick that location in a number of ways. One way is to hold the marginal effects at means where we're simply calculating the average of all our covariates and then getting the marginal effect for the one we care about. Another way is to pick a representative value. We might not actually care about the marginal effect for everybody. We want to know the marginal effect among authoritarian or highly democratized nations. We can do that as well. Pick a particular point in the distribution, fix the values at where we want them to be, and then calculate the marginal effect. Sometimes the simplest and often the most preferred way is the average marginal effect. And what we do here is rather than say, why do we care about representative values, we could get the marginal effect at every observed value and just calculate the mean. And if we do that, we can say, what is the change in the probability of a tie given a change in a covariate holding everything else at the values that are observed? Now, the main advantage of the average marginal effect is your statistical assessments of significance, or z-values, are actually always going to be the same as your coefficients. The disadvantage of the average marginal effect is when you're in big sample spaces, as you often are with TURGM, or high-dimensional models. It takes a really, really long time. Not really, really long always, but often. And the standard errors take longer. And so sometimes it's useful to simply hold things at representative values. So the ERG margins package implements both marginal effects at means and average marginal effects. And the only difference is after ergm dot, do you write AME or do you write MEM? That's the difference. Everything else is the exact same. Not under the hood, but in terms of what you guys deal with. That's the exact same. And so what we're going to provide to the ERG margins package ergm.mem is the model we're working with, TURGM_3, and then the variable we want to interpret. Here, this is the lagged shared partnership term. And so the way we can interpret this, and apologies for those who can't see it, is the marginal effects at means is 0.005. And so what that's telling us is for each additional shared partnership two nations had in the year 1990, the probability of them forming a new alliance between 1990 and 2000 increases by about 6 percentage points, while holding everything else at means. So this is essentially practically the exact same interpretation as a coefficient, except we get it on the scale of probabilities as opposed to odds ratios or log odds. So we'll do the same thing for the lagged degree centrality, calculating ergm.mem. And here we get a negative marginal effect at means of negative 0.00001, which is telling us that each additional alliance that I had in the year 1990 is associated with about a 0.01 percentage point decrease in the odds that a new nation will form an alliance with me between panels. So the interpretation is the same as we had before, but now we are talking about the increase or the decrease in the probability rather than the odds. All good? I prefer it. Some people still interpret odds ratios, but the tide is shifting, and it depends on the field. So if you're in a field where people are anti-odds ratios, that's cool. Go marginal effects. If you're in a field where odds ratios is still acceptable, be an opinion leader. Be an early adopter. Do it for me. Then you can still get away with odds ratios, but this is also an option, especially if you want to compare between models. Then you really need the marginal effect. Mm-hmm. I actually prefer the average marginal effect, but it takes a little longer. So here, it's not massive because our data isn't too large. But if you're working with like 20 network panels or longitudinal data of something like 1,500, 2,000 people, it doesn't actually take much because the size of the network increases exponentially as a function of each node we add. And so it actually has a pretty low threshold to start being annoying. And so it really depends, because some people, what they want to do is report essentially the marginal effect for every variable in the model, at which point even slightly longer runtimes become irritating. But if you're really just trying to pull out one relationship and say this is what the marginal effect is, it's not going to cost you too much usually. I will say one of the bigger bottlenecks is how many terms you have in the model. And so if you have something like 20, 30, 40 variables, which is not uncommon in TURGM, it can actually become really prohibitive to do it the average marginal effect as opposed to the marginal effect it means. But since you asked, this is the code for the average marginal effect right here. We're just changing the AME from the MEM. And as you can see, our interpretation for the lag degree centrality doesn't change much, but it isn't the exact same. So now, rather than a decrease of 0.0001, we get a decrease of 0.0003, per increase. So that's actually about twice the size. It's a relatively small starting value. So whether you make heads or tails of it, that's up to you. But there is a little bit of a difference there. And so the results aren't guaranteed to be the same. Substantively, they're usually pretty reasonable approximates. But there is a decision to make about what you think is the most representative quantity. Good questions? OK. So we've talked about between panel dependencies. And now we get to do the really more tricky thing, which is talk about the within panel dependency. And so what we're going to include here in Tergem 4, and this is the one I warned you guys, run it ahead of time because it takes a while, is we're going to include an endogenous statistic. So this geometrically weighted edgewise shared partnership term is a nonlinear term for triadic closure. What it's telling us is what is the effect of a closed triad per each additional triad with diminishing returns. So the idea here is that we're essentially penalizing additional mutual affiliates so that if we have 3 or 4 additional mutual affiliates, each, the third and the fourth, aren't contributing as much information as the first and the second to tie formation. We're picking, we can actually allow this to vary arbitrarily. Oftentimes that creates longer runtimes. So frequently what we do is pick a parameter and fix it there to speed things up, and then change that parameter around a little bit and see how robust our results are. Usually what we're trying to do is find a parameter that has good model fit and is relatively robust in terms of estimation. So when we include the GWESP term, what we're specifying is an endogenous triadic closure statistic. It's analogous to the lagged share partnerships we have up here. But the difference is this is the between panels dependency. The lag shared partnerships is modeling the effect of us having a mutual affiliate in 1990. The GWESP term is modeling the probability that we form a triad all together between waves. And so these are the emergent triads. And when we run this model, the reason that we're getting really long runtimes is because the model no longer reduces to a logistic regression. Instead, what we have to estimate is the aggregate level model, which involves a very long sequence of Monte Carlo simulations that all have to be updated and can potentially get stuck in local peaks and get problems related to collinearity and all these things that make estimation more difficult. And so it's usually these endogenous terms, specifically the within panel endogeneities, that cause estimation issues in Tergem. So if you followed along with me and you ran it ahead of time, what we can do is summarize the main results. And what we'll see here is we actually do get a positive and pretty powerful effect from the geometrically weighted edgewise shared partnership. But what's interesting is that effect actually isn't eliminating the effect of lag shared partnerships. There seems to be something going on here where we're both conditioning our alliances on the alliances that already existed and our mutual affiliates, as well as coalition formation. And so if we're thinking about how these alliances actually are forming, especially in the 1990-2000 window, it appears to be consistent that we are creating new alliances based on who we had alliances with in the past. But we're also getting together in groups and creating new alliances or creating new coalitions. And if that might sound surprising, I want to emphasize it's actually consistent with something we just saw earlier in the descriptive results, which is these new groups forming over here, which did not exist in 1990. And so any effect of all of these nations getting together and forming alliances with one another as part of coalition building would not be captured by the lag shared partnership term because those dependency structures did not exist in the prior panel. And so even though it's a little strange to think about, it is totally consistent with our data and specifically the unobserved change process that we're trying to capture. So in terms of interpretation, this, again, we can exponentiate. The interpretation of the geometrically edgewise shared partnership term is often a little weird because what it is essentially, I don't want to exponentiate this because it's going to make your eyes bulge. But what it's telling us is each additional increase in a shared affiliate between waves is associated with a new alliance forming, but there are diminishing returns to every single affiliate we create after that. In other words, if we share an alliance with one nation, that's going to bump up our probability of creating an alliance by a good amount. But if we share an alliance with 2 nations, well, the marginal gains from that second alliance actually aren't that helpful or as helpful as the first. And for every additional mutual alliance we have above that, it continues to decrease. So I'll get the marginal effect because I don't think it makes your eyes pop as much, but I don't remember. Yep. So here we actually have a quite small marginal effect. And so even though our coefficients are quite large, again, this is one of the reasons odds ratios can be misleading, because it all depends on where things are at the mean and what the distribution of change statistics are. The effect at the margins for the average observation is actually not massive. It's smaller than the past dependencies we observed. And so this is telling us that we do have an increase in the probability of a tie forming for every additional triad closed between waves, but the marginal gains are actually quite small. It's something like a probability of 0.000007. Okay. So one other quick thing I'll do to plug my own research a little bit is when we get convergence issues, oftentimes what's driving the convergence issues is collinearity problems. And here we actually have a few telltale signs of collinearity. And where they're occurring is first we have a massive coefficient here, which isn't necessarily wrong, but it's something to account of. But the bigger concern are these two. So this is the node covariate for national defense capabilities and the absolute difference. And their standard errors in their estimates have skyrocketed from prior models, where they already were reasonably large. And so what this is often telling us is there's not actually a lot of unique variation for them to work with, and there's a good chance they're collinear with the within panel dependence GWESP term we just included. So we can evaluate this using the vif.ergom command, which also comes from ERG margins. And this will tell us exactly what the variance inflation factors are for every term. And what we're seeing is that the node covariates for military spending or defense capabilities and the absolute differences are about 176, which is insanely large, especially if you're in a generalized linear framework where you're like, I don't want a VIF more than 4. 176 is a bit bigger. Now, ergom is actually pretty tolerant of high correlations, but not necessarily this tolerant. And so when we're getting to this high of levels, one way we could potentially handle this, if we're trying to fit the within panel dependency, is to try to omit one of these terms, maybe the absolute difference or the node covariate, depending on which you think is less relevant on theoretical priors, and try to re-estimate the model, see if you can get a bit more traction. Okay. We have about 20 minutes left, so I want to go a little quickly here to show you some additional utilities we have of the TERGM specification. And so we might move a little briskly and skip a few slides. So the first thing I want to show you guys is how we can do model fitting. And so in the world of ergom, the way we typically fit models is we simulate data from the model we actually have and see if the structural characteristics of those networks are consistent with the structural characteristics that we actually observe. Usually what we're using is the terminal network as the goodness of fit criterion, meaning that we are comparing our projections to the second network panel, but we can use other panels if we want to. So BT, ergom, and StatNet both include a goodness of fit command, and they contradict one another. And so what we're going to do first is just detach the BT ergom package and reload StatNet, so we make sure we have the right version of goodness of fit included. We'll run the GOF command, and as we see R is worrying, what it's currently doing is simulating a distribution of networks from the model that we fit. And what it's doing is on every single network, it's calculating the distribution of edgewise shared partnerships, the degree distribution, the distribution of ties connecting focal statistics, and comparing those to the data we actually have. So if we run line 190, this is the output from the very extensive procedure that we just got, where StatNet is reporting here how many edgewise shared partnerships we actually saw versus how many were contained in the simulations versus the data. And even further up, we get summary statistics for other things condensed here. This is just the edgewise shared partnerships, but it's a lot of output is the point. Most people don't report this table or spend too much time looking at it. What we usually do instead is plot it. And so we're going to use this plot.gof command, which inherits from ergom. My R is a little outdated, so you might not have to do some of this par mfrow thing here. But if you are having problems plotting it, just replicate the code up front. And what we're going to first do is just change the plotting margins so we can plot all the goodness of fit stuff we want to. And then we're going to use the plot.gof command from the ergom package. And what it's going to give us is plots or figures summarizing the performance of our model with respect to the structural characteristics we observe. And so what we're seeing up here is the model statistics are reporting how many ties or the proportion of statistics simulated from the data that align with the number of ties connected to those statistics. In other words, what are the edge counts for every single statistic we observe? The black line is tracing our observed data. The blue dot is the mean of the simulated distribution. The black band is the median, and then we have our Box and Wister plots. And so what we're seeing is for the distribution of statistics, it falls in the range, but it's not as centrally located as we might hope for. In terms of the geodesic distances, the path lengths between different nodes that we're seeing in the network, it's doing pretty reasonable. We're getting the general shape. Most of the observed data is actually falling between the Box and Whisker plots. We're capturing the right amount of disconnected components, which in this network is actually quite critical because we had all those isolates we were observing in the first two visualizations. Where our model sucks is in the degree terms and the edgewise shared partnerships. So here our degree distribution is not great. If that was the only thing that was wrong, it might not be fatal, but it's not good. And so this is definitely something that would raise eyebrows. Partly what the model's doing is overestimating the degree centralities of nations between 2 and 14. And it's underestimating a huge spike here where some nations have a ton of connections and are accounting for a lot of alliances. And so we're missing a lot of the nodes that are drawing a larger number of connections. The other place we're doing really, really bad is our simulated networks are dramatically underestimating edgewise shared partnerships. And specifically, we're missing this high level of clustering that we saw before with all of this coalition building. Now, if this were a research application, I'd be extremely frustrated because the first step you take in trying to fix these goodness of fit issues is to include a term that captures that statistic. So if I were to not see the model we just fit, and I looked at this plot, I'd be like, oh yeah, you've got to include a term for triadic closure. We already have 2 terms for triadic closure. This is bad. I would be upset about this in practice. The other thing that we could do that we haven't done yet is try to include additional terms to capture degree centrality. So there are additional parameters we could include, such as geometrically weighted degree terms that account for the distributional shape of degree centrality within the network. And we could include those as well with the hope that this fixes something over here. If I were in practice, just to give you some guidance on what I would be thinking about if I saw this, first, I might say it could be the collinearity problem we just encountered. Maybe we don't have an accurate estimate, and that's what needs to change. And so the first thing I would do is kick that out. I might also try removing the decay parameter, or the fixed term we had in the GWESP argument, in an effort to allow for a more flexible edgewise shared partnership distribution. The other thing that I'd be trying to think about is try to bring in additional knowledge or theoretical priors. So one of the things that we often get here is when we see a spike in the degree distribution, we might say that's because we didn't include the degree term. But what it can be the case is it can actually be selective preferences on other attributes, not just degree. And so it could be the case that there's some other exogenous characteristic of nations. What is their productive capacity? How much money do they have? What is their educational training that might drive migration or create other political interests that could actually be creating spikes in degree centrality at a specific location? And so what I want to emphasize here is even though the knee-jerk reaction when we see these things is to control for that term, degree or edgewise shared partnerships, it can actually be misspecification on other terms that create the lack of fit. And so that's always something worth exploring as well if we have the data and capacity to. Jim?
So in this case, I think as an illustration of how to do this, agree 1,000%. In this particular case, isn't it partly just because this is actually a one-mode projection of a 2-mode network? So I join NATO, I join these alliance structures. If I'm an alliance with NATO, I'm an alliance with everyone else in NATO. And so it's effectively, under the hood, a 2-mode network. It's the cliques that's creating these spikes.
I think that's reasonable, yeah. I think for this alliance network, it could definitely be the case. And one of the things that's nice about Turgum is we can do it in the bipartite sense too. So if we have this data, which I don't in particular because I didn't create these data, but the underlying data generating it is there's actually a certain alliance event that we can model within Turgum as a bipartite network. And presumably that should help us deal with some of this. We're also, because Turgum is very flexible, we could include edge weights to try to account for that redundancy in the original bipartite network and offset some of the projected clustering that we almost always get. And that could be another way of trying to handle it too. Yeah, good point, Jim. Okay, so we have 10 minutes left now. And I want to talk about two more things. One is alternative estimators. So what we've talked about so far is, lost my train of thought. What we've talked about so far is how we can specify within panel endogeneity and how we can do so with Markov chain maximum likelihood estimation. We also talked about how many problems that can create. Now, one way of actually dealing with this is to not estimate the model with Markov chain maximum likelihood at all. So something that Skylar Cranmer and Bruce Desmarais have shown is that in sufficiently large networks, you can actually do a bootstrap logistic regression to get TERGM estimates. And so this is the method that BT-ERGM includes. And so if we respecify our model in BT-ERGM, we can load BT-ERGM in. And BT-ERGM has slightly different requirements for how you provide data. So we're going to just include the lag degree statistic as a covariate at wave 1 as well. It's actually not going to be included in the model, but BT-ERGM wants it there. And we're going to include this. And next what we're going to do is actually do a bootstrap estimation of our TERGM. And so the BT-ERGM command, you'll note, something that's actually very restrictive about BT-ERGM is we're only allowed to model formation. And so we can only model the new ties. We can't deal with some of the more precise modeling capabilities we're going to talk about in a moment. But something that makes it more useful in terms of estimation is now what we're going to do is simply just bootstrap the data, estimate logistic regressions to everything, and then report those estimates. So what we're using is a BT-ERGM command. And rather than specifying the estimate as MCLE, we're going to specify R equals 500 to represent 500 resamples from the data. We're going to specify parallel as multi-core just to speed things up, and 3 processors. Now, as this runs, I want to urge a word of caution with BT-ERGM. The key term here is bootstrap pseudo-likelihood is a consistent estimator, but it is also a biased estimator. And what that means is that it only provides valid results when our data are sufficiently large and we have sufficiently long time periods. In this particular case, the results from our bootstrap estimation are not going to agree with our Markov chain estimation. And the reason is we have 2 time periods of 160 nodes. Bootstrap pseudo-likelihood is intended for more like 5 panels at the minimum, thousands of actors. And if that's the case, we can actually get consistent estimates in a reasonable amount of time with bootstrapping, where our Markov chain estimates probably break down. But the trade-off is we need to remember it's only contingent on the amount of information available. In small samples, these estimates usually aren't reliable. I'll put another plug here. ERG margins works with bootstrap ERGM. So we can do it that way. Do we have any clarifying questions while this finishes running? Yeah. This sample is going to be a problem. So even the data we're working with, I think usually I don't feel safe bootstrapping till I have over 1,000 nodes. And even then, if I have fewer than maybe 4 panels, I'm probably not going to want to consider it unless I absolutely have to. Yeah. Those are the benchmarks I use. I don't think there's actually an established precedent in the literature, but it passes my sniff test. OK. So in terms of the bootstrap ERGM, we get our point estimates. But since these aren't normally distributed statistics, go ahead. My preference is at least 1,000 nodes, and what's that? I prefer at least 4. Mm-hmm. Again, that's my criteria. That's not a standard in the literature, so I want to be clear. So as we can see, we get our bootstrap means, we get our point estimates. This is the average of the bootstrap distribution. This is the point estimate from logistic regression. Recall that what I said earlier, usually our pseudo-likelihood estimates of coefficients aren't off by that much. And so sometimes people interpret the estimate, sometimes it's the bootstrap mean. We don't get our critical values directly. Instead, what we get is our bootstrap credible or confidence interval, based on the bootstrap distribution, because we might not have normal statistics. And what I really want to emphasize here is the difference between our Markov chain estimates, or Markov chain Monte Carlo estimates, and our bootstrap estimates. So the edges parameter from our formation model with Markov chain maximum likelihood is about 3 times the size of our bootstrap estimates. Our polity parameter also about 1/3 of the size in our Markov chain Monte Carlo model as compared to our bootstrap estimates. Polity parameter also way off. Edge covariate for conflict is quite different. And in this case in particular, with our Markov chain Monte Carlo model, we had concluded that histories of conflict actually don't affect alliance formation. And in our bootstrap model, we would conclude histories of conflict increase the likelihood of alliance formation, right? So the implications of our estimator can actually be quite consequential. In this case, because our data is so limited, I would not trust the bootstrap estimates. Even though our Markov chain Monte Carlo model didn't fully converge, it was at least consistent with our earlier pseudo likelihood maximum or dyad independence model, and that gives it more face value in my eyes. Whereas our bootstrap results are very, very different. And so this, again, is to just emphasize bootstrapping can be an extremely useful tool, especially when computational resources are limited. You're working with big data. If it's digital trace data, some big data type thing, that's great. But the substantive implications can be quite impactful, especially when we're working in small sample spaces. Okay. All right. We're going to have to run through the last bit of this a little quickly. But there's 2 final capabilities of Turgum that I really want to emphasize to you. And what we've talked about so far is how we can think about Turgum as a limiting case or restrictive case on tie formation. But there's actually multiple ways a network changes. So I forgot my marker. So if we go back to what I wrote on the board in this minimal change network example, only 1 new tie forms between these 2 panels. But actually 2 old ties dissolve. And so what that means is we can actually think of a second change process where the ties represent the ties that are no longer there. And we can treat this second change process as a second dependent variable. Now, if we're thinking in this framework, this is what's called a sturgum. It was developed by Pavel Kravitsky and Mark Hancock. And it references a separable temporal exponential random graph model. And this is exactly why in the Turgum command, we have to tell Turgum that it's a formation model if we want to treat the new ties as the dependent variable. But what we can also do is include a second model in the same equation, wrapped in the dis parameter. And what this dis argument is saying is model the effects of each of our covariate on a tie dissolving. So what we're going to do in this Turgum is actually model both processes at the same time. I've omitted the Guess parameter so that we only have a logistic regression, not something more complicated. And we're going to run Sturgum 3. And what you'll notice is, once again, it actually runs quite quickly because we are working in a sequential exogeneity state. So the first thing I want to draw attention to, even before we interpret results, is that the formation side of the equation actually provides the exact same coefficients that we saw before. So we're just adding on to it by adding a second model for the ties that dissolve. But now what we can also interpret is the asymmetric effects, or essentially what is making it more likely for a tie to dissolve, not just for a new tie to form. And here we start to see some interesting things. So for example, node covariate polity is telling us that more democratic nations form fewer new ties, but those ties are also more stable. Because node covariate polity, even though not significant, is telling us that, that alliances are less likely to collapse for more democratic nations as well. We can also start to see kind of effects on, or potentially asymmetric effects, such as the absolute difference in polity to similar levels of democratization create more ties, and the alternative side, which is do more different levels of democratization cause old ties to disappear. I'm trying to see if there's anything else interesting that pops out. Node covariate military spending. So for our defense capacities, we didn't see nations forming new ties with nations that had high defense capacities. But we do see nations essentially maintaining the ties they already have if their connection has high military spending capacities or high defense capacities. And so there's a premium on maintaining those strategic alliances that support, essentially, that can support you in terms of military conflict. We also sometimes just get weird stuff. So for example, we get the negative coefficient for tie formation. People with more, or nations with more alliances in the past are less likely to create new ties. Also, nations with more alliances in the past tend to hold on to those ties quite well. It's kind of interesting. If we want the marginal effect, we can again get it, and we can do this to essentially compare the asymmetric effects. So this is the marginal effect at means, telling us that for each additional alliance we have, each additional alliance we had in 1990, it decreases the probability of a new alliance forming by 0.01 percentage points. But each additional alliance that we have also, let me say this right, decreases the likelihood of an old alliance collapsing by 1%. Okay, I'm out of time, so I'm going to just do one last thing, I swear, and then you're done with me. And that's just to circle back to what I said at the beginning, which is that we can also model stability and change as separate processes. And so far what we've been working within is the classical case of Tergem as a formation model, and then adding dissolution onto it. But another way of thinking about this is that actually we have two types of ties going on here. One is the ties that are persistent across time, and the other is the ties that change. And so Tergem allows us to actually model the effects on tie stability and tie variability separately. So this cross-wrapping is essentially predicting the likelihood, or predicting the probability of observing a tie given that it exists at multiple panels. Whereas the second parameter here, the second argument, the change parameter, is modeling the probability that a tie changes. Now I want to be clear because this change parameter is a little weird. It's modeling the probability that a tie changes in either direction. It could be formation or dissolution. Okay? So we can fit this model again. And what we get, again at the top, the cross-sectional is telling us what is the likelihood that a tie will exist at any point in time or persist across time. We're going to see it at multiple observations. And the bottom panel, what is the probability that a tie is going to change? It could be formation, it could be dissolution. And so a positive parameter on the change side is going to be saying a tie is more likely to change between waves. A negative parameter is saying that a tie is less likely to change between waves. And finally, because that interpretation is a little weird, I wanted to show you can actually replace change with formation. And so this model that I'm running right now, Sturgeon 3C, is giving us effects on the cross-sectional distribution, was the probability of observing any tie, and effects on the probability of tie formation, what is the probability of creating a new tie. And those are the same types of coefficients we interpreted earlier. The only word of caution, we cannot include cross-sectional dependence, formation, and dissolution all at once. We get a perfect collinearity problem in the same way we get an age period cohort problem. So we got to kick one of them out of the model, but we can always choose two. I'll end with that. Thanks, y'all.
My last questions, Scott, before we...
Yeah, Tom.
Yeah, so lately I've been getting familiar with Tergem-based applications like simulations, and there you specify a distribution parameter. And I'm curious, right, like if one of the most basic things you say, like this is the typical relationship, as far as like actually after Tergem's here, how is that? I guess I'm curious about the edge term in a dissolution part of the model, right? And then as far as these applications where you specify a typical duration, like how does that get implemented here?
Yeah, that's a really good question. So edges term in a dissolution model is telling us the probability that a tie will dissolve by random chance.
Okay, that's just the
Exactly right. So essentially what we're doing is saying every tie that does collapse, treat it as a tie in itself, and that's the tie we're on. In terms of incorporating duration, I'll be explicit in saying I haven't worked a lot in this area. I know, however, that the longitudinal exponential random graph models that Tom Snyder's have developed to try to account for continuous time processes and account for durations as well. I know Pavel Krivitsky has also developed models in Sturgeon that attempt to incorporate tie durations. But in terms of the actual explicitly modeling of it, it's not something that I've done, and most of the Tergens I've worked with have been strictly in the discrete time space, and so they haven't dealt with this duration.
Thank you, sir.
appreciate that, yeah. It's really hurt here. We're kind of decide, do you want to do a one projection, where it's on programs, or do you stochastic models, and try to figure out which one is the right approach. I think it's basic. I can use things,
Full context.
Oh, yeah, sorry. So I'm a higher education scholar, and I study social support, personal well-being networks of students, and how that relates to their connections, well-being, those kind of things. So there's a data set through the University of Michigan. It's called the Healthy Minds Study. And they look at about behaviors, but they do collect relational data. So the bipartite network is actually 15 years worth of basically social support networks. So they ask college students, who do you go to for social support? They can nominate friends, family, faculty, advisors, and so I have these 2 more networks of support. And so initially what I might need to do is collapse them into a one-hole projection of the post-support networks. Like faculty and advisors who are co-nominated.
Okay, so is it the individual faculty advisors?
Yes, yes. Yeah, and seeing the evolution of that over time. But it would be a value data set as a one-hole projection, if I'm understanding that correctly. And I don't know that works internally.
It does.
Oh, you can?
Yeah, it just makes things, the estimation problems get even worse. So that's a good news.
Okay, so you can do value data for terms. The interpretation, I have to think about it.
Yeah, so the number of shared advisors or mentors.
Yeah, because likely the trials already exist.
I can just plug in my computer. That's probably the easiest
You
way.
can just plug it in right here. I'll use this one from here.
Okay.
You can just switch
Are you
the thing.
interested
There we
in
go.
the faculty being selected as advisors?
Yes, as in their support network, yes.
So you're more interested in the faculty selection than the post-selection?
That's a good question. I would say
And the reason is because when you're projecting to a one-node network, you're creating ties and shared distribution. And that
Actually, don't plug it right now.
All right. Is this working? I don't think this. I think the battery might be dead on this. Well, it doesn't say so. It's muted. Can you hear me now? Can you hear it all now on this thing? Trying it now. Trying it now. Trying it now. Any chance? No. I think the battery's dead or some such. I'm getting. Yeah. I don't think it matters that much, so I can shout. So.
Well, we could hear it.
Oh, you could hear it?
Yeah, we're just, let's see. Let's try. I think it needs to. Yeah, try talking now.
All right, can you hear now? Any chance now you can hear it back there? Margaret, you hear it now? Maggie, anybody? Emily? No, they can't hear it. Can you hear it now? If I shout, you can hear me, right? Amen. There we go. All right, I'm not sure this mic's working that much. We'll keep it on anyway. All right. The plan now is just to do we've had a long day, and so we figured we'd end the day with a little bit of dessert, which is network visualization. And so this is, for many of us, the reason we got into networks, or at least one of the first things that, maybe not the reason we got into it, but at least something that first captivated our imagination, was these kind of cool pictures, right? And if you find yourself in the consulting world or doing any of this kind of stuff, at some point in the day, someone's going to say, can you make me a network picture? That's there's a lot of that we end up doing. So if you're going to be in the business of making network pictures, at least have a little bit of idea about why you might do them and why they might be fun. So we're going to do a pretty quick version of why we make pictures and sort of how to make a good one from a bad one. Like many of these things we've done in this workshop, it's a lot easier to do something bad than it is to do something good. And the way we do something good is a little less instructive than the way you can do. So there's no actual formula. This is making pretty pictures is something almost realistically of an art over a lot of the other things. So networks have been pictures have been foundational to networks from way back in the beginning. So the earliest sort of network-like images are coming out of kinship diagrams, and this is from 1871 in this case. There's also the other area where you see a lot of sort of diagrams a lot like this, are bureaucracies, right? So bureaucracies have been around forever, and so this is a good example of an organizational chart from 1921. But for many of us, the ones that are really sort of captivating came from Moreno's sociograms. And he has this wonderful book, Who Shall Survive, and a number of papers in the journal Sociometry, which have these images. And when you can kind of imagine when these things were first written, and as you read the descriptions of them, it really is this, like the first shot through a telescope or the first shot through a microscope. They're looking at this and they're just amazed at the extent to which they're seeing things that otherwise, and it's so clear that there's something else there that they wouldn't see otherwise. We're going to come back to this particular image quite a bit today as we sort of go through some various options. But he did it with all kinds of different elements. The place where I think a lot of these images, the original ones, really played very nicely was in community studies. And so the community study literature would send in teams of ethnographers into small towns, and they would try to ask people what's happening in those towns. This is Lundberg and Steele from 1938. And these images, this book is kind of incredible because all of these images that go off the page connect to another image on another page. So these things are actually very well done. And if you go through, you can see they have these sort of compiled edges where you're like this, M31 here is gaining all of the ties that are going off to another page. And if you read the book, you'll see that this is M31. So all of these ties here end up being connected to these sides. Those are those sets. So you could link these things across these different data sets. And there was an attempt to really document the social fabric of these communities in a way to try to understand, in this case, what the leadership structure of and what they came. This was a working steel town, and there was a very strong working class elite and a very strong working class and a very strong elite. But the city was being run by women, and so M31 was one of the, this Iron Lady of the town, and she organized everything else that was happening, and it sort of had this wonderful sort of sense that came out of the community study and became clear when you look at this kind of image. Quickly, though, people realized that once you have a little bit of an image, let's add more to it. And so there became this layering process where you're trying to add extra information. And so some of the early hand-drawn images were adding things like pie charts. So this was a neighborhood level map, effectively, of visits from one to the next. And the pie charts represent the extent to which people were coming from different places. Now, sadly, the network image has sort of in contemporary world has been a little bit co-opted. So now we've come to think about viral marketing in this case, and this was literally a case where you're trying to use a network image to do something like show how to use hand lotion, if I remember correctly. And sometimes it's just like a complete, silly or almost dangerous. And so, and this is a case, this was a study of the conflict dynamics in the Afghan conflict, put together by some folks at DoD or some consultants to DoD. And you might wonder what a quagmire looks like. There you go, right? So there's an image of it. And of course, you get downright spoofs of the real thing. So this is someone making a joke out of the Christakis and Fowler work about how your networks, how obesity is contagious. I still would love to know how someone managed to make, because if you look closely, like it's not just a random scattering of points. They actually did tie points together in here somehow. So I mean, someone spent a lot more time doing this than I would have imagined. But lest we think, right, that only journalists do bad network visualizations, the sad part is that bad network visualizations are ubiquitous in this field. So this is a published image in a journal. I don't remember which one I got it. I hid the names to protect the guilty. But it's a case that, there's oftentimes people feel that they have to put a network image in, and just like whatever default shows up out of their screen, and they're using, they throw it in this set. And this one, if you know something about the context, maybe you can tell a story, but it's certainly not compelling in itself. So what I like to do is figure out how you can, what we hope to get out of a visualization. And a good visualization should be some kind of a gut check on the social reality you're trying to describe. It should communicate something that is intuitive and interesting and immediate and allows the authors and the readers to get something out of that image that would be harder to describe any other way. And so you've seen this diagram already a couple times throughout the course of this workshop, and people have picked up on it in many places because it's such a nice illustration of this conflict between racial integration and actual social integration, that we think we're doing everything right if we can get people integrated in the school door, but if the social networks are segregated, you've kind of lost the battle. And so that story pops out kind of nicely by just knowing what this image looks like. And so having that has been fairly compelling, and people have liked it. And so the question is, what is it sort of under the hood that makes a network compelling? And I have a whole sort of theory about how to do this well, but I want to just put a couple of ideas out there. One is that if you think about scatter plots, this is the classic series, each three of these scatter plots have the exact same regression fit, so you can fit the same lines, or the same slope, the same standard error, all that stuff to them. But the visualization tells you something that you wouldn't see from the regression summary statistics. And that's part of what a visualization does well. A visualization captures the gist of the whole thing in a way that a summary statistic does not. And it works in a scatter plot because the axes are meaningful. And so if you think about this particular element here, the y-axis and the x-axis, they're both ordered arrays. You have the exact same information if I just permute the x-axis. Right? There's nothing inaccurate about this display of information. All the data points could be recovered, but it's not intuitive. It doesn't mean anything. And so the meaning of a scatter plot comes from the fact that the scatter plot has a fixed understanding of what the underlying space is. And so what I encourage us to do is make sure that we know what our underlying space is in a network. And sadly, we don't. And so in networks, any space goes. And that's kind of where you get these sort of crazy sort of fits across different sets. And these are all three images of the exact same network, all in the published literature of the Zachary Karate Club. And so some of these spaces, some of these underlying spaces, I would argue, are no different than a randomly permuted scatter plot. You don't get anything out of this image that wouldn't be better had by some of these other images. So if that's the case, what is the, I'm going to skip some of this, but what is that underlying space that we're trying to capture? There tends to be three underlying spaces that people tend to use. And there's a tree-based layout, a space-based layout, and a fixed coordinate layout. A tree-based layout, or some kind of a hierarchical layout, there's a fixed meaning to the y-axis. It's authority, or it's rank, or it's something. And then the x-axis is your free space to move. And that's used to essentially sort the lines to try to minimize crossing. And so whatever's going on of interest is on this y-axis, and we can say, you know, there's the general, there are the colonels, there are the majors, there are the captains, and there are the sergeants, right? So we have it down, we understand where it fits, and it works perfectly well. A force-based or a space-based layout is where you try to find a fixed length to the edge set, and you put nodes near each other if they are tied to each other, and they're far apart if they're not tied to each other. Now, some kinds of relations have an inherent ordering to them, and we should exploit that. So in a hierarchy, you want to put that so that the top nodes are at the top and the peripheral nodes are at the bottom, and take advantage of the flow of authority from top to bottom. Or you could flip it and go from bottom to top, or you could make it a circle from center to periphery. There's lots of ways to do that, but you have a meaning, an ordered meaning set, so use that to your advantage. It makes no sense to put that in a space-based layout. In a space-based layout, I can find the root of this tree if I look really close and find the node that has no incoming edges. But why make your audience do that, right? So don't force them to do something they don't have to. A space-based layout is best when you're trying to emphasize the clustering and the heterogeneities in the network. When you're trying to make sense of how this thing's not a single ordered, but there's different pockets in the network. Those pockets get turned into clumps or clusters in a space-based layout. So what you see in this case is that these nodes that have transitive closures, they're all going to be drawn into each other, whereas the nodes that they're not connected to or have these disconnected sets are going to be pushed out to the side. And so that sort of notion of a space-based versus a hierarchical layout is very useful for capturing that kind of social closure. Now I can do a tree-based layout on this kind of network, but it's noise. Like there's nothing there to be had that's of substantive use. Now the obvious choice, humans typically exist in spaces, is to think about a fixed coordinate system, and the classic fixed coordinate system is a map. This is a network of hospital exchanges. And so you can see major regional hospitals, like that's probably Bozeman. Bozeman sends out to Helena and some places in North Dakota, and there's Spokane, and so here's Seattle. And so you have these places, and a map works because we know the space, right? We know this geography, and I can point to where Denver is, and or Utah, and what have you. But this model doesn't particularly fit the data. And I had this little fit score I've introduced in the bottom. What the fit score is, it says if this model is working well, if it's working perfectly, then there ought to be a one-to-one correlation between the social distance and the physical distance. And so that would give you a correlation of 1. If the physical distance mapped onto the social distance perfectly, you would have a correlation of 1. And it turns out that those distances are easy to calculate, and so we can do that. And so the geographic case in this particular case has a correlation of about 0.5. So the geography constrains the network, so it is positively correlated. But if I use a standard geometric or a space-based layout and let Fruchtem and Reingold put people near where they're at, you get a much better fit. And it's what you end up discovering is essentially Chicago, the sort of center Midwestern piece, actually pulls together the whole country in the middle, and you get those shortcuts between it. Now that fits better, but your audience knows what geography is, and so I would argue this is probably a better representation if you're trying to understand how hospitals are working. But once we have that fit model, we can think about it. Now another fixed coordinate is a circle. Circles tend to be useless, right? So a circle doesn't work very well by itself, and you can see it fits pretty poorly. The main thing a circle will do and circles were originally used when you were making sociograms by hand because A, it was easy to do, right? You can put nodes on a circle. And if you have a really small network, you can trace all of the lines and the tangents don't get hidden under the nodes. And in some cases, for really small networks, that might be useful. Now, one time I have found circles useful is when I let the whole network lay out as a space. This is, again, that hospital network. So I take that space-based layout and then a community detection on top of it. I cluster those, and then by taking a circle out of each one of those, I can see some extent to which there's density in the middle. There are other ways to do that, but that might be one reason you could defend it. People love these. I hate these. These are chord diagrams. Chord diagrams are the pie charts of the network world. Don't use them, all right? I can think of almost no reason to do it. I'm sure someone out there can find one for it. The main thing the reason that magazines and newspapers like them is because it's just so much color. It's like pop, right? But you can do better than that. You can save the color without the lack of any kind of flow information. So there's a whole thing here about distortion, but in the interest of getting you out of here, I'm not going to go through that too big. I'm going to focus instead on trying to solve a couple of problems. And so the first problem that we have is scale and density. And so this is that example I showed a couple of days ago about co-voting in the Senate. As a network, most of this information is completely redundant, right? In this case, a senator is a senator is a senator. What you really learn is that Democrats don't get along with Republicans. You don't need this element of information to get it. And in fact, you'd be better off probably looking at a heat map. So if you properly sort a heat map, you can extract from the sociogram and have much more information. And what you notice is that then these nodes in the middle that are not sort of swamped by these clusters become perhaps a little more apparent, and you can sort of interrogate that one way or another. The other thing you can do, this is the same graph that Tom showed a moment ago, is that you can instead look at a process on the network instead of the network itself. And so that we don't really care, if we really care about diffusion processes, let's look at the adoption curve as opposed to the network, and maybe you'll learn more about the underlying setting than you would from just the network itself. And I like doing the adoption curves from all possible networks. So let's imagine what the adoption, all adoption curves could look like on a network. This is your degree distribution right here. So this is the number of people who have ties, the number of people at each one-step distance, the number of people they could reach. Well, after a certain set of steps, you can see that some set of the nodes in this set, the bulk of diffusion would happen on that kind of a speed. But there are some places in this network that move really fast, others that would take a long time to go. It sort of gives you a sense if a diffusion story is what you want to tell, this kind of a plot might be more useful. We've used these kind of tree-based structures to help highlight the importance of things like concurrency in the spread of disease through networks. In this case, we wanted to know how essential concurrency was for driving an HIV simulation. And what we discovered was that you could just plot whether the edge itself was concurrent. Maybe if you squint, you'll see a little more concurrency on the left or on the right there than you do on the left. But if instead you ask, where is concurrency upstream of me in the network? Then what you discover is that these big pieces require having concurrency upstream in order to open up the pieces downstream. And so it becomes immediately apparent that the path level concurrency is helping to drive the flow in these big spikes. We thought for a minute whether or not it'd be useful to add in the cross edges, the ones that didn't carry the simulation, but it seemed to just clutter the story, so we ended up not using it in the paper that we published. The second major problem then is dynamics. How do you display a dynamics on a network? The obvious choice is to animate, and so we have a whole paper on the way you might animate networks. I love network animation. I think it's really cool and fun to do, and Dan McFarland's data that Tom Wolf showed a few days ago, if I remember right, is a nice example of that. The one problem with animations is humans have pretty poor visual memory for movement, so we don't do a good job of being able to remember where things happen. So the kinds of questions that people can get out of this are really to help us see pace of change. And so if you think about what these networks are, this is again that sex network. What you're seeing here is that a lot of these relationships, the question was, who have you had a romantic relationship in the past, that's been ongoing in the past 6 months? A bunch of those relationships are really old. That's the ones you see sort of coming on here now. But then a lot of them, like these are adolescents. These relationships didn't last very long. Boom, boom, boom. They pop up there and they happen. And then the survey ends. And so it's not that everyone dies. They're just truncated. So it's not that there's a massive die-off in relationships, but we stopped collecting the data. So you want to be aware of that. You can take the qualitative version of Scott's tergums and say, how do relationships change over time, and just plot the panels over themselves. And ghosting does a nice job of showing where the new relationships happen. So if you just go through the network, you can build it up one wave at a time. And we found that to be a pretty effective way, especially if people have it interactive so they can flip through it and see where the changes occur. The key to making this work is to effectively lay out the graph. Sorry, in the wrong direction. Lay out the graph in its most dense, and then save those coordinates and stack on top as you go backwards. So essentially you build the visualization backwards from knowing the future to see what the past looks like. It's a little trick. Another way to do it is to use these things called multi-layer networks. And so we create a layer for each dynamic wave, and then we connect people to themselves through time. And so in this case, you're able to use the exact same space layout, and by weighting the within time edges much heavier than the between time edges, the networks almost always fan out temporally because heavy-weighted items within waves can't be connected to heavy-weighted items in a next wave. And so the weak ties essentially implicitly order the spread over the time. And then you just have to rotate it to get it to be a sensible order. And so that's pretty nice. This is a split in a baboon troop, actually, over time. And so there's this one baboon that's holding together the set, if I remember correctly. I thought I skipped these. You saw this talk yesterday, so I'm not going to go through that. I'm going to end today because this is supposed to be the world's fastest thing, just to sensitize you to the art part of this. And so there's a certain scientific element of this, which is you need to make sure there's a data fidelity. You don't want to lie where you can. But you have enough space and freedom to try to figure out like how you make the choice. And so when we were writing the text, we were trying to figure out our visualization chapter. We thought, can we improve on some of the originals? And so like I love this graph. I thought it was really pretty. But it's not the most sort of informative network. You have to kind of read the ethnography to really see what's happening. The first thing you need to know is that in the 1930s, when he was writing this, red meant positive. So red was good. It wasn't negative. We tend to think of as a red tie as a bad thing. And so, in fact, the negative ties were in black and the positive ties were in red. And what's interesting, of course, is that CM here, everyone dislikes CM. So that's the central story of this particular network. And CM has one lonely reciprocal friend in the world. That's what this little X means. And the only other person that likes CM dislikes or likes CM's friend dislikes her. So you end up with this sort of centralized structure around this story of positive and negative ties. And the question is there some other hidden alliance structure built into this network? And so we thought for a while what would be the best way to display this network. And our original thought was to say, well, let's just see what happens when we use some modern layout techniques. And they're fine. It's not clear they do any better than the original. And they kind of end up with some stacking on top of each other that's not particularly nice. We do like the fact that you end up with, I kept the colors as the original just to make it comparative. But I do like the fact that you can sort of get a bit more of the sort of notion of these nodes on a periphery and a similar periphery. But again, this alliance structure idea is not quite there, so we wanted to see if there's something more we could do with that. So we thought, well, let's just try doing it by only taking positive ties as our source. That's the thing that is sort of the backbone of our network. And then layering over it negative ties. So then we can at least compare the two to each other and see how one dislikes the other. But again, combined is kind of a mess, right? It doesn't really work. So at this point we thought, well, maybe Moreno had it right. We should have just left well enough alone. And so we spent a lot of time thinking, well, we could perhaps do something that if it really is this sort of dislike of CM as our story, let's center the story around that and say, well, what is the sort of structure of dislike? So we just flipped the script there. We said, let's let the network lay out by the negative ties and then plot the positive ties over it. And what we discovered was that there's a community detection on top of it that there are, in fact, 3 pretty nice bounded groups with a lot of positive internal ties and almost all negative ties between them, and then some sort of noisy nodes on the edge. And so what you end up with in this case is that this entire cabin, and that's what this is united in their dislike of this collector, which would otherwise be opposition between the set. So we were able to do a nice job, I think, of making a new story, and it pops out a little cleaner by focusing on this one element, which is the dislike of the central node. Now you'll notice what happened in the course of doing this, right? Is I've just told you, I've woven a story around this visualization because I read the case and we thought about it, and we think this story fits, and I generated an image that fits the story I told. It was a reciprocal process of working on that. Some people would dislike that strategy, that it's somehow not scientific, that it's journalistic or some such. I think that one of the advantages of network visualization is that we're not lying about anything here, but we're using our own judgment to help inform what we're seeing. And once we realized that the negative ties were the story and allowed that to be the core thing that sort of centralized the image, we then layered the positive ties on top of it, and we got something that looked a lot like this. And then I went in by hand, and I just organized the groups to be a little more clear. And so for small networks, you can do that. You can go in by hand and do it. For really large networks, you need to do a little less of that, but it's just because it's not tenable to do. But I want to encourage you to have that kind of an approach to your visualization strategy. That what you're doing is you're trying to go in and tell a communicative story about your networks. You're trying to tell something that helps your readers understand what you see in the network. And we've done that now with sort of every sort of bit we do. I think this is an improvement. It lacks a certain historic, I don't know, antique quality that I love about the original, but I think it sort of captures much more of the information and then a little bit more than we would have had originally. So that's what's there. And again, that's the world's way. If you go back in the notes, you'll see I have a much longer version of this, and I'd love to chat with you about the best strategies to get these things. One thing I will point out is that the distinction that you don't get to the last element here without going into something like Illustrator or some other your favorite graphics program and doing a fair amount of handwork. So that in order to get the coloring the way you want it, we deliberately decided to keep a font that's kind of similar to the handwritten ones, just as a nod to the historic set. So those kinds of elements, R is not going to do for you. So from an exploratory network analysis, where you're just trying to learn what the world is, it's best to keep an eye on these sort of notions of fit statistics and understanding where the network, how the network is represented on the page. And I think that's, I would stick with that as the thing you want to do. But when you move from exploratory analysis to presentation, take the time, once you've learned what the story of your network is, to make sure you communicate it and make the image worth the page space. And with that, I'm going to turn it over to Gabe, who's going to give you how to get some of this stuff out of R. And while he's switching over, I'm happy to answer any questions people have them. Please.
You mentioned not necessarily needing to put a full network and publish it because maybe release too much data confidentially. How would you go about the same process when doing partial?
Yeah. So in that case, what you want to do is figure out what part of the network do I need to show, or what simulated version from the network do I need to show, and then I would do the exact same kind of process. I would treat that new object that I've created as if it were real and do my best to show it. I think with fake data, the one thing that you can really do nicely is small multiples. So you can say, here's an ego network around a drug user, here's an ego network around one who has support, here's one who's experiencing homeless, and you can go through all those different features and be iconic about how you set it up. Okay. On that thing on the top row, go to laptop. Oh, all right, back to that.
Can you give him the mic?
You should be on. Oh, you blanked the video. Nope, you did not. Classroom computers where we were. All right, and now we should just go over to laptop. You're not plugged in.
No, I was going to say, I feel like I'm what's standing between you and barbecue at the end of the day, and I'm honestly feeling scared. So yeah, I just wanted to reiterate a couple of things while I'm putting this on, which is that if you're opening my script, at the top there, it will say, oh, you can see now. It should say source and visual. Stick to source. Visual is not great for anything, really, but definitely not for the purposes of going through the script. Something else is be careful about doing too much when you're doing a visualization. I'm very much one of those people who put too many things into visualization. I'm like, there could be shapes and colors, and the nodes are going to change, and the size, and that's never going to work because it's a story, right? Every picture is supposed to be a story. It's supposed to be part of an argument. Something else I want to emphasize before I start is that, and Jim kind of said this already, there are two kinds of visualizations in my mind. There's the gut check visualization, and then there's the final visualization you're going to put in your paper or in your presentation with funders. Probably even that one works really well. And so those are very, very different, and you're going to use different tools for it. I would not try to make the beautiful final visualization every single time you're making a visualization. If you're trying to gut check, a simple visualization is great. And most likely, I'm speaking from experience here, you're trying to procrastinate actually moving forward by making the picture nice. I know that.
Trying to learn what you're not procrastinating.
But by making it simple, sometimes that's more revealing of that gut check moment. And yeah, so there's no true visualization. There are no true layouts. There's no truth to any of this. It's not like any of it is a lie either, but it's all an argument. And so it's going to fit as a part of your story. Think about it like an argument. Okay, so now let's move on to the R script here. So what we're going to do in this R script is mostly going to be how do you do this gut check visualization stuff, and then maybe I'll get us started like a tiny bit on some fun visual elements. But we're going to stick to the basics. We're going to import a bunch of stuff up here as we usually do, and we're going to be using, there we go, all the warnings in the world. We're going to be using a high school network, which is a fake high school network that you've seen in a couple of other tutorials. And they're all coming from IdeaNet. Another great thing about IdeaNet is that it includes a bunch of different example networks that you can use, all sorts of stuff. So that's what I'm going to run here. I'm going to run NetWrite, which is part of the IdeaNet package. Again, this whole conference, just a big sales pitch for this. If you're not convinced at the end of this, then we failed at something. Okay, so all iGraph objects, which is what we're going to be using here. So this net object right here is an iGraph object. You should be deeply familiar with these at this point. They have a basic integration with the plot function that's in base R. And so we can take a look at it here, and you can see the first thing I'm doing is adding a couple of colors that I like to saying, hey, I want to take 3 colors out of this set of colors, and I want to color the nodes by what sex the nodes are. In this case, it's a binary. And when we run that, that looks okay. And in fact, if you do a basic, and we can like blow these up a little bit. Well, there we go. That looks actually pretty decent, right? And I had to do a tiny bit of work. By default, I had to take away some of the labels. I had to maybe make some of the edges a bit more transparent. And that's pretty okay. A couple of things that stand out here. The number one thing that you'll probably realize when you're plotting a network is that isolates and like smaller little pairings on the side will never really help you to tell a good story. Typically, not always, but typically we'll be working with the main component or like the principal component in the middle, right? That's not a hard and fast rule, but it allows you to focus a little bit on, usually we're also interested in the processes that are happening in that component anyways. It's more where the structure is happening. Yes? Let's see here. So first of all, that was all a test. It wasn't me forgetting, and you win, I guess. I also asked it to size the nodes by their total degree. So this is a directed network of a high school where students are nominating each other for friendships, right? So total degree in this case is how many ties did they send out and how many ties did they receive. The sum of that. And so you can see kind of intuitively that the ones that are in the middle of this four-spaced layout, which is what we're using by default, what is mostly used by default, are bigger because typically centrality is associated with degree. Degree centrality is sort of one of the main measures of centrality. In this case, I'm laying it out with like a default force algorithm, but we'll be getting a little bit more into this. But I kind of want to get away from the basic R plotting since we don't have a ton of time. I want to focus on like the good stuff, which is ggraph. For years, I thought of this as gggraph because of ggplot. But basically, this is the sort of traditional, the most used way to plot any kind of data in R is ggplot. This is the same language and the same strategy of layering things, but added for networks. So what do I mean by layering things? And if you're familiar with ggplot, you'll know exactly what I'm talking about. But we're going to start with one layer, which is I'm saying, OK, graph this network. I'm going to tell it what network I want it to graph, which is still this network. And say, lay it out with the same layout, the same four-space layout. We'll look more into those afterwards. And that's it. And what it's going to tell me is, like, I've done it. I'm done. Not much there. The reason why is because this is expecting us to layer things on top of this initial image. And by layer things, I mean points, right? So points are usually how we want to think about nodes. So if I add a little plus sign here, then I go to a new line and add geom node point, I'm saying all those little nodes that were in the network, add a point at the specific location that this four-space layout would set them. Now, again, this is not hugely useful because we don't know the connections. So we're missing still one more element. We're going to add the connection. So I'm going to add another plus sign up here, go to the new line, and add geon edge link. And if I add these, now we're much closer to an actual network. So you might ask, like, what is the benefit of this over the basic R? That's a little bit hard to put into a summary word. The basic R plotting, you can totally do with, but you're kind of fighting against the tide. This is starting you from a more basic level and asking you to work your way up, but as a result, you have much more control over what you're doing. Okay, so let's keep going a little bit. Oh, we don't really like that gray background. The gray background is like making it a little bit harder to read. And so at the end of the layers, so you can see the first layer, we had nothing in it. We added some points. We added some edges. And now I'm going to add this thing called theme graph, which is basically just the aesthetics. And that's going to make it look a little bit more neutral in the background. So far, so good. Before we move on, I'm sorry if I'm going quickly. I'm trying to fit everything in, but pretty simple. Awesome. Like I mentioned at the beginning, you might have noticed this is exactly the same network that we had at the beginning, right? Same data. You can see it's the same layout, exact same thing. I mentioned that we had problems with all these things on the edges, which are really not giving us much better information. If you remember the visualization of the high school that is from Jim's original paper, they put all of these nodes on the bottom right. A good example of a gut check versus a paper check. If you were interested in this structure right here because you're interested in measurement, you have a problem with your measurement of the nodes, for example, you want to check the picture. You only want to check this main component because that's where most of the things you're measuring is coming from. You're going to ignore all of the ones on the edges. But in the final paper, maybe you want to add them all into a little box down here that says, hey, this is how many dyads there are, this is how many triads there are, how many isolates. So this could be one of the differences between a final product and a gut check. The way we're going to take away all those things on the edges here is actually, so we're going to grab just the largest component of the network, which is actually included in IdeaNet. So in IdeaNet, when you put your edge list and your node list and whatever other component you need, it's going to take out the general network with everything in it. It's also going to do a subset of the network that's just the main component. And it directed also the largest by component. And so that's what we're going to use here. And that's a little bit more visible, right? And these are all choices. You might want to keep the isolates and everything around as well. OK, so now we've actually constructed the network. And we're going to do exactly what I said you probably shouldn't do, which is we're going to add as many things on top of that. But just because I want to show you it's possible, OK? But again, I want to repeat, the important part is, do I really need to add colors to the edges? I see this in papers all the time. People will color the nodes, which is nice. That's interesting to see clustering of nodes. And then they'll color the edges the same color as the destination node or the node it comes from. That's not why. That's not necessary. I don't understand that. OK, so one thing that I'm bringing back in here is directionality. So if you notice here, at the very beginning, I said we're looking at a directed network, right? So if somebody nominated, one of the students nominated someone, that other person did not necessarily nominate them. In this representation of the network, I can't tell what direction the relationship is going in. So what I'm going to do to add in that relationship is I'm going to go into the layer where I did the connection. If you remember it called geom edge link. I had it up here. I'm not adding anything new, right? This right here. And inside of that function, I'm going to add some arguments. And those arguments are going to change the aesthetics of that particular layer. So in geom edge link, open parentheses, and I'm putting some arguments. One of the arguments I want to put in is add arrows of a particular length, particular angle, etc., and then make the edges a little bit more transparent. Same thing here in the points. I'm going to say add the points, but on top of that, add color, a different color for each grade, and then change the shape depending on what sex they are, and then have a basic size for it. You can see here that I added another layer. This is where the metaphor kind of loses, because this is actually not adding anything to the graph, but it's modifying this layer right here, the colors. And so these are all things that we can talk about later if you want. This is all sort of the ggplot logic, but you can still think about it as layering things. So this is the two most important layers, actually showing stuff about your graph, and then you're sort of modifying the aesthetics of it. The very last one is just removing the legend.
What's alpha?
Alpha is basically the setting that will determine how transparent the particular object you're visualizing is. So if I had put it up here in the nodes, it would make the nodes more transparent. And I put it in the edges, it makes the edges a little more transparent. The reason that you want to put your alpha transparency on edges is nice is because when there's a lot of them that overlap and they're fully black, it becomes very, very messy very, very quickly. It's a nice thing to play with. Okay, so now we have our high school network and we have a little bit more information. This is already starting to be a little bit useful, right? We can see some of the clustering by grade. These are all the 7th graders, really, really like clustered on their own. Yep, they're doing their own thing. You can see actually that like the seniors here, they're a little bit more spread out, which is interesting. 8th graders are on their side. You can maybe see some sort of sex things here. So there's a cluster of round nodes here that are all together and all seem pretty central to the 7th grader that are all female. So this is maybe the early Mean Girls setting right here. All the boys are on the edges. And we have the little arrows if you look, right? Arguable whether or not the arrows are useful here, but depending on your use case, you might want to focus on one of these areas and look at the arrows. Okay. Let's add some size here. I'm going to go back to adding size, but this time instead of adding just total degree, I'm going to add in degree. And that's because when I looked at this picture, I was like, oh, I'm interested in this group. I feel like the Mean Girls metaphor, all social networks people go to all the time, but it's true of social life. So. And now nodes are going to be bigger. The more people nominate them, the bigger the node, right? So you can start to see who the popular kids are. And maybe my story isn't so great. There's a really popular guy out here. Maybe this is who said the deviant group? I can't remember who used that term. I find that pretty funny. There's a really popular 8th grader. So we're starting to add some information here. But you can look at this too, and another thing that you can notice is that there seems to be some people who connect grades, right? There's these bridges here. And so you can start playing around with, maybe I'll put a score that better reflects those kinds of bridges. So in this case, I'm going to score the nodes by betweenness centrality, right? So this is what I'm putting right here in the size argument. But notice that I'm also multiplying it by 2. And that's because betweenness scores tend to be smaller, and the graphing backend doesn't really understand how to scale things necessarily. So it needs to be scaled in a way that makes sense. And usually that's like integer points, like 1 to 10 or 1 to 20. So I'm going to multiply this so that it's a little bit more understandable to the graphing software in the background. And now we have some more information. So you could tell maybe a different story about who has high betweenness centrality in the school. Okay, we have 7 minutes left. But the point is that that's the iterative process you want to go with. This is the gut check thing. Like, what is interesting about this high school? Is my theory about this high school true, interesting, all that kind of stuff. Layouts. This whole time, I've been using this layout KK, who stands for Kamada Kawaii, I think. You can play around with those. There's all sorts of layouts, hundreds of them. You can just Google and play around with them. There's some that are a little bit more that are different, that are not force-based, and Jim showed some of them in his presentation. Here I'm going to pull out data from a tech firm, and it has multiple relationships that they ask these employees. One of them is, who do you seek advice towards? So instinctually, when you're like, okay, my network is people in an organization, and the connection is, who do they seek advice from? You're thinking, probably some sort of hierarchical visualization is going to be useful. You can see here I'm still using ggraph, but this time I've changed the layout to dendrogram, and I've set a direction. And so instead, what we're going to get is something that's maybe more useful. And you could work on this to make it a little bit better, especially in terms of the labels and where they are. But who's asking advice of who? Right? In a force-based layout, this wouldn't maybe make as much sense. Although maybe in this case it would, yeah. So in this case, it's the in degree. So this person, sorry, it's the, I believe it's the in degree? Yeah, yeah, yeah.
Whenever an algorithm is trying to do a hierarchical layout, its first go-to is to use a directed acyclic graph. If your graph is not a directed acyclic graph, it finds essentially starting from leading edges, going as close as it can to a directed acyclic graph, and lay out based on that. And so usually that'll be the leading edges, sort of leading the purpose of the layout, and leading the edges that are the least likely to have other edges coming into them. And so it creates there's often a little bit of noise in it, so it's possible if you run this again out of a particular layout algorithm, it's possible if you run it again, you get a slightly different order, unless your network is strongly hybrid.
That I learned something today. The one thing I will say that you experience with this sometimes is there's different sort of choices they can make about the source, right? So like which person, so there may be people who are comparable or like structurally equivalent in this advice network. And so which sort of branch it decides to go down can shift, and it will actually give you a warning and tell you.
I mean, using something like this, there's like 6 different hierarchy layouts in iGraph. The convention is layout underscore width method. And so there's a bunch of them in there. And one of them is something like, I don't know the dendrogram one, but there are a number of different ones that have been organized around organizational charts. And so if you didn't know which organization, what they were, these things would probably do a pretty good job of telling you who's in charge, assuming with modulo the accuracy of your data.
There's like an empirical question, right? Like if you don't know someone's job title, but you know how many people nominated them for advice, then that's a really good marker of who's in charge. Although maybe you'll have a surprise, and somebody who's,
I've been trying to get Duke to give me the organizational chart for the university. They won't let that thing go for a second, because as soon as you can see all the layers of hierarchy and administrators at the university.
And people who aren't useful in that?
Yeah, exactly. They won't let that out.
I didn't say anything, dude. I'm being audio recorded. Yes, and then, so my following example was, what if we're looking at people who are friends? So this is the exact same data set, but I'm pulling of this multi-layer network, I'm pulling who is friends with whom, right? And I'm also going to look at it as a dendrogram, the sort of default dendrogram. And it's doing something, but it's maybe not as useful. Although in this case, you could maybe find some interesting stuff. But you can see this person is flying over to 127. Maybe a force-based layout would be better. Okay. So
It's a whole fascinating field of graph layouts. And it turns out that this kind of problem is really hard to do.
Yeah.
I mean, it's the simultaneously optimize the ranking on a hierarchy and minimize the edge crossing. It's a really difficult. It's akin to the clustering problem for community detection. It's just really hard to do, and to make it readable.
Yeah, do not interpret me as saying that the people who do this aren't doing a good job. This is just really, really tough task. Okay, so I wanted to move on to one more thing because I know a lot of people are interested in ego networks. We got 1 more minute, so I'll show you an ego network. Okay, there's a package, an additional package, I know, called tidygraph, which basically allows you to manipulate your network, whether that's a StatNet object or an iGraph object, in particular ways that are useful. And it has pretty good integration with this package we've been using, the ggraph package, and allows you to do some things. So you could have done this without tidygraph, but I'm giving you code that I think does this efficiently. The idea of what I'm doing here is I'm grabbing our network, our original high school network, and I'm saying, for the, give me all the distances that nodes have from the node that's labeled number 1, that has ego ID number 1, right? Give me all those distances from that node. And then I'm saying, lay out my network so that we're focusing on person number 1. Okay, and then I have a couple of other aesthetic things that you're welcome to go through and if you want to copy them. And then you'll start to get things like this, right? So you can focus on specific parts of your network and then say, how far do I need to go to capture the entirety of the network? It's a sort of a way of, there's measures that will capture this, like how far does one node have to go to capture the entire network, right? This is a way of visualizing that. And that'll work great for if you have an ego network, right? It doesn't necessarily need to be an individual person inside of a network. An ego network is, a full network is just a compilation of a bunch of ego networks in a lot of ways. So, last thing, and then we'll go to barbecue, is that you might want to facet your data, which means you might want to split your visualization into multiple different visualizations that are subsets of the data you're looking at. So in this case, for example, I'm just going to run through these. You might want to split it by the node attribute. Are the nodes male or female? In this case, we're looking at the network from the point of view of the women in the network and from the point of view of the men. You can see that there's a clear difference in the structure of the network from each of those perspectives. You can see that like really dense clique here for the women in 7th grade. You can also facet by edge attributes. So are they different kinds of edges? In this case, we're going to go back to the Strazis and the Medici, right? So on the left-hand side is the network of the Florentine families, their business ties, and then on the right-hand side are their marriage ties. That can be really useful when you're comparing, you have an inkling that maybe those two things are going to be correlated, maybe. This is a good gut check. Or maybe they're different in a specific way. Maybe some people are more central to one or to the other. And then you can do interactive stuff. So I'll just leave you on, this is what, sort of an example of what, let's see here. This is the Medici families and how their marriage ties are moving and dissolving. So this is the kind of thing that you can do the dynamic network. Okay, I don't want to keep us a single extra minute. I know everybody's like, please let me out. But if you have any questions, I will be down there, so I'm happy to answer questions.
So the barbecue folks they'll start around 6:30. They're coming, getting us the world set up and such. And so we're going to get our stuff, we're going to get the stuff. So go home, change into jeans or whatever it is you'd like to do, or just walk around campus, and we'll see you downstairs again from 6:30 to when we're tired, drinking beer. So we're going to be tired before you walk, but that shouldn't stop you.